Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
SBMicro, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. SBMicro promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components, since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. SBMicro members have also been significantly investing in the establishment of research and development centers. An example is the El Dorado Research Institute, located in Campinas, state of Sao Paulo. El Dorado has the country's first semiconductor prototype laboratory. Another example is the ITT chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces the dependence on global centers of semiconductor components. There are many opportunities. Only in the Internet of Things field, the economic impact expected until 2025 is about 10% of gross national product. Semiconductors are the brain of the electronics industry and the heart of the technologies that move the world. Brazil is already part of this important universe. ABCME believes in knowledge, innovation, and people as the keys to identify new technologies. Above all, ABCME believes in Brazil.
somewhere, maybe right at this very moment, the next technology breakthrough is about to inspire the next generation of minds, thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good, because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. Their top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our ESOF electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3 of the world's high-frequency electronic designers, empowering customers to confidently bulletproof designs long before they're built. As the physical prototype is made, customers turn to Keysight once again to validate that it works properly in the lab and in a variety of real-world environments. These complex tests help prevent losses that technology companies may face if there is an undetected defect hidden in their product. The device is finally ready for mass production, and Keysight is ready to help its customers get the latest, greatest technology into the hands of eager buyers. Tens of millions of units are at stake here. Customers rely on Keysight to keep the line moving with accurate test solutions and tools to help them maintain quality. The result? A bug-free, cost-effective, high-quality product in the hands of people who need it. Faster. If there's a signal to be measured, Keysight is there, from satellites to base stations to mobile devices. Our job is to ensure the signal is clear, true, and reliable. It's what we do for communications and beyond, energy, aerospace and defense, computers and semiconductors, automotive electronics and safety, industrial applications, education and research. In fact, the minds of Keysight have been behind the most important technology breakthroughs of the last century. And today we offer world-class services along with the broadest design and test portfolio of any company in the world. With our global network of experts, we provide an emerging array of services to accelerate our customers' business goals, including calibrating multi-vendor test instruments, managing asset portfolios, and providing training, consulting, and other professional services. As a premier future technologies enabler, partnering with customers to help them move from design through manufacturing faster and more efficiently, no other electronic design and test company is better poised to help deliver what's next. First.
Each new day, technology is more and more present in people's lives. Everyone is more and more connected. Technology does not stop evolving, advancing. Smart modular technologies is at the very heart of all this evolution, developing and innovating in the semiconductor industry. with a large and modern production center, advanced equipment, high tech, high precision tooling, machine-to-machine communication, robots, training and advanced manufacturing, prepared for the fourth industrial revolution. Industry 4.0. Smart delivers products that form a tripod, processing and storage, communication, energy. More than 15 years producing semiconductor components for the world's largest manufacturers and dominating the chip packaging technology in Brazil. Memory modules at the forefront of high performance. Lithium-ion polymer batteries provide power to the most renowned devices in the mobile communications market. Approximately 670 million reais were invested in the development, design, and implementation of semiconductor components, such as memories for smartphones and other high-tech memory integrated circuits. And additional investment that can reach 700 million reais by 2021 is already planned. Smart is a global company and is proud to have chosen Brazil to be its technology center for semiconductor components packaging. Strategically located in the city of Atibaia, state of São Paulo. Smart also has a research and development center dedicated to its operations in South Korea. Products with high standards and excellence. 250 million reais have already been invested in research, development, and innovation of products and manufacturing processes. An example of this is the unprecedented investment in the creation of a semiconductor prototyping line within the El Dorado Research Institute in Campinas, state of São Paulo. The worldwide technological evolution does not stop. The priorities for the Internet of Things are already defined in Brazil. Smart is part of the National Internet of Things plan, developing innovations to keep at the forefront of all this evolution. People recognition, training and specialization. Professionals with the highest levels of academic background. The challenge of further driving and developing semiconductor technology is the challenge of creating the future. Smart works unceasingly to be at the front line of this future. Think memory. Think smart. Smart modular technologies, developing technology and projecting the future in Brazil.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
What sparks innovation? Is it thinking bigger or smaller? Does it strike fast or slow? Is it a flight of fancy or a stroke of genius? Innovation is everywhere, on desktops, in pockets, on wrists, in us. Innovation answers big questions, finds inspiration anywhere. It connects great minds, imagines the impossible, and propels us forward. At Keysight, innovation inspires us, fuels us to redefine precision in measurement, to surface insights, to remove barriers so the next stroke of genius is yours. We are Keysight. We accelerate innovation.
Designing state-of-the-art millimeter wave products, whether for 5G, defense radars, or satellite communications, requires expanded test systems. Applications at millimeter wave frequencies require wider channel bandwidths and multi-element antennas to overcome increased path loss, which must be tested using over-the-air test methods. Over-the-air testing has traditionally involved more test equipment, more measurement uncertainty, and difficulty getting accurate and repeatable measurement results for chipsets and network equipment. Until now. Testing applications at millimeter wave frequencies is about to get much easier with Keysight's new VXG microwave signal generator. The VXG is the world's first dual-channel 44 GHz vector signal generator with 2 GHz RF bandwidth in a single box. Featuring a dual-channel architecture, the VXG allows quick switching from blocker and interferer tests to dual-channel MIMO and beamforming tests without ever having to touch your hardware. With its ultra-low phase noise and the industry's highest output power, Keysight's VXG overcomes over-the-air path loss challenges without sacrificing error vector magnitude or adjacent channel power ratio performance. The VXG, together with pathwave signal generation, gives you access to a wide range of evolving standards-compliant 5G new radio signals for testing base stations, mobile terminal transmitters, and receivers with channel coding and multi-antenna support. If you are designing, manufacturing, or deploying millimeter wave devices, Keysight's VXG will give you higher confidence in your device's performance, faster. Visit www.keysight.com/find/VXG for more information.
Technology now connects everything and everyone, everywhere. From smart cities to smart clothing, we generate billions of new connections that bring us closer, make us healthier, safer, smarter. But the more connected we are, the more challenging it is to meet our expectations. How do you innovate what's next, first? How do you keep up with the accelerating pace and complexity? More speed, less power, perfect accuracy, tighter security. The pressures to be first and best are greater than ever. At Keysight, we work with you to design, test, and operate tomorrow's most innovative technologies today. We help you adopt emerging protocols and standards before they're defined. We challenge you to reimagine your innovation processes in automotive and energy, aerospace and defense, wireless communications, networking, cloud, and the Internet of Things. We integrate your development workflow to accelerate your next creation. We make your network stronger, and we bring our decades-long insight, research, and expertise with over 500 industry and application experts around the world to help you every step of the way. Our customers are the world's visionaries and innovators. They partner with us to innovate faster across every stage of their development lifecycle and every layer of the stack, making their businesses more productive to gain a competitive edge. They dream, we test. So the next great innovation that connects and secures the world is realized faster than ever.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Everything has something to say, but someone has to make it communicate. talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
ABSEMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABSEMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets.
Just confirm you are looking at my screen. Yes, you are?
Yes.
Nice. So good morning, everybody, or good morning, good afternoon, or good evening. Actually, people from everywhere is with us. So thank you for coming to the Chip in the Fields 2021. This is our tutorials day, which coincides with the Electron Devices Society Mini-colloquium of this year. It is my pleasure to be the chair of this event. I am Marcelo Antonio Pavanello from FEI University, and it is my pleasure to welcome you during the day, in which you have the opportunity of listening diversity of researchers worldwide renowned, and we will cover several aspects. I have some echo here, which is from my own. Oh, I see where it is coming. Here you have an overall program for the conference, and now we are here in the tutorials day. So we are about to start. Our agenda for today, as I've been, We will start with Professor Yogesh Chauhan from Indian Institute of Technology, and then we will move to materials with Professor Mario Lanza from Saudi Arabia coast. Then we will have something on neuromorphic computing, and then we will have a joint presentation with SBCCI tutorials in quantum computing. And finally, we will have a presentation from IBM, Dr. Mukta Farouk, she will talk about heterogeneous integration for AI architecture. So as you can see, we have a variety of themes that are very relevant in the micro and nanoelectronics scenario nowadays. So without further delay, because we are a bit behind the scheduling, I just would like to thank and say a few words about the Electron Device Society that is sponsoring our Mini-colloquium. Electron Devices Society is a worldwide society associated to the IEEE, very famous and very relevant technical society. Electron Device Society promotes conferences all over the world. Our main publications are the Transactions on Electron Devices, Electron Device Ladders, Transactions on Devices and Materials Reliability, and Journal of the Electron Device Society. We have also for our members a very wide number of chapters, not only professional chapters, but also student chapters. And these numbers are not precisely updated, but it is, not precisely updated, but we have about 140 chapters worldwide and 59 in Americas, 43 in Europe. We have Africa, Middle East, and so on. So it is a very important and very disseminated society all over the world. We also have some awards and recognition. So we distribute about $40,000 annually in awards and fellowships to both professionals and students. By being an active member of EDS, you will get free online access to the following EDS publications: Electron Device Ladders, Transactions on Electron Devices, Electron Devices Meeting, which is the most renowned conference in electron devices in the world, and Journal of Light Wave Technology. Of course, it will also offer you discounts on IEEE and Electron Devices Society conferences and publications. And we have a set of additional benefits, such as the IDS member roster and the EDS newsletter, which are publications and benefits that are very relevant to keep you online with the hottest information available in the world. So by saying this, I would like to thank very much Electron Devices Society for giving us the opportunity of organizing this mini-colloquium. I also would like to thank the people behind the scenes, the people in the backstage, Rafael Brum, Lucas Zucchi, and Lucas Mota, which are doing their greatest efforts to put all over the tracks and keeping it working pretty well for us to have this nice mini-colloquium. And without further words, I will move directly to Professor Yogesh Chauhan presentation. Let me just briefly introduce Professor Chauhan. Let me see if you... So Professor Chauhan is a professor at Indian Institute of Technology in Kanpur. He was with Semiconductor Research and Development Center at IBM Bangalore during 2007 to 2010, Tokyo Institute of Technology in 2010, University of California at Berkeley during 2010 to 2012, ST Microelectronics in the period between 2003 and 2004. He's the developer of several industry standard models, such as the ASM, GAN HAMT model, bulk BSIN, formerly BSIN 6, BSIN CMG, and BSIN IMG. For those who are not familiar, these are the standard models for multi-gate transistors, BSIN 4 and BSIN SOI models. His research group is involved in developing compact models for GaN transistors, FinFETs, nanosheet gate-all-around FETs, fully depleted SOI transistors, negative capacitance FETs, and 2D, two-dimensional FETs. His research interests are characterization, modeling, and simulation of semiconductor devices. Dr. Chauhan is fellow of the IEEE, editor of the IEEE Transactions on Electron Devices, and distinguished lecturer of the IEEE Electron Devices Society. He is the member of the IEEE Electron Device Society Compact Modeling Committee and fellow of the Indian National Young Academy of Science. He is the founding chairperson of the IEEE Electron Devices Society chapter and vice chairperson of the IEEE chapter section. He has published more than 200 papers in international journals and conferences. He received the Ramanujan Fellowship in 2012, IBM Faculty Award in 2013, and P.K. Kelkor Fellowship in 2015, CNR Howe Faculty Award, Humboldt Fellowship, and Shwarnajayanti Fellowship in 2018. So as you can see, Professor Chauhan is an expert in the field of modeling. He has served in the technical program of the IEEE IEDM conference, International Conference of Simulation on Simulation of Semiconductor Process and Devices, IEEE is their conference, EDTM, and International Conference on VLSI Design, and International Conference on Embedded Systems. Okay, this is a very brief introduction for the set of contributions for Professor Yogesh Chauhan. So I would like to thank him very much for accepting our invitation to give this talk, his talk during our mini-colloquium. So let me just change the right to Professor Chauhan to share his screen. Just a second, please. I'm just finding him. Oh, yes, he's here. So I have to Okay, I'm being informed that you should be able to share your screen now, Yogesh. Could you please try?
Yeah. Can you see my screen?
It is coming. Yes. Yeah, so you have the ball, Yogesh. Thank you very much for accepting our invitation.
Thank you very much, Professor Marcelo, for inviting me to talk on this topic in the conference. And so today I'm going to talk about FinFET and nanosheet transistors, emphasizing on the modeling of these devices. So this is my group here at IIT Kanpur. I have a large number of PhD, postdoc. This is an old picture. Because of COVID, we have not been able to click a new picture. We regularly publish in journals and conferences, and this is the device characterization laboratory here, where we can do all types of characterization. We work very closely with the industry as well as the universities on different topics, and we really work with almost all the semiconductor devices, semiconductor companies in the world. So let me start here with the MOSFET. We know that this is the structure of the MOSFET. When we apply the gate voltage, this barrier gets reduced and electrons cross this barrier. And that's why we have the drain current flowing here and controlled by the gate voltage. If you plot it on the log scale, we see that even when we have zero gate voltage, there is some off current. And when we apply large gate voltage, there is on current. Our desire is that we have high on current and low off current. So the drain current in MOSFET, and during the on region, you can write this equation, and in the off region, you can write this equation. So what we want is high on current, and this we can get through decreasing the channel length, increasing the oxide capacitance, and increasing this VD minus VTH. And off current has to be reduced. So for that, we have to increase the threshold voltage and play with this threshold swing. And you can see there is a trade-off here playing when we are doing it for the threshold voltage. So what has been driving here is the technology scaling. Each time the minimum line width is reduced in the lithography, we say a new technology node has arrived. And some examples are like 90 nanometer, 65 nanometer, and these numbers refer to the minimum possible metal line width, which can be reliably printed on the wafer. The gate length, actual gate length may be different. And this is started all the way from 10 micron, and we are still going fine with this technology scaling. So at each new node, all the geometrical features are reduced by 70%. And if you multiply the 70 into 70 for area, what we get is the 50% reduction in the area. So now you see that with this, we can have twice the number of circuits on each wafer, and the cost per circuit is reduced significantly. So ultimately, this scaling actually drives down the cost of IC. And this has been driven by Moore's law. So Gordon Moore predicted that number of components per IC function will double every 2 years. And he made this prediction using only these 5 nodes, but it's been pretty much working even till now. And you see that how the transistors per die have been increasing and the minimum feature size has been reducing. So the computing power has been increasing and the cost has been really decreasing exponentially. And it's not the technology, it's actually the economy, the cost thing. So you see the price per transistor on a chip has dropped now. And some people say that it is actually now the price per transistor is 1 character printed on the newspaper. And if we can apply the Moore's law in the aviation industry, then we would have now only paid a penny for a New York to Paris flight, and it would have taken 1 second. Unfortunately, the Gordon Moore's law doesn't work in other industries. So this is actually giving us huge profits to companies, high performance and low cost, and this has been achieved by making everything smaller. And as you can see, the price is now, you can say, $1 nano per transistor. So that's really nothing, or no industry can match the exponential decrease in cost and exponential increase in the number of transistors. So ways to drive this performance and decrease cost is that we actually decrease the pitch. So we bring elements closer. This helps us in increasing the faster signal transfer and the processing rate increases. For the same chip size, now we can have more functionality, more number of circuits. Also, the wafer size was doubling every 10 years, although now it's not doing so. And currently, we are still stuck with 300 mm wafer. And we use less energy or less power to achieve the same function. So in the last 45 years, you see that price of memory or logic gates has dropped 100 million times. That's really, this rapid price drop has given us new applications. The primary engine which is powering this proliferation of electronics is the miniaturization. So we have more circuits on each wafer, which gives us cheaper circuits. And this also is instrumental to the improvements in speed and power consumptions of ICs. But there are some problems. One is threshold voltage roll-off. So you see, if we decrease the channel length, the threshold voltage, which we actually designed at this, let's say, and at some point now it is rolling off. And this is coming because the barrier height is decreasing. Another problem is the velocity saturation effect, and short channel devices, now the VD set, which we might have calculated using long channel effect or long channel MOSFETs, now it is decreasing. So the current gets saturated much below the VD set. And this minimum value of subthreshold swing is now is stuck at 60 millivolt per decade because of the Boltzmann statistics. And that means the off current, if you do some maths, will be some 100 nanoampere W by L into 10 to power minus VTH by S. So to minimize the off current, we have to increase the threshold voltage, but that's not an option because the on current will also decrease, and that will result in low speed. We should reduce this S. That means we should increase the COX. So let's use thin oxide, which has been done. Decrease the seed depth, play with the substrate bias or low doping, and decrease temperature. That means put these ICs or computers somewhere where you actually have lower temperature. So other problems which have been there are this lateral, which is the doping. So there is this encroachment coming from the depletion layer from source and drain, and that causes this threshold voltage roll off, and this has been avoided by halo doping here. So there are small barriers here which actually helps in making this VTH roll off curve flatter than it would have been without these halo doping. Another important knob which industry has placed is the strained silicon, which helps in increasing the mobility. So when these two materials where the silicon is over silicon germanium, you can see there is a strain, and that actually changes the band structure or band curvature, and this, which in turn increases the mobility. Oxide thinning, which you saw we needed, has been giving us good results because you can see that COX increases, but then there has been a gate tunneling current flowing from gate to the channel. So that's a problem. And this has been avoided by using high-K metal gate. So the technology trend has been that Intel, for example, brought the strained silicon, high-K metal gate, and then moved to FinFET, which we will talk about. And all this, you can see the strain has been increasing by putting more and more germanium concentration, and the dry current has been increasing with each new technology. So that was a smooth ride, but what's the problem? Problem is that if you see in this equation, the VTH and also the subthreshold slope or swing, we cannot actually change much. So if that we cannot change, then we cannot actually continue to increase the on current or decrease the off current. Why it is so? We see the problem is these depletion layers from source and drain, and this causes actually problem in the charge sharing, which is a textbook. You know this, what is happening with, because part of this gate is actually now compensated by this depletion charge. Also, if you see that when we are decreasing this length, now drain is so close to, let's say, the middle of the channel, that now the drain also acts as another gate. So that means now the MOSFET becomes resistor at a small length. You can see here that now the gate is not able to control the current here. Now it is not at all functioning like a transistor. Also, even if we make this oxide very thin so that we can have a very good gate control, but there will be some leakage paths here which are far from the gate, and that we cannot do anything. This leakage current will be there. So what to do to remove this leakage current is to actually remove all this silicon which is there, and then we will be able to remove these leakage paths. So this was done, and this was the, you can see these two devices came in the last decade around 2010-11, when FinFET was announced by Intel to bring, they brought it in the production, and FDSOI was also announced around the same time. So what is going on here is that we had here leakage paths here, we had silicon here, you remove that silicon, put here oxide and another gate, and now it becomes a double gate transistor, right? And if you flip this, and then you can see here you can have maybe a tri-gate transistor or a control from 3 sides. And here this is more like a fin, and then that's why it is called the FinFET. Right? And this has been in production now by various companies like Intel, TSMC, etc. So this was one of the first demonstration of FinFET in 1999. Note that in around 10 or 11 years ago, before it was brought in the production. So this was a 30 nanometer fin which allowed 2.7 nanometer silicon dioxide and out of the body, and the subthreshold swing was really good, 66 millivolt per decade. And then there were several demonstrations for better and better smaller transistors like 10 nanometer gate length, 5 nanometer gate length, and 3 nanometer even gate length. And if you see the FinFET from Intel, the first generation, you can see it's more like a trapezoidal here, but then later on 14 nanometer or so, they actually brought it, the process was better, and now these are taller and thinner fins. So what is happening here is that either you can design this for a fixed leakage current. So you see, if for a fixed leakage current, you can increase the performance like this way, or for same performance, you can bring down the leakage current, right? So this is what has been going on when we say that technology has been advancing in each new generation of technology. The second way which has been is that you remove this, whatever was the silicon here, instead of that, have a SiO2 dielectric, and then there is a silicon here in the backside. So the leakage paths have been removed, and this is what is called either ultra thin body SOI or FD-SOI technology. And here you can see also silicon thickness plays an important role, and you can control this off current using this TSI or silicon thickness. And this has been also brought in production by different companies like Global Foundries, Samsung, SBMicro, etc. Another MOSFET architecture which has been there is what is called gate-all-around or surround gate technology. And I'm talking about here mainly the vertical gate-all-around technology. And this has been used to reduce the footprint and increase the density. So now let's talk about the models. We have VSIM CMG and VSIM IMG model. These are especially the VSIM CMG is the first industry standard for FinFET. These have been used by various companies, different VSIM models, and FinFET model is first industry standard, which became in 2012. So the VSIM CMG was selected in 2012. It can model the FinFET on bulk, FinFET on insulator or SOI, vertical gate all around, or even the horizontal gate around, okay, or nanowire technology. There were 4 device architectures or 4 core models here. So double gate, tri-gate, FinFET, quadruple gate, and gate all around. So there were 3 core models. One is intrinsic double gate core taken from this. Another was perturbation based double gate core for high doping, and the cylindrical gate core. And then options for bulk and SOI substrate. So the model has also short channel effects. So threshold voltage roll-off is modeled well, you can see versus channel length. Quasi 2D analysis results in this characteristic length, which is used to model this. And then there are similar expressions for double gate and FinFET tri-gate. And we have analytical expression model for all these effects like Debel, threshold voltage roll-off, subthreshold swing degradation, etc. Also, the quantum mechanical effects, which are significant, especially for the advanced technology nodes. So here I'm showing you how the charge centroid is changing with the increase in inversion charge. So as the gate voltage is increased, inversion charge increases, and you can see that the charge centroid, which is far from the surface, starts coming closer to the surface. And this is also either you can see the tri-gate or FinFET, or also this gate all around or nanowire. So this affects the capacitance behavior and has been already modeled in the BSIM CMG model. Finally, when we have all these effects modeled and coded in the model, then we verify it with the measurement. So here I am showing you model validation from all the way from 30 nanometer to 10 micron FinFETs. So you can see this is IDVG on the linear scale, on the log scale, and this is GM, all accurately matching the measured data. And this is the model behavior for different temperatures. So here you can see from -50 degrees Celsius to 200 degrees Celsius, and model can capture the temperature behavior. And this is the model behavior on log scale, and again for different temperatures. Now, what has been, we have seen that the FinFETs cross section has been complex, and different demonstrations have shown that you can have this more like a rectangular, trapezoidal, more like omega gate or tri-gate, etc. So then we improved the model. So the first what we already had was the double gate FinFET model here modeled using this 4 equation, and this is the cylindrical FinFET model using this equation. So this is what we are calling the deductive model, and then from these two we combined and came up with single unified model. And this model can model actually any geometry. So here now we have only these model parameters, which are fin area, channel doping, channel width, and insulator capacitance. So if these are given for any geometry, you can see these double gate, triple gate, surround gate, or cylindrical gate, and trapezoidal, or any of these fin shapes can be modeled using this unified model. So this is the model validation which we did for SOI FinFET here, shown here. This is a long channel transistor, IDVG, transconductance, drain current versus drain voltage, and the GDS output conductance. And it also has 3D model for short channel effects model, where we have again combined these two models for double gate and cylindrical gate into a unified lambda, which is used to now model the short channel effect. So this is model validation for especially checking the scaling all the way from 1 micron to 50 nanometer here, IDVG linear scale, log scale, and here we are showing the threshold voltage roll-off versus gate length. You can see captured very well and compared with the TCAD simulation. Then we also have a new quantum mechanical effects model and a body bias model, which helps in improving the fitting of not only the IB, which we have already seen, but also the capacitance. So you can see now that you have a perfect fitting of capacitance, gate capacitance shown here. Then we have been working on other effects. So what we see when these fins are very, very narrow, then we start seeing behavior more like a quasi-saturation effect or current saturation coming due to these extension regions, that means source drain region. So now we have a nonlinear source drain resistance model, RSD, which is a function of current. So as this current increases, you can see that this source drain resistance also increases. And this also shown here, you can see this drop, especially in the GM. This can be captured using this new model. We have written a book on this BSIM CMG model, which actually talks about all the intricacies and detailed derivations of the model. Feel free to take a look at it. And this is the book which we have written for the BSIM IMG model for FDSOI plan. So now coming to the more, what is happening is beyond 10 nanometers. So there have been a lot of discussion on 3-5 FinFET, gate all around transistor, etc. So the key points we have for 5 nanometer and beyond, that we have to reduce the leakage current to get the better substrate slope. For this, we have to continue to use ultra thin channel, and one option is, for example, nano seed transistor. Another knob we have is that use higher mobility channel. So of course, silicon NMOS, PMOS are there, but even germanium, PMOS, SiGe, and even 3-5 materials like indium gallium arsenide. So then we have worked on modeling of these different transistors or materials. So here you see that we are modeling here the 3,5 FinFET Indium gallium arsenide, and using the new quantum effects model, you can see the model can capture the current behavior very well, and this is the transconductance shown on the right. Also, the quantum effects start playing more critical role, especially like in this geometry, triangular cross section. So here you can see the comparison without quantum effects and with quantum effects. So you can see quantum effects actually are reducing the drain current, and the model is capturing it very well. Then we have also worked on the germanium p-FinFET model. So here again shown the drain current, the transconductance and derivative of transconductance. And this is the drain current versus gate voltage here for high VD 0.5 volt here. Then we have, as I said, the model captures the nanowire or gate all-around transistors of these, any of these geometries. So it could be vertical, horizontal, etc. So then this is the model validation on asymmetric nanowire transistor, where the channel doping actually is changing from source to drain. So this is already, you can see, captured using the model IDVG, and not only just normal room temperature, but also for different temperatures. And note that this is experimental data for a gate all-around transistor. Then we have been working to improve also the nanoseed transistor or the gate all-around transistor model. So you can see that there have been several demonstrations in the literature. So this is IBM demonstrating nanowire, then the stacked nanoseed. All of this is now modeled using BSIM-CMG model. Also Samsung calls it multi-bridge channel MOSFET, and also this is twin silicon nanowire. So again, the model can capture all these transistor variations, and even like a stacked nanowire here showing NMOS, PMOS, and from IMEC like circular. All these, the BSIM-CMG model, the improved one, the new BSIM-CMG model can capture all these variations in the geometries. And here we have also compared or validated it with the TCAD simulations. So circular gate all around, square gate all around, and the triangular gate all around. So all these you can see, and the triangular has the strongest quantum confinement effects. That's why you start seeing that it is having highest threshold. Then beyond 3 nanometer or so, we may see some other effects like quantum capacitance, tunneling, the band gap variation, or effective mass variation. So we have been working on these effects. So this is just a refresher that how the density of states for free electrons is. So especially talking about bulk MOSFET, we have this proportional to square root E. In 2D system like ultra thin channel transistors, it will be constant, and in gate all around it is proportional to 1 by square root. And all these are shown together here, how the density of states versus energy is. So if we start seeing the different subbands, we will have these effects shown here. So we have worked on 3-5 channel transistor here, and here the quantum capacitance starts playing important role, especially in the low effective mass material. So this quantum capacitance comes in series with the centroid capacitance, which will be actually decreasing the total capacitance. So this you are seeing how as we are increasing the gate voltage, different subbands will come into picture, and you can see for it's a 2D system, so we have a flat behavior of capacitance. And if I plot this is the normalized gate capacitance versus gate voltage, you can see we start seeing these plateaus, right? And this is a classic signature of a 2D DOS effect. And this is here shown for different channel thickness. So you can see here large channel thickness like 25 nanometer is like more a conventional behavior. But as we decrease the channel thickness, we start seeing these humps, which are coming from 2D DOS effect. And same is true even if we play with the effective mass. As we are decreasing the effective mass, we start seeing these humps again in the capacitor. And then this is here again shown, which we have already modeled here in this paper, and this is shown here for different VDS. So VDS is, we very well know that VDS causes this hump, but now we have combined effect of 2D density of states and the train volume. Also, the charge centroid effect in conjunction with this quantum capacitor, this is going to further deteriorate the CV, and that's why you see this slow rise in capacitance, especially for longer or larger channel thickness. But as we decrease the thickness, you can see that these humps are coming. Another problem which might be there, especially in the low effective mass materials, but it may also be there even in silicon, is the source to drain direct tunneling. So normally we talk about top of the barrier, so over the barrier, but then if this barrier thickness is very small, then we may have here a tunneling directly from source to drain. So here we have worked on understanding this effect, and you can see here we are showing here how the subthreshold swing versus gate length is going to change, and it shows that how it is important that we not only model just this effect, but also the variation in the effective mass with the confinement. So all this is very important, and these results are showing that the classical ballistic is not good enough, and we have to make sure that we are actually capturing the effective mass variation and the band gap variation when we model these effects. So then we have been looking into further other effects. So when we talk about the scaling in FinFET and nanosheet transistor, if we talk about the cross-section scaling, so then we are talking about the quantum effects. So then what we see that we already discussed is that instead of 3D density of state, we start seeing 1D density of state, or we may go from 3D to 2D if it is a nanosheet transistor. Also, we see that effective mass increases and subband energies and band gap increase. And then another thing scaling when we talk about is the channel length scaling. So if we reduce the channel length, then we may go from drift diffusion to quasi-ballistic transport. And both of these are going to affect the device behavior, and we need a model which we already now have implemented in BCMCM. So these are the publications which I am using here to talk. So conventionally, the long channel transistor here, we talk about it. We have the drift diffusion transport. We have lots of scattering, and we have the carriers are losing the energy with each time. But when we talk about the ballistic, now the channel length is actually very close to lambda or less than lambda, so there is no scattering, right? The mean free path, the channel length is less than mean free path, and there is no energy loss. But in reality, we actually will never have ideal ballistic transport. We will have a quasi-ballistic transport. That means some drift diffusion and some ballistic transport. So we have worked on modeling of this. We start with the potential profile, use the Poisson equation, and use the charge profile to get the terminal characteristics, and then on top of that, we add the short channel effects and other higher order effects. So we start with some estimate of charge profile, and this we have divided into ballistic and drift diffusion components. So we start here some maths that we are assuming that the scattering happens at every lambda distance, and in each of these scattering events, a fixed fraction S of the incoming carriers are scattered. And then these electrons encountering even a single scattering are no longer considered ballistic. So these are some of the equations, and we call this ballisticity as number of ballistic carriers versus number of scattered carriers. And then we use this 2D Poisson equation, reduce it in the 1D Poisson form, use these boundary conditions, and to calculate the surface potential. So here, this is the center potential. You can see here, it's a long channel ballistic, no potential drop in the channel. And short channel ballistic, there will be effects coming from the source drain. So that's why you have these variations. And then we use the potential to calculate the current. With some of these approximations, we can calculate the ballistic current. And then once we have the ballistic current, we already know the drift diffusion current. add the external resistances and other higher order effects like mobility degradation, velocity saturation effect to calculate the total current. So here I'm showing you the validation. This is shown for the 10 nanometer NEGF double gate FET. This is for the 3.5 hem 10 nanometer FinFET, 10 nanometer nanowire, and indium gallium arsenide long channel transistor. So all of these experimental results can be very well captured by the model. And also in compact models, we have to satisfy benchmark tests. So again, here we are showing you that how the derivatives of current behave and it passes the double symmetry test. And here, this is the capacitance model. You can see that the quasi-ballistic actually case is also decreasing the gate capacity. Then we have further improved the model. There were some problems in the model, like current was not conserved throughout the channel, bias ballisticity was assumed bias independent, and charge stage flowing from the drain were not taken into account. So then we improved here, added the current continuity in the channel, and then you can see all these equations. We use these equations. I'm not going into details of these equations. And then we have actually finally improved the model, which is much more physical than the previous one, and also validated it with the experiment. Then we have been working on the gate-all-around transistors. So this is the model which we developed for different geometries, materials, type of transistor, includes the subband quantization, quasi-ballistic transport, and temperature. So I'm not going into the equations. I'm skipping these equations. But here is what you start seeing, the impact of quantum capacitance, and this is the 1D DOS. And you remember that 1D DOS is proportional to 1 by square root E. So you start seeing the impact of this DOS. So in each subband you have these humps, and then current capacitance goes down. Okay. And this effect is also seen in current here, especially at low temperature. So you can see this hump which is coming at low temperature, and this is here a purely balanced transfer. And then we have validated it against the measurement for different types of devices. So rectangular drift diffusion, circular here, and also circular quasi-ballistic. And model can capture the characteristics very well. Also validation with measurements for different, so germanium, indium arsenide transistor. We have also worked on circuit simulation of this, how the radius of this will change the results, especially the intrinsic delay, and even simulated the SRAM here for different radius of this nanowire. Then we have further worked on the cross-sectional scaling, so especially talking about the DOS transition from 3D to 1D. And what we see that the decreasing the radius is causing this higher subband energies and increased band gap that actually results in higher threshold voltage, and also the increased effective mass, which decreases the mobility. So we have used this decade simulation to get the characteristics. So this is a GTS simulator. It uses KP theory to calculate the charges, to get the band structure, then calculate the charges and terminal characteristics here. And this is here, I'm showing you how the impact of these subbands you can see. So for a large radius, you have a 3D density of state, so you have a conventional capacitance value. But if you decrease the radius, you start seeing these humps. All these are coming from different subbands in 1D DOS, right? So you can see as we are decreasing the radius for very large, very small radius, the threshold voltage has increased significantly. So in the given voltage range here shown, you only see the 1D, one subband only. And the same is shown here for silicon also, but silicon, you don't see that strong effect which you are seeing here in the 3.5 material, but still you see that here, for example, you have these effects. And this will also impact the circuit design. So here, if you see, I'm showing you the GM, and you see that this is the effect of subband which you are seeing. And this is more pronounced in GM by ID here, where you see this hump coming from the subband. So we have modeled these effects. I will skip equations here, but this is the end result, that how the band gap is here decreasing with the radius for silicon and 3.5. Here threshold voltage, how it is changing, and also the effective mass, how it changes. And then we used all this model to capture. So you can see this is the model, which is the black curve here, and similarly black curve here. That's the model validated over the TCAT simulator. And this is model validation with the experiments. So here you can see again shown here for low temperature, because this effect is more pronounced in low temperature due to Fermi statistics. So you can start seeing these humps also on the measured cap. Then we have worked on the nanoseed transistor models. So the BSIM CNG 111.1.0 is the first industry standard model to include these nanoseed specific compact model. And this has geomod, different geomods, etc. So now we have geomod 4 for all channel shapes, including round corners. So here we use this GTS to understand the effect, and then so here we are calculating the band structure, using it to calculate DOS, then charges and terminal current. So this is the expression for charge, and these are what I already showed, that there is no subband separation here for large nanoseed width. But as we reduce here, you can see that the subband, first subband and second subband are coming into picture. And the D parameter, which we are calling the dimensionality, we start seeing that not only we need to use in the model just the integer D, that means only 1D, 2D, 3D, but we have to use some non-integer D, which you are seeing here, right? So the increasing width of this nanoseed reduces the confinement, and it increases the dimension from 1D to 2D. This dimension also increases with increasing nanoseed thickness. And here we are seeing that we have significant effects of subband separation and threshold shift. So this is the dimension versus nanoseed width. Here you can see it is transitioning from 2 to 3, including on non-integer D. And this is the model of D, the dimension here, modeled using a semi-empirical formulation. And this includes the effect of nanoseed width and nanoseed thickness. So here you can see the nanoseed TSI is 5 nanometer. You can see how it is going from 2D to 3D. And here for 2 nanometer, you can see these ones here, right? And this is really, you have to control it using a model parameter. Then another effect which we have also modeled is the mobility in nanoseed transistors. So here you can see that how the seed thickness is changing the mobility. Here you can see also the quantum confinement effects are playing in this, especially at the low carrier density. And this we have modeled it using a detailed model formulation here. And we also model the impact of variation in effective mass here. And we have these different parameters which actually take into account how the mobility varies with different seed thickness. So here is the validation with the experimental data for different radius. This is the drain current versus gate voltage, and here the drain current versus gate voltage for different gate voltage. And you can see here compared to the old model where you were getting the higher current, now you actually start getting the lower current, but this is very well captured by the new model. So to summarize, we are working on industry standard model development at IIT Kanpur, and we collaborate with UCB and release these models. All these models are implemented in Verilog A code, tested on commercial simulators, validated with experimental and TCAT data, and we work regularly with major semiconductor and EDS companies to provide the better and updated model as required. So that's it, Marcelo, from my side. Any question?
Thank you very much, Yogesh, for your very clear, very clever presentation and very nice work. I can see here a question for Professor Sergio Bampi. Based on your cylindrical GAA simulations, quantum mechanical effects in silicon will in fact, and practically for ion over IOF ratio, limit the radius or the diameter to about 4 to 5 nanometer. Is it the case, or am I missing some points?
You read it based on your limit the radius to about 4 to 5 meters. Is it the case? So I would say that I don't want to make a prediction that that will be the limit or not. It all depends on how good quality silicon, along with the how good quality surface you can have. That will be there. There will be strong quantum mechanical effects when we are talking about the reduced radius, but we will have to. There might be always a play off or a trade off between off current and on current. If you decrease the radius, you will have better and better electrostatic. There is a second question for the nano seed FET. Is the optimum thickness for NFET or for PFET any different? I don't have answer. The reason being that optimum thickness will depend on not only electrostatics but also mobility. So it really needs a lot of measurement and good process control. And we have not seen much published data on this optimization.
I have one question, Yogesh, please. We have seen in the past few years that the industry is moving in direction to nanosheet. However, nanosheet seems to be intrinsically limited in terms of scattering, because you can, depending on the thickness you have in the nanosheet, you can have a lot of scatter centers in the surfaces because of the processing. Could you please comment on your opinion if the nanosheet is the, let's say, the limit for the MOSFET in terms of architecture, or the pillar, as you demonstrate, the surrounding transistor would be the one, in your opinion, please?
So, see, why? So, what's the problem? The surround gate, if you see, the problem is it's a vertical, and the control is like the doping itself is not easy to control, and also making on top of each other. Again, this is already used in some of the technology like DRAM, what I know. But talking about the logic, when we say is the nanoseed will or is going to come in the production, the region. So reason being the FinFET is already reaching limit, and if you reduce the thickness further, there are problems of not only the control but also like bending. So nanoseed has option that you can have horizontal seeds, and also another one problem can be, for example, scattering. I would say that industry will have a good control on the surface. So when they bring this in the production. The one problem can be that there will be a limited current from each nanoseed. So the solution is going to be same as in FinFET. In FinFET, there were multiple fins. In nanoseed, there will be multiple seeds to improve the current or increase the current.
Great. Oh, I see in the chat, and there are no additional questions. So, oh, one appeared here. Process integration in the vertical pillar is too difficult, right? So I suppose that the process technology for nanosheets will be the key to minimize surface effects and also the optimum thickness of nanosheets. Is that so?
I think so. I also think so that what you are saying is correct, that the process control will be much better and easier compared to the vertical pillar technology.
Okay. So, with that, I would like to thank you again, Yogesh, for your disposal to be with us this morning. Thank you very much for your very kind and very nice presentation. And it has been a pleasure to meet you and see you in person during this day. Thank you so much.
Thank you very much. Thank you. Bye.
Thank you, Yogesh. So after this very nice talk, let me just share my screen once again. Just a minute, I'm searching it here. And yes, it is over here. So we are moving then to, I hope you are seeing my screen now. Yes, you are. So then we are slightly delayed with respect to the program. So next we will have a 50 minutes interval for taking a coffee, give some walk, and then we will be back here at 10:15, no later than 10:15, to start Professor Mario Lanza's presentation from Saudi Arabia, talking about hexagonal boron nitride-based electronic devices and circuits, status and prospects. So if you are arriving now, you are at the 2021 IEEE EDS Brazil Virtual Mini-colloquium. And I am Marcelo Pavanello. I welcome you. And after the interval, we will be back. Thank you for the moment.
Something to say. Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB-IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
SBMicro, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. SBMicro promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country. producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components, since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. ABCME members have also been significantly investing in the establishment of research and development centers. An example is the Eldorado Research Institute, located in Campinas, state of Sao Paulo. Eldorado has the country's first semiconductor prototype laboratory. Another example is the ITT Chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces the dependence on global centers of semiconductor components. There are many opportunities. Only in the Internet of Things field, the economic impact expected until 2025 is about 10% of gross national product. Semiconductors are the brain of the electronics industry and the heart of the technologies that move the world. Brazil is already part of this important universe. ABCME believes in knowledge, innovation, and people as the keys to identify new technologies. Above all, ABCME believes in Brazil.
Somewhere, maybe right at this very moment, the next technology breakthrough is about to inspire the next generation of minds, thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good, because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. Their top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our eSoft electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3.
Good morning, good afternoon, good evening once again. Welcome back. We are at the 2021 IEEE EDS Brazil Virtual Mini-colloquium. I am Marcelo Antonio Pavanello, and I'm the tutorials chair of these SBMicro 2021 Tutorials Day. So for those who are joining us now, please be welcome. We are now moving to the next presentation, which is hexagon boron, entitled Hexagon Boron Nitride Based Electronic Circuits, which will be given by Mario Lanza. So let me just say a few words about Mario's achievements. Just a second, please. Okay, Mario Lanza is an associate professor of material science and engineering in the King Abdullah University of Science and Technology, Coast, in Saudi Arabia since October 2020. Dr. Lanza got his PhD in electronic engineering with honors in 2010 at Universitat Autònoma de Barcelona. During the PhD, he was a visiting scholar at the University of Manchester in the UK and Infineon Technologies in Germany. In 2010 to 2011, he was an SFC postdoc at Peking University, and in 2012 and 2013, he was Marie Curie postdoc at Stanford University. In October 2013, he joined Soochow University as an associate professor, and in March 2007, he was promoted to full professor. Professor Lanza has published over 120 research papers, included in science, nature electronics, nature chemistry, and IEDM. Edited a book for wireless VTH and registered 4 patents, one of them granted with 5.6 million Chinese yens. Professor Lanza has received the 2017 Young Investigator Award from Microelectronic Engineering from Elsevier, and the 2015 Young 100 Talent Award, among others. And in 2019, he was appointed as Distinguished Lecturer of the Electron Devices Society. Professor Lanza is Associate Editor of Scientific Reports in Nature and Microelectronic Engineering from Elsevier, and serves in the board of many others, like Advanced Electronic Materials from YLA VCH, Nanotechnology and Nanofutures from IOP. He's also an active member of the technical committee of several world-class international conferences, including IEEE IEDM, IEEE IRPS, IEEE IPFA, and APS. He leads a research group formed by 10 to 15 PhD students and postdocs, and they investigate how to improve electronic devices using 2D materials, with special emphasis on two-dimensional layered dielectrics and main resistors for non-volatile digital information storage and artificial intelligent computing systems. Okay, that being said, I will move back and pass the ball directly to Mario, inviting him to give his. Mario, the ball is yours.
Thank you so much for the nice introduction, Marcelo, and for inviting me to give this talk. It's always a pleasure to give a talk in Mini-colloquium organized by EDS. So, yeah, as you have already said, I work in the field of 2D materials-based electronic devices. We are starting to do circuits also. So, this is not an easy task because, as you know, integrated circuits are made of many materials, right? We call them silicon circuits because it's the most important semiconductor, but it has many others. It has metals, different kinds of metals. It has transition metal oxides. It has dielectrics, high-K dielectrics. So, and every material is different, right? We also use doping techniques. We also use the quality of the materials can be very different depending on the method that we use to grow them. So there are many factors that influence how feasible is to introduce a new material in one electronic device and in one chip, let's say, which is at the end what we are carrying. So there has been some interest on two-dimensional materials since 2004, since the people in Manchester isolated graphene for the first time. And there has been a lot of research. And as you know, every material and every technology first has a phase of a lot of optimistic feelings. Then people start to get pessimistic because things don't work so well. So the curve goes down. And then you get the stable at one level that is the level in which you will reach impact into the business, into the market. So I wanted to give a realistic view on where we are in terms of electronic devices, and especially oriented on hexagonal boron nitride, which is the 2D material with the widest band gap. So it can be used as a dielectric. Something that graphene and transition metal dechalcogenides like molybdenum disulfide cannot do. And also, I would like to give an impression on how to use this material for electronic device that is very attractive now, called memristor, which can be used for different applications, as I will show you. So this is the outline that I will follow. I will start with introducing the fabrication of 2D materials-based circuits. And then I will talk about the materials and methods that we use to synthesize the materials that we will use, and especially the methods to synthesize them, because you will see it make a big difference. Then I will show some morphological and local electrical properties of these materials. And then I will go for the membristors. First, the bipolar and threshold resistive switching, which is the fundamental functioning at the device level. And then we will go to crossbar arrays of membristors for artificial neural networks. So here I put some papers that indicate how relevant this is right now for publishers and also for the industry, for both. We have reached a level in which foundries have started to get used, have started to get interested, with two-dimensional materials. At the beginning, nobody wanted to hear about 2D materials in microelectronics industry, but now some institutes, IMEC, and companies like TSMC, Samsung, they are starting to publish very nice things. And here you have some examples from Nature, and also one entire special issue was published by Nature Materials in 2019. I'm writing a perspective paper for Nature Electronics in this topic that will come published in a couple of months. So it is definitely a very hot field right now. And regarding the synthesis methods, you can see something that is, you can see that there are very different methods. The method that was used, the very first method that was employed to isolate two-dimensional materials is this one, mechanical exfoliation. Basically, you take a tape, you put in the middle a piece of crystal, and then you exfoliate it. And by this force, you can produce small flakes of this two-dimensional material. If you repeat the peeling many times, these flakes can be very thin and can reach monolayers. However, what you get with this is a microscopic flake. And with this, you can make maybe 1, 2, 3, 5 devices, maybe 10, maybe 100 if you are very skilled, but cannot make more. And this is not scalable to the wafer level. So this is just for prototypes in the lab. It's good to understand the fundamental limitations of the material. It is not good to fabricate devices. Also, within this little flake, you can fabricate very few devices, so it's impossible to understand how variability affects and how yield affects the devices, so which is in fact the most important thing. So there are other methods that have been developed. By the way, the quality of the materials produced by mechanical exfoliation is normally really, really good in terms of crystallographic orientation of the atoms. You have them arranged in a distribution that matches the theoretical models. So if it's graphene, for example, you will have these carbon hexagons. And as I mentioned, it's good to understand fundamental limitations. However, because this method is not compatible with the industry, we need to develop other methods. So here, there is a summary of all the other methods, most of them. One is by molecular assembly. This is also a bottom-up method. However, you get many, at the junctions of these molecules, you get several, let's say, imperfect bonding. And it's also not especially cheap. You can see it, the price is relatively high compared with others. Then we also have liquid phase exfoliation, which basically consists on doing also mechanical exfoliation, but do it in a larger scale. So you get some powder material and you exfoliate it, and what you get is a liquid containing a lot of flakes of this 2D material. And later you can spin coat it on a wafer, and you can have a film of many flakes together. I will show you later. However, still we'll have some imperfections in the junctions. And here there is another one that I want, is the one that I will focus, which is chemical vapor deposition. And this method is very interesting because it can allow wafer scale growth of 2D materials. However, there are some locations where you get this perfect crystal structure, but there are other locations where you get something that is highly defective, okay? So this needs to be considered because there are many papers that show you a very small image and they tell you, wow, we got fantastic quality. But in fact, when you get 70, 80 pictures, TM pictures, which is what we analyze normally, that is an exception. Normally you have a lot of defects. So with this method, there is a problem with the chemical vapor deposition, which is that you require high temperatures of around 900 degrees. So basically, you cannot grow 2D material on wafers that have patterned silicon devices. It's not possible because you will destroy all the devices. This high temperature will destroy everything. So what you need to do is to grow it in an independent substrate, which is normally can be metallic substrate, normally for graphene and boron nitride. It can be silicon oxide for transition metal, decalcogenides like molybdenum disulfide. And then you transfer it. Basically, you put a polymer on top, you etch the copper, and then the polymer with the 2D material stays floating on one solution, and then you fish this with the target substrate that you want to use with your wafer containing the silicon chip or containing whatever you want. And then on that place, you can now pattern the 2D material as you wish. So this is something very interesting, but it needs to be understood that there are two risks in this process. One is that you get rest of polymer that get your material contaminated, or rest of copper also. And also that you have cracks during the transfer, which basically can short whatever, because you are going to use this as a dielectric. So if you have a little crack or a little pinhole, you're going to make a short circuit across the dielectric. Whatever you have there is going to be broken. So for monolayer, this is extremely harmful. You have a very high probability to get many devices shorted. But for multi-layer, which is what I use, above 6 nanometers, I would say 3 nanometers, you get something that the yield starts to be really, really acceptable. So this is something that I have observed. My group has done this quite often. So here there is something that you have to understand, which is the boron nitride. There has been amazing publications of wonderful behaviors with 2D materials. Recently, we have even seen unconventional superconductivity, and that the boron nitride used as a substrate can increase the mobility of the graphene because there is less scattering. There has wonderful publications, wonderful results, and world record of mobilities and whatever with 2D materials have been reported with exfoliated materials. Here I show you one example in which these authors reproduce what it was done in one Nature Nanotechnology paper of 2010, where they observed record mobility in graphene field effect transistors when using boron nitride as substrate. Well, if you repeat this with materials, this was repeated 8 years later with CVD grown materials, the same structure. And the mobility was remarkably lower. This is an indication on how difficult it is to reproduce the behaviors observed in exfoliated materials using CVD materials. This is extremely complex. I give a lot of credit to these authors for this paper, even if they observe much less mobility. When you try to publish this, you cannot reach such a high impact factor journal if you don't have record mobility. In my opinion, this has much more value because this use industry compatible methods. So this is something I always, when I discuss with editors, I always try to emphasize that we need many more works on 2D materials using scalable methods. So if we take a look to the to what it has been reported. Let me see. One moment. Move a couple of slides here that fit better. So you can see that, again, what I mentioned, the mechanical exfoliated material, you can see something like this. It's a very small flake. This is what I was telling you before. It has different thickness fluctuations. And as I mentioned, this you cannot do this with a wafer at a wafer scale. What you can do is to use a mechanical transfer, a mechanical peeling with a material that has been produced by CVD method at the wafer scale or in a larger areas, and then transfer it. This is fine, okay? But this mechanical exfoliation is for the transfer, not for the growth. So this is something that that needs to be also understood. So if we think on the other methods, that what I mentioned about the liquid phase exfoliation, basically you have this solution containing all these flakes and you can spin coat it on different parts on different substrates. You can also get a film of two-dimensional material flakes, but it's a film of flakes. It's not one atomically thin with smooth substrate. So basically, this SEM picture is what you see about the material. It is really, really rough. Okay. This is the cross-sectional TM picture of one of these structures. You can see a lot of flakes that merge to each other. So basically, you are going to have a lot of dangling bonds. And if you are making an insulator like boron nitride, this can be a big problem. So, yeah, so this has also an even bigger problem. Apart from the variability, if the device is very homogeneous, very inhomogeneous, two devices that you may fabricate may have different properties, of course. But the even bigger problem is that this kind of liquid phase exfoliated and spin coated films, they are unstable for lithography. So basically, you cannot make very small devices because normally this is used more for inkjet printing and the lateral resolution is very small, which doesn't make it not useful for electronic devices and circuits, but not for high integration electronic devices and circuits. This needs to be understood. However, there are still many applications. So this can be a useful technique for other applications, not for high density applications. Here I show you one example of one work that used liquid phase exfoliation that is a little bit better than the others. The authors managed to coat a 100 millimeter wafer with a quite homogeneous film of molybdenum disulfide. They fabricate several devices and they observe a relatively small and nice mobility. This is something quite meritorious. This is why it was published in Nature in 2018. However, there is an important problem here, which is this scale is 100 micrometer. These devices are huge, okay? So this was a good proof of concept in 2019, but this is not competitive in terms of logic integration. So recently, in 2019, actually, it was the first time I started to see papers coming from companies, strong papers on 2D materials-based devices from companies. The first one comes from TSMC in the top row, and the bottom one from IMEC. And both of them do field effect transistors using two-dimensional materials. This one uses molybdenum disulfide. This uses different transition metal dechalcogenides. And the interesting thing is that both of them were smaller than 100 nanometer in channel length. So this starts to be good. This starts to be one layer with it's atomically thin. It's less than 2 nanometer. It has a very small channel length. So this is something starting to be good. The paper in IMEC is even better because they analyze device-to-device variability, which is, by the way, large. So this is something that even if we're still not there, but we are already in a good, starting in a good direction after many years of 2D materials research. So in my case, I'm not working on field effect transistors. so much because one transistor is a device that is difficult to fabricate. So what I am doing is to fabricate membristors. Membristors is basically one capacitor with a reversible dielectric breakdown. It's a metal, insulator, and metal. And when we apply an electrical field, we can start to change the atomic structure of this dielectric. You can see that I can change slowly this composition, and then I can form a conductive nanofilament between the two electrodes across which current can pass. Actually, if I keep applying, this filament can span laterally. And then if I reverse the electrical field, what I see is that I can destroy, or at least partially destroy, this filament. And then what I get is, again, an initial high resistive state. And this can be done, if I switch the polarity again, can be done, the filament can be formed again. So you can switch cyclically between this high resistive state and low resistive state. The principle is similar to the dielectric breakdown we know in nature. Like, for example, a lightning between cloud and the ground. Both are separated by an insulator, which is the oxygen. But if there is enough electrical field, we can reach the dielectric breakdown. So what is the difference? The difference is that the dielectric breakdown in the nature, in the case of the lightning, is a volatile phenomenon because this filament doesn't stay here. After a short time, it disappears. With the membristors, depending on the materials that we use, we can induce volatile resistive switching or non-volatile resistive switching. So both of them can be used for different things. Okay, so I will explain you. So our approach is normally people who have studied membristors until now, and most of the papers you can find, they use at least the best performances, okay, they have been achieved with transition metal oxides, like hafnium oxide, aluminum oxide, especially tantalum oxide. These are very good resistive switching dielectrics. There are several other studies with other materials, including perovskites, MXenes, and many other materials. However, I can tell you that the best performances are always achieved in transition metal decalcogenates. So you will see several high impact factor papers with these materials, but because they are new materials and editors like something novel, but in fact the performance is really, really far from transition metal oxides. In my group, what we do is we had the hypothesis that two-dimensional materials could work for membristors. And not any two-dimensional materials. We think multi-layer hexagonal boron nitride is the key. And the reasons are like this. The first one is that the boron nitride has a wide band gap, so it will be insulating in the insulating state, which means that the off current will be low. This is important because if you use semiconductor, you're going to have much higher off current. And the second thing is that if the multi-layer boron nitride is grown by chemical vapor deposition, you will have some native defects, as I show you in one of my previous slides. Then what you are having here is one nearly amorphous material that is embedded inside very stable two-dimensional material. So basically, when you have membristors made of traditional materials, it's difficult to control this filament because it can span laterally, it can have different ramifications, it can look like a tree. And this is difficult to control. However, if we have the filament in these defects, it cannot expand laterally because this is much more stable, at least for the voltages that we apply. And the fact that there are less atoms involved will make possible to control this phenomenon better. Moreover, most of the electronic devices die due to heat, right? To thermal heat. And this material is a very good thermal conductor. So we have all the ingredients for having a very good behavior and good reliability. So if you want to know more about membristors, which are the most recommendable fabrication methods, the most recommendable figures of merit, and the most recommendable methods to obtain these figures of merit, I recommend you to read this paper that I wrote a couple of years ago with a group of experts. We try to put some standards on this fabrication and characterization, and even simulation. There is a section on simulation. So regarding the materials and methods, as I mentioned, I use chemical vapor deposition in a system that looks like this. We use different precursors. It can be boracine or ammonia borane. We have a reactor, a tube furnace, where we put the sample. The sample is just copper foil. Although you can also put a silicon wafer coated with copper, but you need to make sure that the copper is not stable. And then we heat it at high temperatures and we introduce the precursor. When the precursor starts, it forms some islands. And then these islands at high temperature can expand laterally until they merge. And we'll have here a grain boundary because these HBM grains will have different orientations. So we are now in chaos buying our CVD system to start to do this experiment. In the past, we didn't fabricate the material by ourselves, but we collaborate with different people in United States, in China, and also we buy samples commercially available to try to observe the behavior. We did hundreds of comparisons between samples and devices. We also got some exfoliated material from NIMS in Japan because they have very good quality to understand the physical limitations. So the things that we do, the first thing that we do when we get the material is to analyze the quality through Raman spectroscopy and through XPS, and also, as I showed you at the beginning, with cross-sectional TEM, which is also something I will show you later. But also, more important, we make characterization and electrical characterization at all scales, starting from conductive AFM in vacuum with the tip in contact with the boron nitride, which this gives you a effective contact area below 10 nanometers square. I will say in vacuum, even 1 nanometer square. We also use some nanodot electrodes, but also we fabricate real devices using shadow mask for the big ones, so that we won't have contaminants from the photoresist. And also we use photolithography and electron beam lithography. So you see, we cover all sizes. And one important thing that we can do with AFM that people cannot do, most of the people cannot do, is to apply pulse voltage stresses, because what we do is we connect the semiconductor parameter analyzer to the tip of the conductive FM. So this is a quite unique experiment that we got experience on this, and we have already demonstrated. This is very useful when you want to use the membristor as electronic synapse, because these devices work with pulses always. So this is again a slide to show how we do the transfer and the device fabrication. We need to do the transfer as I showed you before, but first we need to put the bottom electrode and then the top electrode. And with this we can get the metal insulator metal structure. In our case, the insulator is the boron nitride. So you see here one picture with two isolated devices, what we call two cross-point devices. But I also will show you later the fabrication of a crossbar circuit with hundreds of devices. So if we analyze the electrical properties of this material, you can see that the exfoliated device is very homogeneous. We can see that there is almost no difference. Nearly all the points show the same behavior. If we make, here in this plot, we present more than 250 RAM voltage stresses performed at different locations, and we see that the deviation is relatively low. If we take the same thickness material and we repeat this experiment, but for a material grown with CVD, from boron nitride grown by CVD method, you will see it's much more inhomogeneous. As I mentioned at the beginning, we have some defective locations. So this is what they produce when every position has a different electrical conductance. Also, we have some multi-layer islands and some wrinkles and both of them are more insulating. As you can see here, they show less current. This all may endanger their device-to-device variability if we use this material to fabricate devices. So we have analyzed these inhomogeneities, where are they produced? And we analyze very large area of one sample, that is polycrystalline boron nitride on polycrystalline copper. And what you can see is that we observe the copper grain boundaries very well defined. Sorry. We can also observe the boron nitride grain boundaries. And actually both locations show higher currents because we have a higher concentration of boron nitride defects at those locations. But moreover, actually you can see the grain boundaries in the boron nitride, they also show higher current. But moreover, we also have that inside these grains, there are also point defects across which the current is higher, is much higher. So because this AFM tip, we can be located wherever we want, we zoom in into this map, and then we put the tip outside this highly conductive spot and inside the highly conductive spot, and we apply a constant voltage stress. What we see is very interesting. We observe that outside there is no current. This is a very strong material with a perfect layer structure in that location, and basically there is no leakage current. It's a very good insulator. However, within this defective area, if we apply the same stress, we see a current that is much, much higher. This is in the nanoamp range. And also it fluctuates between two different states. This is what we call random telegraph noise signal. And basically what it's showing is that there is being trapping and detrapping of electrons inside the structure of the material, which means that there are dangling bonds. Okay, so the material contains more defects. And this is something very interesting because it is a clear indication that these local defects behave differently. And the RTN is, it precedes the resistive switching behavior, which is what we need for the membristors. So when we found this result, we thought, oh, these devices may show resistive switching. But here we are just measuring with the tip of the conductive FM. So in the next step, we go to fabricate devices, real devices, metal insulator metal. You see the exfoliated devices, they show very low current, very, very low. And the current starts to increase after 6 volts for a thickness of 6 nanometers. However, when I trigger the dielectric breakdown, this is a dramatic breakdown that destroys completely. There is a little explosion where the metal basically is removed and there is a hole inside this boron nitride. When we fabricate devices by CVD, it is very interesting because now we can fabricate several devices all in parallel with photolithography. This is wonderful. We can get information about the variability. You can see that here we measure one device, and every device needs to be fabricated one by one. Here we can measure many devices. We observe in this case, by the way, after the fabrication, we can confirm the presence of boron nitride by seeing, for example, continuous wrinkles that expand inside and outside of the effective area of the device, which is the cross-section point, this point. So now we see much higher currents than here, than for the exfoliated device, and the currents show wide deviation, okay? So in fact, this is a big problem. This deviation is a big problem. So let's go to see what happened if we try to measure these devices. So initially, the first devices that we fabricated, they show very high leakage current, as I told you right now, and very low breakdown voltage. Like here, this device, for example, is breaking at less than 0.5 volts. So basically, because our initial goal when we started to work with this was to use this as a gate dielectric. And when we saw this first plot, that it breaks here, we thought, oh, this is a disaster. we got something super bad. So We were quite depressed. However, the student who was doing this experiment applied negative voltage after that, and then we observed that the initial conductance can be recovered. And if we repeat the test with both polarities, we see non-volatile bipolar resistive switching. This is the clear signature. Actually, we can plot the resistance of every state, and we can observe a good separation between both states after some initial transient. We see a very good separation. So with this, it's a first indication that you can fabricate an electronic memory that has two states, the high resistive state and the low resistive state, to emulate the ones and zeros of the binary code. So we published this in Advanced Functional Materials because it was the first demonstration on this type of material. So as I mentioned before, this cannot be done with exfoliated material. This is what you observe if you try to do this with exfoliated. After the dielectric breakdown, you see this crater that I mentioned before. This was seen by a group in Japan. It has been also seen by my students in my lab. So the next step is to understand how this resistive switching mechanism happened. And to do this, we performed several experiments. The first one is to fabricate devices with different metallic electrodes. And what we observe is that the speed for the breakdown is different depending on the metal, which means that most probably there are metallic particles entering into the boron nitride. We have also done cross-sectional TEM images, and we can observe that the material starts to contain some dark areas that were not there in the fresh sample. Here in this picture, you may think that they are, in this case, this material has titanium and gold. So you may think this is gold because it looks darker. However, I talked with experts on TEM and they told me it is not like this. This dark color could come also from titanium penetration due to different orientations. So we did another experiment. We collected several cross-sectional TEM images, and we did EDX and also EELS test. These are both tests to tell you the chemical composition of the material at the nanoscale. And what we observed is that for the fresh samples, we see the metal insulator, metal boron nitride metal structure very clearly. The boron and nitrogen signals are nearly perfect. They are symmetric, they overlap, and there is no metal inside the boron nitride film. So it is a quite good, pristine structure. For the stress devices, we observe two different atomic motion. The first one is movement of boron towards one of the electrodes. And the second one is penetration of metal inside the boron nitride. So this is something very interesting because normally for metal oxide membristors, you have either movement of oxygen from inside or penetration of metal from outside. But in this boron nitride, it's different. If you take out the boron, the nitrogen normally doesn't move because until the melting point is quite stable, but the boron vacancies, they can be activated. However, especially at these defective locations, okay? So, however, if you take out boron, you cannot make a conductive nanofilament. There is nothing conductive there. So you need metal penetration. So the mechanism is a kind of, it's a quite novel mechanism. It's a combination of both mechanisms, in fact. So in the next step, what we did is try to fabricate smaller devices and demonstrate the presence of resistive switching in smaller devices. And here you see a device that was fabricated using electron beam lithography. So you see here the bottom electrode, and then we transfer the boron nitride, the top electrode, and we also observe non-volatile resistive switching, non-volatile bipolar resistive switching. In this case, the device is 150 nanometer by 200 nanometer, and it has titanium boron nitride gold structure. So this was a very nice proof of concept. We can go very small. And why we can go so small? Okay, there is a key point here. We always need a defective region to produce the resistive switching phenomenon. However, we observe in the conductive AFM, especially in the TEM, that these defective regions are produced very often in this, the distance, the inter-defect distance can be 10 nanometer or even less. So we have defects everywhere, so we will always catch some defects across which we can induce the resistive switch. Actually, we find something interesting that is not observed in other metal oxide membristors, which is we can also produce easily and quite reproducible volatile unipolar threshold type resistive switching. We just basically reduce the current limitation and we can produce the set. But when we ramp the voltage down, this filament self-destroys because the current that we induce was not very high. So these atomic rearrangements are not very severe. They can self-recover when we switch off the voltage. This will be the case of the lining when we recover after some time. And this is something very interesting because, as I mentioned, it cannot be done with transition metal oxide. So now, this has the indication that because we have also threshold type resistive switching, we could use this device either as neuron, electronic neuron in one neural network, if we use it in threshold mode, and we could use it also as synapse if we use it in bipolar mode. However, for fabricating neurons and synapses, what we need to do is to observe this with the pulse voltage stress. So we basically repeat the experiments and we confirm that both regimes are observed with the pulses. For example, we can observe that when we increase the conductivity using short pulses, the current that we reach is around 50 microamps. And when we stop the test, we can see that the current recovers completely. Actually, it's not constant, it recovers. And if we increase the distance between pulses, we can see this recovery very clearly. However, if we actually, this is much better than what has been observed before in other silicon oxide and transition metal oxides. And probably this reproducible relaxation is one of the main reasons why this paper was accepted in Nature Electronics. And we also see the non-volatile regime. If we keep applying pulses, we can reach higher currents around 600 microamps. And then now if we stop the test, this is not volatile. Here the currents don't disrupt. When we apply the read voltage 0.1 volts after the test, we can still see high current. So this is something quite remarkable. In this case, we can reset the device, but we need to apply opposite polarity. So here, if we apply pulses with opposite polarity, we can reduce the currents across this device again. And actually, we also observe a very smooth potentiation. Normally reaching, after applying pulses, reaching such a smooth potentiation is something really, really difficult. You can check many papers. You will not find something like this with other transition metal oxides, I can promise you. And we can control the speed of the potentiation with the voltage applied, but also with the time of the pulses. So based on this, we thought, okay, with this we can fabricate, maybe we can use this for hardware implementation of artificial neural networks, which is what we are working currently. So let me first, before I go to this last work on circuits, give you an introduction about artificial neural networks. I'm not an expert in the field in neural networks. This is more something related to mathematics. It's for mathematicians. Actually, artificial neural networks are mathematical models. And there is a high interest by the industry and by governments to use these artificial neural networks because they are advanced computing systems. They don't use the von Neumann structure with a memory and with a CPU. And this advanced computation may bring benefits in terms of economy, wellness, national security, many fields actually. So basically, these models, this mathematical model consists on one data set that is placed to the inputs of this neural network. And there are some mathematical operations. And at the end, one output is activated. It can be used for recognizing data sets, for doing computation. So basically, different types of data like images, like speech can be processed using neural networks. So the main building block of artificial neural networks is called perceptron, and it has a structure something like this. Each perceptron has multiple inputs, and the value of each input is weight is multiplied by one number, and they are all summed. Then the value after this sum is compared with another value. It is an operation that we call thresholding, and then if this operation in some cases, if this thresholding level, if the value of the sum is higher than the thresholding, you can activate this output. Okay, there's something has some similitudes with what happened in a real biological synapse between two neurons. So if you try to implement this building block with electronic devices, for example, CMOS transistors, you will find that you need a lot of devices to do one single electronic synapse. One single synapse is only one of these, okay? And this can be expensive and space consuming. At the same time, we have requirements for these synapses. We need to, for the synapses, we need to find multiple stable states with a linear transition between them, and we should be able to potentiate and depress the device, which means basically increase the conductance and decrease the conductance. For the neurons, we only need two states, and one of them need to be volatile. So it need to be unstable and recover. And also we need high nonlinearity transition between these two states. And of course, we need a low power consumption, high yield, low variability, high endurance, and high integration density, which is common for both of them. So the key point is that this building block that we are seeing here with several transistors can be emulated with only one memristor. As I showed you before, we can have memristors that show threshold type resistive switching and volatile resistive switching. So with this, we can emulate the functioning of the neuron and the synapse. You can see it here better. Actually, all this building block can be implemented using, it is basically a matrix vector multiplication, and it can be implemented with a crossbar array of memristors that exhibit non-volatile bipolar resistive switching, and this neuron can be implemented with one memristor that exhibits threshold type resistive switching. So it's as simple as this. I can show you one example in this publication where the authors fabricate this crossbar array. You can see here 8 perceptrons. One perceptron is one column because it has many inputs and one output. And then here we can see the neuron, which is the comparison with the thresholding level. You see, this is the building block, and then the neuron, which is one perceptron. Here we have 8 perceptrons. And you see the authors use hafnium oxide for the synapses, and for the neuron they use silicon oxide. But there is an important thing, which is this silver electrode is what enables this material to have the threshold resistive switching. So what we are doing in my lab is to try to optimize the memristors to exhibit both behaviors. So in the previous part of the presentation, I have shown you, if you remember this slide, here I show you that this boron nitride, when I put titanium here, it can show non-volatile bipolar resistive switching. And if I lower the current limitation, it can show threshold type resistive switching. Okay, with this combination of titanium boron nitride and gold, you can reach both regimes, but none of them is super good. You can see both of them, but none of them is extremely good. So what we did is to optimize the behavior. So first we use gold electrodes to fabricate devices that show volatile and show non-volatile bipolar resistive switching, as you can see here. And we also fabricate these devices at the crossbar structure. So you can see these wrinkles appearing here, and confirming the presence of the resistive switching of the 2D material, sorry. And we observe resistive switching for two different current levels. These levels are stable. You can see we measure for 10,000 seconds in each level, and they are reasonably stable. As I mentioned, we fabricate so many devices. We can see, I mean, this crossbar array that you see here, that you see one portion, because the whole picture, then you don't see anything. It was 100 by 100 devices. And there is one important point that worried us at the beginning, which is the presence of these wrinkles and maybe rest of polymers may induce some problem on the variability, because we saw when we measure devices that we have in the first ramp, in the dielectric breakdown, what we call the forming process, we have a big variability here. It is bigger than what we see in transition metal oxides like hafnium oxide or silicon oxide. So the variability of the forming is reasonably big. We have measured if there is any relationship between the density of wrinkles and the breakdown voltage. And the answer is no. There is no relationship. Okay, so there is intrinsic variability in the breakdown, but not due to the wrinkles. And actually, if you try to do the switching, we don't see such a big variability of the set voltage, reset voltage, high resistive state current, low resistive state current. We don't see such a high variability. The big variability is at the beginning when we induce the forming, but not later. Later, the variability is reasonably low. Actually, here you can see a plot comparing 48 devices collected. This one is the first 16 is in the same crossbar array, and the others are randomly selected in a wafer. We can see a variability that it is comparable to the best we have found in transition metal oxides. This is the comparison for cycle to cycle variability, because we only have one device, okay? And the best we can get is 1.53% and 2.2%. This percent is the coefficient of variance, okay? You can check the publication to see how we calculate this. Basically giving you the distribution. And it is among the very best. This one has better size, but the devices are also bigger. This is important, okay? Because achieving low variability in a big device, I mean, you always need to fabricate small device. So if you don't fabricate small device, whatever you see in the big device is not going to be representative. And then we also compare multiple devices, 48 for this current limitation, 16 for this current limitation, and we see variabilities that are really quite nice. Of course, if this is done in an industry, I think they will get even lower. So, but this is a very good indication for a professor working in a university. I think this is remarkable compared to the literature existing. Then we did something additional, which is very interesting, is we tried to measure more conductive states, because to make one synapse, you need several multiple states and a linear potentiation, as I mentioned before. And we have achieved to potentiate the device from the nanoamp range to the milliamp range. You can see in the paper we show 25 stable states. Here we see some of them, because when you arrive to the milliamp regime, they are much closer, so you will not see them here. But this plot demonstrates that these states are stable for different regimes. This is something that has never been seen with transition metal oxides, in the sense that in transition metal oxides, the on-off ratio is much lower for this for this potentiation and depression studies. So basically, I showed this to one of my friends, Professor Dmitry Strukov, and he thought this was remarkable. And he thought this could really have application for simulation, for the hardware implementation of artificial neural networks. So he made a simulation at the system level in which he predicts what will be the accuracy and the cell-to-cell, the membrane-to-membrane disturbance, if we use this type of devices or devices with this performance to build a real neural network. And he observed that the accuracy that we could achieve, I mean, to build a neural network and to use it to classify images from the NIST database. And what he observed is that the accuracy is pretty high, achieved 98%, and the cell-to-cell disturbance is very small because the currents that we achieve are very low for some states. So this is something that strongly indicates these boron-nitride membristors could be useful for hardware implementation of neural networks. However, this is simulation. Okay, we have not fabricated a neural network. We are working on it. Fabricating a neural network it's very complex. You're going to see papers trying to exaggerate. We have built a neural network. Nobody has built a neural network with membristors. Let's say a powerful neural network. You need a lot of peripheral hardware. Okay, there are a lot of simulations there, but if we talk about hardware, you also need CMOS components to fabricate multiplexers, to fabricate other devices that need to be connected to the crossbar array. Okay, so this is not so easy. We are now fabricating on this, and hopefully we can present new results on hardware implementation soon. Finally, let me just show you one remarkable study on the threshold behavior. When we use silver electrodes, we have managed to observe threshold type resistive switching at ultra low current. This is something that I've never seen in any other study, to show several cycles of threshold type resistive switching. The most conductive state is 1 picoamp, so this is super small. Actually, it is so small that we could then measure directly the energy per state transition, and we had to estimate it. So the estimation that we did is like this. We know the state of, we know the current in the low resistive state, which is 1 picoamp. Actually, it can be down to 110 femtoamp. We know this current level. We know the voltage. So if we want to calculate the energy, we also need the switching time. However, the switching time cannot be measured with one standard semiconductor parameter analyzer because the noise level is around nanoamps. So if you apply some pulse voltage stresses, we have confirmed that this device can switch for several cycles. You can see here 2000 cycles, but we cannot measure the switching time from 10 femtoamp to 1 picoamp, for example. So what we have done is to measure the set time for the minimum level current that allows us to measure, which is in the range of nanoamps. And we observe this time is around 200 nanoseconds. So if the switching time from the noise level to nanoseconds is 200 to nanoamps, sorry. If this switching time is 200 nanoseconds, the switching time to a lower current will be always smaller. Okay, so we use this value. I wanted to make clear how we use this estimation. The reviewers agreed with us for doing this estimation, and we calculated an energy that is extremely low, is 8.8 femtojoule. This is more than 1,000 times lower than the smallest ever reported before, and this is close to the thermodynamic fluctuation energy. So basically, it cannot be lower. Of course, we will need to, if we use this in a real circuit, we will not be able to work in this regime, but we will be able to reach ultra low energy consumption. And finally, I wanted to show you the most difficult plot of the whole study. We measure 80,000 cycles. We measure the resistance in every cycle. In the case of endurance plots, let me just mention something. You will see papers in which they report billions of cycles. Okay, there is something important, is only the studies that measure the resistance in every single cycle are reliable. If you see a plot with 1 point here, another here, another here, another here, and they say 1 billion showing you 9 points in the plot, forget about that. You need to measure it in every cycle. And we have also observed that if we fabricate several devices, we can reach also similar characteristics and distinguish absolutely all the cycles, which is something very complex to do and never reported in any 2D materials-based register. So as a conclusion, I wanted to say that boron nitride produced by mechanical exfoliation is a fantastic dielectric. However, this is not scalable to the wafer level. If you use CVD, which is scalable to the wafer level, you will not get an extremely good dielectric. You cannot use it as a gate dielectric, but you can use it as a resistive switching device. It's a MEMS resistor. And with this, you can create you can create two stable states to fabricate to fabricate electronic memories. You can induce several stable states to use it as a synapse, or you can also induce one stable state and one unstable state. And with this, you can make a neuron. So I think this is all the technical information I wanted to give you. We have published several articles in this field. You can see some of our papers here. We have two advanced materials coming soon, and one Nature Electronics coming soon. So you can also check if you want more information. And also, finally, let me just mention that I am starting a new group in KAUST. I joined KAUST in 2021 in January. So I have several open positions in my group. We offer extremely generous scholarship for the whole master. We have here fantastic laboratories. I have never seen something like this, and I worked before in Stanford. So I think this is an amazing school. This is why me and my team, we are moving here. We are now buying all the machines new. We have an amazing clean room. So I think it's a good opportunity, because especially for master students, we offer full scholarship. We offer the flights, we offer the salaries, everything is included. And for PhD, we also offer full scholarship. So I think it's something that if there are some young people hearing me, maybe if you are interested in working with us, you can contact me. And that's everything from my side. Thank you very much again to Marcelo for inviting me and for this nice organization.
Thank you, Mario. Thank you for accepting your invitation. Thank you for a very nice presentation. You forgot to mention that by going to KAUST, you will be close to the World Cup next year, right? So you'll be you'll be very close. The person that accepts your invitation to go to KAUST will be very close to the World Cup next year, right? The soccer.
Yes. Yes.
It is another advantage, right?
It's another reason to come to the area.
yes, of course. Not only for the work, but also for the soccer. So, question for Luis Pinotti here in the chat. So first, he congratulates you for nice work, and then he asks a question concerning the artificial neural network. My question concerning the artificial neural network is if the boron nitride devices can be integrated in FPGA chips for simulation of analog signals. And his question continues. And if we are close to using the boron nitride devices to implement the full firing of the neutron, maybe encoding phase shift between neurons for the computing task. And he thanks you for the answer.
Yeah, actually, the point of the integration, because we have the transfer, we can definitely integrate it in a crossbar array. This is something that we are doing. If your sample is patterned with some devices, let's say CMOS transistors, you also can connect this boron nitride to these terminals of these transistors. Actually, we are working now. We are making a tape out in TSMC to fabricate one chip, and then we will transfer our boron nitride on top, and let's see what happens. We are trying with some wafers from China. It gives us good results. However, they are single transistors, some small 1T1R crossbar arrays, and we want to do also some other circuits, even for other applications. So far with the 1T1R and with the crossbar arrays of 1T1R, in which we have the CMOS transistor and the boron nitride memristor, it works very well. And we can control and even reach much lower variability because the CMOS transistor, I mean, you see here the problem, right? Here we have some overshoot when we measure, because the current limitation of the semiconductor parameter analyzer is not enough fast. But with one transistor limiting the current, this is instantaneous. We don't need to worry about overshoot. And what we see is that the variability is lower. So we think integrating this in circuits will have benefits. And regarding to the analog, here we are seeing nearly analog transition from one state to the other. And we also see that all these states are stable over the time. So what is being difficult is to control the depression and then potentiation again, and then depression again, which is something we still didn't present. We have progress on this, but we are working on this. I think it has a lot of potential. So given the support that we are getting in terms of funding and in terms of publishing, I mean, funding agencies and editors are betting for this approach of integrating the study material in the chips. So I think even companies, you see the foundries doing. So I think it can have applications. In our case, we don't want to start with the most difficult thing. The transistor is much more difficult to fabricate than one memristor. It requires more lithographies, it requires more materials. So I think this is a winning horse because it's much cheaper. You can reach higher integration density. Variability is not a huge concern, as I can show you before. So basically, the numbers that we reach a yield of 98%. I forgot to mention. So nobody has reached these numbers with transistors so far, even the companies. But we have reached with memristors because the device is less sensitive to variability intrinsically. So I think we are in the good direction, but who knows?
Excellent, thank you. So, well, unfortunately, we are a bit behind the scheduling. And then I will ask the people who has some questions to Mario to send them to me, and I can forward it to you by mail, and then you can answer them. Once again, I would like to thank you very much for your very nice presentation. So let me then interrupt. Luis is thanking you for the explanations. So let me then come back to my screen and just say that we are now we are a bit behind the scheduling. I hope you are now looking at my screen. So we are going to have some interval, but not a 15-minute long interval. We are doing just a 10 minutes interval, right? So we will start at 11:35, and then we will preserve a bit of most of the lunch break for everybody, okay? So see you in the next 10 minutes. Thank you for coming and see you. Mario, once again, thank you very much.
Thank you very much for the invitation.
Everything has something to say. But someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB-IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
ABSEMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABSEMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions.
Hello, Merlin. How are you going? Oops, your microphone is mute.
Unmute. Can you hear me?
Oh, yeah, sure. Good to see you. Very nice. It has been a pleasure to talk to you today in the morning.
Thank you. Thank you for your help.
Oh, that's nothing. And thank you for accepting my invitation. It is a pleasure to have you with us. And we are just in the break. And then in 5 minutes, we should be ready for restarting over the mini-colloquium. So it's time to have some order and then spread our legs and so on. And then we will be moving back.
Okay.
And but I see it is sunny there in UK, right?
Yes, today, miraculously, we've had a bit of sun.
Oh, very nice. Very nice.
The last 2 weeks, it was completely dark and miserable.
Oh,
yeah? Yes. We had
Oh.
rain. So, yes.
Okay. So we are, I see we are in the main room.
Am I? Yes. The thing is that I cannot.
I don't know. Well, actually, I tried to open and break out a room, but it wasn't working for me. I don't know why.
Yes,
so
and for me
started
also.
Talking here in the main room anyway. And okay.
But I have a problem, Marcelo, because I cannot see my presentation. I'm seeing this SBMicro background slide.
Oh, yes. I think they have to give you the right to share your screen, and then you need to share your screen once again. You try it in the I think as I've seen here in the chat, you already tested the microphone and sharing screen. But once you came back to the main room, you have to share your screen once again.
Can we try that now? Because I had
yes, they are telling me that you can do it right now.
Okay, I can share my screen. That's wonderful. Why is it showing me 2? It's already shared, I think, somewhere else, maybe.
It is
Let
just
me see.
It is starting.
Can you see?
Yes, it works perfectly.
Okay. Yeah, that works.
Very nice.
Okay.
So, I will give you two or 3 minutes more to and then we restart. Okay.
Okay. I'm okay whenever you are.
Thank you very much. Thank you very much. Very kind from you.
I will move this down so. Hello. Marcelo.
You right?
Okay. You're still there. I can't see you because I've minimized this, so just want to know.
No problem. No problem.
Okay.
We are just about to start, and I will get back the screen just to introduce you, and then I will pass back to you the ball to start the presentation, right?
Thank you.
Yeah, I thank you. Okay, so Okay, let's restart. So welcome you that is joining us now. You are at the Chip in the Fields 2021 and in the SBMicro conference tutorials day, also which coincides with the 2021 IEEE Electron Devices Society Brazil Virtual Mini-colloquium. I am Marcelo Pavanello, and I will be with you during this presentation. And it is my pleasure visiting here the program. We are behind the scheduling, so we know additional. It is my pleasure to welcome Merlin de Souza from University of Sheffield in UK. I will just say a few words introducing her to our audience. But firstly, I would like to thank her for accepting our invitation to be with us in this mini-colloquium. And okay, so moving directly to her introduction, Professor Maria Merlin de Souza received her PhD from University of Cambridge. She became Professor of Electronics and Materials at the Emerging Technologies Research Center, Montfort, the Montfort University in 2003, and Professor of Microelectronics at the University of Sheffield in 2007. She has been a technical and member of the IEEE International Electron Devices meeting between 2012 and 2017. And a technical committee member of the IEEE IRPS Symposium between 2003 and 2013. She is currently technical committee member of the European Microwave Conference, EAS, REF, ISPS, and others. She has published over than 100 journal papers and 150 conference papers. So it is my pleasure to welcome her and pass her the ball. Merlin, thank you very much for accepting our invitation. The ball is with you, and I'm going to stop my video and
thank you.
Can share your screen once again, and your camera is also on, and people will be following you. Okay?
Okay, thank you. So, yes. Can you see my screen?
Yes, your screen is perfect. Okay, you are ready to go.
Thank you. Thank you for this invitation. And it's my real pleasure to be able to give this talk. It's the first time that I'm giving a talk in Brazil. And it's quite special for me because I have a family and cousins in Brazil that I have never met before. So let me start off my talk. Well, let me see what's happening here. Seems to be frozen. Okay. I'll begin with this traditional figure of scaling according to Moore's law. And basically what it shows is that starting from a 10 micron gate length with only a couple of thousand transistors way back in 1970, in 2019, AMD released this EPIC ROM chip, which was done in 7 nanometer technology node and held 32 billion transistors. Now, basically, Moore's law says that every 2 years, the feature size scales by 0.7 times and the transistor count doubles from node to node. But one of the things that we need to notice here is that in these latest technology nodes, these numbers are no longer related to the physical dimensions of the gate length of the transistor. Let me quickly go through the basics of the MOSFET or the MOSFET transistors, which lies at the heart of this CMOS revolution. So it's a 3-terminal device where the source and drain consists of very, very heavily doped regions of the same polarity, and they are separated from each other by a lightly doped channel that is controlled by the third terminal, which is the gate. Now, the gate is separated from the channel by an insulator. And by switching or adjusting the voltage on the gate, it creates an inversion layer at the surface of this semiconductor and allows electrons to flow from the source to the drain. Now, this current which flows is proportional to the charge because Q equal to CV. It's proportional to the mobility of the carriers, and it's proportional to the lateral electric field, which is the drain voltage divided by the channel length. If you plot this drain current versus this gate voltage, you can see that it is a linear relationship, and below a certain threshold voltage, it feels as if there is no current flowing through the transistor. But if you show the same plot on a log scale, you can see that it has a rich characteristic. It's a straight line, which means that the drain current is exponentially dependent on Vg minus Vt. Now, why do we have this current? Is because the tail end of the Boltzmann's distribution of carriers in the source region have enough energy coming from thermal vibrations to cross this source to channel barrier. Now, over the years, we have been specific about what we want from generation to generation in terms of the improvement in our electronic devices. And there are two criteria. The first is the delay. The second is the power consumption. Now, delay time tau, which is the transit time for a carrier from the source to the drain, is simply the charge divided by the current, because current is rate of flow of charge. And this is proportional to square of the length. So if we want to make our device faster and faster, we need to reduce Vd, and we need to reduce L, and we need to increase the denominator here by high mobility channel materials, for example, and to boost up our current as much as possible with high gate capacitance. When it comes to the power consumption, we have two contributors. The first is when the device is switching, which is called the dynamic power consumption, and that is simply given by the energy, which is half CV squared divided by the time. And that is time is the reciprocal of the frequency. And the static power consumption corresponds to the off-state leakage current, which we have just seen, and that is Vd times I. Now we can see in this article way back in 2006 that the static power consumption has exceeded the dynamic power consumption at quite a long while ago. So what have been the challenges of innovative scaling through these decades? The first and foremost objective of design is to ensure gate control under all bias conditions. That means this gate should control the channel region. But we know, for example, in an N MOSFET, we apply a positive voltage to an N-type region, and this is a reverse biased junction. So when we apply a voltage here, we will have a depletion region extending into this lightly doped region, and this field penetration affects the control of the gate over the channel. So it's not just enough to reduce the channel length, we needed to reduce the junction depth, and that resulted in an increase in the series resistance. So industry had to bring in new technologies to replace ion implantation, which involved molecular doping that allowed these regions to be doped well above the solid solubility limit of the material. We also want to increase the doping here to support a shorter gate length and to prevent this depletion region from extending here. But the problem with that is that you end up with a high threshold voltage, which reduces your drive current. And another problem that arises with increasing the doping here is that you end up with a higher electric field here that increases the band-to-band tunneling and thereby the off-state leakage. So one of the techniques to support this is to introduce what is known as a super steep retrograde channel, where the bulk of the doping lies well below the surface. And indium was one such atom which was introduced into the CMOS line at the 65 nanometer technology node. And the other big problem that arises, or the challenge arises, is that in order to boost up the capacitance, we need to thin down this insulator, and that led to a very high gate tunneling current that increased the standby power dissipation, and this was therefore replaced by high K gate dielectric at the 45 nanometer node. So if we look at the history then, at the 90 nanometer node, industry introduced silicon germanium technology to boost up the mobility of the PMOS transistor via strain in 2003. And at the 65 nanometer node, they introduced indium channel. There were two companies that did that, and we worked with one of them to solve some of the problems that came about because of the very peculiar problems arising from the heavy indium atom. At the 45 nanometer node, when high-K was introduced in 2007, there were a lot of issues, including soft optical phonon scattering, a lot of traps, and we were also involved in the resolving some of the problems associated with this introduction of the high-K. At the 32 nanometer technology, industry introduced self-aligned via patterning in 2009. But in 2011, they shifted at the 22 nanometer node to a three-dimensional geometry instead of the conventional planar transistor. So just going into this a little bit in terms of the substrate, in the beginning, transistors were planar on bulk CMOS, but this requirement to have very good control of the gate over the channel meant that there were ideas of partially depleted SOI and then fully depleted SOI introduced that allowed for much better electrostatic control. And there was a French company, Soitec, which continued to pursue this option. So then the FinFET, of course, is a device where the gate wraps around the channel in 3 dimensions. It allows for much better electrostatic control. And since it was introduced in 2011, pretty much since then, in subsequent nodes, all that has happened is that the fins have become taller and thinner in size. Now, in the 2019 IEDM, Robert Chow, who is a fellow at Intel, gave a presentation on some of the technologies which are about to come in the future. And he mentioned a bit about these 2-dimensional stacked materials, as well as other materials such as 3,5 or gallium nitride, for example, which is very useful for the power management side. And in fact, last month, Intel announced the ribbon FET technology, which will be the 2 nanometer node, they said, in 2024. And they announced that this will be a big step change in the technology, similar to what the FinFET did in 2011. And you can see the way in which the stacking of the materials is taking place in the vertical direction. So looking ahead, what are the challenges to achieving a drain supply less than 0.3 volts? Because that has been the target more or less over the last 10 years. And it's one of the challenges to reduce our power consumption. To answer that question, we go back to the log of this IDS versus the gate or the drain voltage. Here it is the gate voltage. And we can see here that in the subthreshold region, the slope of this line is always restricted to 60 millivolts per decade at maximum. If we reduce this voltage by 60 millivolts, what it says is that the leakage will increase by an order of magnitude. And that has the net effect of reducing this on-off ratio, which means that the fan out or the number of transistors that can be driven by a gate becomes small. For a good transistor, we want very steep switching. We want it to switch vertically rather than have this slope. So the entire emphasis has been to try and beat this Boltzmann's limit. Now let's try and understand this Boltzmann's limit a little bit better. I've already said that it comes from this factor, this Boltzmann's factor, KBT, and the drain current is simply exponentially dependent upon the surface potential of the semiconductor. And we saw that the subthreshold slope is the inverse of the slope of the log ID versus VG. And we just multiply and divide by this d psi s, and we can then express it as two factors. One is dVg by d psi s, and the second is 2.3 kT by Q. Now this is called the body factor M, and the second term is called the transport factor N. Now to get N less than 1, one of the ideas is on tunnel FETs, but I'm not going to cover that in this talk. I'm going to focus mostly on the body factor M. So when we apply a gate voltage on a MOSFET, this voltage gets distributed across the oxide, and the remainder of it gets dropped across the semiconductor in order to create this inversion layer channel. Now in this scenario, we are neglecting the work function of the transistor because we are assuming that both the metal and the semiconductor have equal work function, and we don't need to spend any more voltage in order to achieve flat band. Now, if we differentiate this equation, then M is simply dVGS by d psi s. It is a factor. It indicates the coupling between the gate and the semiconductor and shows how strongly they are linked together. That means if all of the applied voltage was dropped entirely on the semiconductor and nothing was dropped on the oxide, then M would be 1. Let's consider these two cases. The first is M greater than 1. That means the numerator is greater than the denominator, and the voltage across the oxide is then greater than 0. And you can see that a much larger voltage is dropped across the oxide and the remainder across the semiconductor. But if M is less than 1, then the numerator is less than the denominator. And what happens here is that the dVOX, or the voltage dropped across the oxide, is opposite to the direction of the applied voltage on the gate. And this will then lead to voltage amplification. Let's try and visualize this, what it means, because this is a simple way to explain things. And so I just take a beaker and represent this dVGS by this red lines here. In the situation when M equal to 1, d psi s is exactly equal to dVGS. But in the situation where M is less than 1, we are applying a small voltage on the gate, but we are seeing a much bigger voltage in the semiconductor. That means we are amplifying the voltage applied on the gate inside the insulator itself. How does that work? Let's go through a simple basics of what is a capacitance. Now, a capacitance consists of two parallel plates, and if you apply a positive voltage on one of the plates, it attracts charge of the opposite polarity on the other plate. And the amount of charge that it attracts is directly proportional to the voltage that you apply, to the thickness of or the separation of these two plates, and the dielectric constant of the material. In a capacitor, the more voltage you apply, the more charge gets attracted. So in a linear fashion. And that means the energy that is stored in any capacitor, which is described by this relationship, is given as half CV squared. Now, we can see that this is an equation of a parabola. Now, on the other hand, in a negative capacitance device, the energy versus the charge profile is not a parabola. It's not U-shaped, it is W-shaped like this. And if you double differentiate this curve, the reciprocal of it is the capacitance here, plotted in blue, and that is a parabola here. And you can see that this is the zero line here on this axis, and this portion of the capacitance is actually negative. It's less than zero. Now, the charge versus the electric field or the voltage, because electric field is just voltage divided by the distance, the profile of that is described by this S-shaped curve. What does it mean? Now, we know that when you apply a voltage on a capacitor, the charge begins to increase until it reaches this particular voltage. But here you can see that even though we are reducing the electric field now, the charge continues to increase up to this point, and then it begins to resume the normal behavior that you would expect in a positive capacitor. That means in this particular region, the slope is negative and the capacitance is negative. And this is then results in two states inside the insulator. This is one state which has lower amount of charge, and this is the second state on the top which has a much higher charge. And this S-shaped curve is described by this polynomial. And this is a characteristic property of a ferroelectric material which has got dipoles inside it. So typically alpha and beta represent the dielectric constants of this material. And for most general analysis, people ignore the fifth order term. Now, what happens if we take the ferroelectric, we sandwich it between two metals and we apply a voltage across it? Now, we are talking about an intrinsic transient negative capacitance. And what that means is as follows. We saw that the U versus Q profile is W-shaped, as described by this equation. And if we just apply an electric field to this equation, say of plus 0.3 megavolts per centimeter, we can then tilt this energy profile. Because in this black curve, the minimum energy points are here or here. It's not here. And the material, if it wants to swap from one state to the other, it needs to transition by the application of this electric field. So this will then result in the dipole moving to this point in the U energy curve and then dropping down over into this energy minima. And when you release the electric field, it will then jump back to this side. So it has moved from one state to another, and this takes a finite amount of time. Now, if you want to make this fast, you need to apply high voltage. But if you apply a low voltage, this process takes a bit of time. You can't have both. And in CMOS, we know that our main goal is to try and minimize the voltage on the transistor. So if we had to do a quasi-static simulation of this transistor, therefore, of this ferroelectric FET, what we will get is, therefore, we get steep switching at these 2 points corresponding to this transition at these 2 ends. And we will always end up with hysteresis. Now, we want to get rid of the hysteresis because obviously we cannot operate in a CMOS device under hysteresis. And the idea for that was proposed by Salahuddin and Datta in 2008. What they suggested is that you put a dielectric in series with a ferroelectric, and so you get this energy profile of the dielectric, which is parabolic. The ferroelectric is W-shaped like this. And if you add these two, you then get this red curve, so that the state of this ferroelectric remains in this flat portion. If you then apply a small positive voltage, you can see that it tilts the parabola to one side, exactly opposite to the direction in which it tilts the ferroelectric. So that the net is that this dipole moves to this situation. And then if you keep on increasing this voltage, it drops down even more. And going back up, you can see it will move back to this U-shaped profile and then go back when V equal to 0. Just looking at the Q versus E curve, we have the straight line for our dielectric. We have the S shaped for our ferroelectric. But you can see that when we combine these two, we have got rid of this negative slope. And so the slope now is either infinite or positive in the positive direction. And that eliminates the hysteresis, or is supposed to eliminate the hysteresis between the forward sweep and the backward sweep, which comes because of these two states of the ferroelectric material. The conditions to stabilize this, they proposed, was that the thickness of the ferroelectric should be less than or equal to the thickness of the dielectric divided by the dielectric constants of both materials. Unfortunately, over the last decade, people have been trying very hard to get rid of this hysteresis. And there was a review published by Purdue University in 2019, which showed that the smaller your subthreshold slope, the larger is your hysteresis. You can typically observe hysteresis-free negative capacitance FETs, but only at a very small scan rate or a low frequency of operation. So this has been a challenge. Now, there are lots of claims of hysteresis-free FETs, and one of them is this work by Purdue again, where they showed in IEDM 2017 these N and P-type germanium transistors, where you can see in the forward and the reverse direction that there is very little hysteresis. And subsequently, the next year in 2018, they showed the same thing on a molybdenum disulfide transistor. But in this case here, they actually said, they showed just slow, medium, and fast. They didn't actually tell us what the frequency was. But you can see that as you increase the frequency, this hysteresis begins to increase. The other thing you notice in this paper of theirs is that in the forward direction, the subthreshold slope is much higher, but in the reverse direction, it is quite small. So there can be two reasons for this, you think. One is they didn't stabilize this device correctly. Or the second thing is transient effects. Now let's understand what is the meaning of transient effect. So one is intrinsic and the second is extrinsic. And very often this ferroelectric FET is described by what is known as this LK equation that describes this S-shaped profile. Now, let us start with this LK equation where rho dq by dt is given by minus du by dq. This is nothing but Ohm's law because this side is V equals I times R. R is rho is the resistivity. And we can assume gamma equal to 0 for simplicity, and the electric field is nothing but voltage divided by the Tox. So we differentiate this right hand side with respect to charge, and we then get this equation when we substitute it in here. Now we can represent this equation by an equivalent circuit. That means if we drop a voltage across an intrinsic ferroelectric, it has a resistive component here, R dq by dt, which is given by rho times Tox, because you just multiply Tox everywhere to get rid of the denominator. And the capacitor is given by this term, which is 1 over Tox times 2 alpha plus 12 beta q squared. So in this original conventional ferroelectric idea, it was proposed, this is the LK model, where it is assumed that as you apply the voltage on this ferroelectric, these dipoles switch from one side over to the other side. And you know that this material has negative capacitance in this region. In this part, of course, it is greater than 0. But then in 1990, there was another school of thought which said that a ferroelectric is not really a single domain where it is possible to switch the dipoles from one direction to another. What actually happens inside the material is that when the electric field strength increases, these small grains are formed which start to expand with the dipole in the opposite direction. So the original dipoles in the original direction start to shrink, and these new dipoles start to expand. And without actually checking about the intrinsic mechanism, they said you can get this hysteresis, but you don't really need to have any negative capacitance associated with this behavior. And this is referred to what is known as an extrinsic transient effect, because that's talking about a multi-domain scenario, not really associated with a single domain picture of the ferroelectric. Now let's try to understand the origins of hysteresis. And we look first at the energy profiles of an unstabilized ferroelectric versus a paraelectric, which is like an ordinary dielectric. And we have already seen the U versus the Q curve. We saw that it is W-shaped and you can tilt it. But when it is a U-shaped paraelectric, we can do the same thing. When you apply an electric field, it will move it from one side to the other. That means that the system acquires a non-zero polarization from the electric field corresponding to that minimum. Now, under steady state and dynamic conditions, what happens? Let's look at this equation. And we can then see that in the steady state, dq by dt is 0. And we can then see that we get this blue curve in a ferroelectric, and the hysteresis is eliminated only in this scenario. In a general dynamic condition, when dq by dt is not 0, you would always expect to see a hysteresis. And this hysteresis, of course, depends upon the value of your rho. How does this differ from a paraelectric? Not that much, really. It's just that this is tilted forward with a positive shape, but you would still get this hysteresis in the curve as long as we are considering dq by dt not equal to 0. And corresponding to this Q versus E field, we have this behavior of the energy versus Q. This is the U-shaped profile of a paraelectric, and the blue one is the W-shaped profile of a ferroelectric. But under dynamic conditions, you can see that the green and the red look pretty much identical. You can't really make out the difference between the two. So let's look at the dynamic transfer characteristics of a ferroelectric FET in such a case, because we can now recognize that there is a frequency of operation. And what we see here is that as we increase this frequency in a ferroelectric FET, mind you, it's not a stabilized FET, you can see that the hysteresis increases. And these regions here correspond to the voltage dropped across the oxide with VGS. And we can see very clearly that they have the same corresponding relationship in the IV curve. And if we look in the literature, we'll see loads of facts being published, which show this small region of steep switching being achieved in the characteristics of a ferroelectric FET. But most importantly, I want to point out this particular figure that we published about 2 years ago. And it shows that in a ferroelectric FET, it is actually possible to get less than 60 millivolts per decade, both in the forward and the reverse direction. But you can see that you have to eliminate the frequency is very, very difficult. Except in the most stringent of cases when dq by dt is equal to 0. And there was only one other paper which more or less discusses the role of this resistivity in the literature, and that's from Hiramoto. In 2017, he tried to extract this behavior of hysteresis versus frequency. And you can see that he goes no more than 20 megahertz here, even though the rho is only 100 ohm centimeter. What is the situation with the paraelectric FET on the other hand? It looks almost the same. You have almost the same looking apparent behavior. But you can see that the forward slope is always larger than 60 millivolts per decade. It's only in the reverse sweep that a paraelectric is able to get sub 60 millivolts per decade switching, depending upon the value of rho and the frequency of operation. So it is the delay of this series RC circuit that results in less than 60 millivolts per decade during the backward sweep. And if you look at one of the latest papers from Suman Datta and his team, you can see that in fact a ferroelectric FET that they have published very recently, a few months ago, actually looks almost like a paraelectric FET. And in the forward sweep, it does not even show any region where the slope falls below 60 millivolts per decade. Now, most recently, in fact, earlier this year, we have shown that you don't even need a variable capacitor in order to get the conditions for m less than 1. You can even assume this is constant and that your voltage across the oxide is dropped across these two elements, because the parallel capacitor of this insulator doesn't make any difference. And we derived these conditions for m less than 1, and there are two of them. The first is here, that dVg by dt should be less than minus kT by QRC. And for the off state, and the second condition here we can see is that d psi s by dt should be greater than minus kT by QRC. Unfortunately, this situation happens only when the channel charge is less than 0, which means that the device is in the off state. So you would never really see it in practice. So just looking back at this body factor versus scan rate for this constant RC FET, we can see that we can get a body factor less than 1 for both the forward as well as the backward sweeps. But It is only in the backward sweep that we would actually be able to see this. The conditions under which this happens in the forward sweep occur when the device is in the off state. So you're not going to be able to see it at all. So there have been lots of people who have been modeling these transient negative capacitance steep slope FEFETs. And one such group is from Intel, from Mark Roder's group. And they use what is known as the PRESAC model. This is a quasi-static model again. And they introduce this delay time constant. They don't go into the microscopic model that leads to this delay. They say we don't care about it. But even with a single domain, large domain, you can see that you get this hysteresis, and they call it as an ideal hysteron. But the minute you have an ensemble of small domains, it becomes very, very difficult to control it and to be able to get this steep switching. Of course, the response time can be increased with a high voltage, but then that is too slow for low voltage CMOS. In fact, Hiramoto actually has published a paper in 2016 where he says a finite time response of between 10 to 100 picoseconds means we can achieve switching of 10 megahertz with negligible hysteresis. But of course, CMOS doesn't work in megahertz. We all know that our processors are now in the gigahertz region. Now, there have been a lot of papers from various groups, high-profile groups actually, talking about this multi-domain and how to get hysteresis free. And basically what you can see is they have many domains, and that leads to large number of hysteresis. But they say literally you have to go down to 3 domains, to reduce the amount of hysteresis. Of course, this is quite a bit of a challenge, and their model actually doesn't take into account the resistivity of the material. So we thought, let's add this resistivity and see what happens. We haven't actually published this work yet, but you can see that in an intrinsic ferroelectric FET without stabilization, we take rho equal to 100 ohm centimeters. And the parameters of our ferroelectric that we have considered are published for this 1.5 nanometer node, which is going to be out in 2028 and has been published by Salahuddin's group in just very recently, a few months ago. So we take these alpha beta parameters, and their thickness is 1.5 nanometers. And we then stabilize this, and we can get a certain dielectric that we can add in series, and we can get rid of this hysteresis at 1 megahertz. But the minute that we extend the frequency, increase the frequency, we can see that again the hysteresis reappears, even though this is a single domain approximation. We are then forced to reduce the resistivity of the material all the way down to even almost 1 ohm centimeter in order to get rid of this hysteresis. And then we look at what happens if we look at the multi-domain approximation. We can see here that we've got 5 domains. And if we just vary the resistivity from domain to domain by only 20%, we can see that it's very, very difficult to get rid of the hysteresis altogether. So that's the first challenge. The second challenge we find is that this optimization requires us to reduce the capacitance of the dielectric. And when it becomes so small, then what happens is that it comes to a stage where the stack is no longer able to respond because all of the electric field gets dropped across this dielectric alone. So that becomes very, very problematic, not just for the switching, but also for the reliability of the device. And how far can we scale when we want to reduce the capacitance, you are forced to increase the thickness. So that brings about a big problem. I'd like to point out a recent development, or maybe not so recent, but there was this idea proposed in a theoretical paper from UCL in London by Pavlo Zubko in 2016. It's a Nature, Letters to Nature. And they proposed this concept of superlattices, multi-domain ferroelectric superlattices. And most recently, in fact, it's not yet published by this group from Berkeley. They have been able to demonstrate superlattices of hafnium oxide, zirconium oxide, extremely thinly scaled, and they have managed to overcome this 1 milliamp per micron holy grail in microelectronics, which to my knowledge has never been achieved so far. Now you can see that they, in their paper, which I've just sort of copied here for the sake of explaining, they say that there is this performance indicates that the equivalent oxide thickness of their stack is only 6.5 angstroms, which is even smaller than the interfacial silicon dioxide of 8 to 8.5 angstroms, and they've shown the TEM figures of that in their paper. But what they have not yet shown here, I'm afraid, is the scan rate or the forward and the backward sweeps in this transistor. So maybe since it is still under review, that is something that that might come out of this work. But it's a very promising work to take this direction forward. So the reality is that even in a stabilized FET, it is typically operated in a non-quasi-static mode, and it's a combination of both transient and negative capacitance effect. So are there any other mechanisms of steep switching in paraelectric FETs? And that's the question that brings us to our contribution. So we've heard from the previous speaker that tantalum oxide is a very good material, and we made thin film transistor way back in 2017, where it's got quite large geometries. We have not scaled the device, but we began to see these very peculiar characteristics. And what happens in this device is that when you apply a positive voltage on the gate, it attracts the negative oxygen ions inside the material and drives the positive vacancies towards this interface at the channel. And that boosts up the number of electrons in this zinc oxide and gives a very low conductance state and increases the current. What is interesting is that always between a positive charge, an electric field goes from positive charge to negative charge. So an internal electric field is generated by the separation of these ions, which is opposite to the direction of the applied electric field. And this is why I was trying to explain in the beginning what is the concept which is required to have this M less than 1 condition. You have to have an internally generated electric field which is opposite in direction to the applied gate field. So we were able to show steep switching even down to 26 millivolts per decade without any ferroelectric. This is purely a paraelectric and is a non-filamentary process as well. Our frequencies are quite low though, because we did not optimize the device, and the gate of the device extends on the entire chip. So there's very large capacitance involved because of that. So what is the mechanism of what we call as a solid electrolyte FET? It's called an SE FET here. And it's got these two states. One is with the vacancies towards the channel. The second, of course, is with the vacancies towards the gate. And we developed the theory of this by solving the Poisson equation in combination with the density of states of the material. And we can see here that the U versus Q has got not a perfect W-shaped profile, but it's got these kinks which result in this negative capacitance effect. And we can see that in the forward direction between point C to D, this actually happens when the device is in the off state, because the threshold voltage of the device is somewhere at 0 volts. So we are only able to see steep switching in the reverse direction, as we have just explained. In the forward direction, the subthreshold slope is much higher. So if you look at the subthreshold slope versus frequency, then we can see these are the experimental curves, and this is the theoretical curve. And we can see that for a certain region, we can get steep switching in this device based on this mechanism. Now, why is this behavior not related to interface states? That can be a normal question to ask. And of course, we did this with silicon nitride. And if it is with interface states, you get a clockwise hysteresis in your IV. Whereas in the situation where you have this negative capacitance effect, the hysteresis is counterclockwise always. So what comes next? Traditionally, and of course, Mario Lanza gave a bit of background to this. Traditional computers are very limited because of the separation of the memory unit from the processing unit. And the tendency then is to try and imitate the mechanism of the human brain. In a human brain, each neuron actually does the processing. It stores the information as well as it does all the communications. And so the trend is towards memory, a concept called compute in memory, where you can link all of these memory devices or memristors in a crossbar array to simulate the cross connectivity of the neurons in a brain. And because they are compact and they can be easily integrated into CMOS on the drain voltage, pretty much two-terminal memristors have taken off quite a lot. Now, let's look at what is this conventional. I want to move this. Sorry. So let's look at conventional von Neumann architecture versus a human brain. Of course, a human brain works on what is known as spike timing dependent plasticity. And what that does is that it's the time difference that these between the signals received from one neuron to the other, which determines the strength of this connection between the neurons. Now, that's a very simple concept, actually. It says that if this neuron spiked just before this one, then it means that it spiked because of this neuron, and so the connection between them is strong. But on the other hand, if this one spiked first and this one spiked second, it means that this one spiked because of some other neuron, not actually this neuron. So the strength between these two neurons is weakened. And just this timing difference between these spikes is what dictates plasticity. So we look at the spike timing dependent plasticity of our S effect, and we can see that we've got some strong EPSC current that we have registered. And we have also been able to report 3 to 4-fold increase in EPSC with the frequency of the stimulus spikes. And this is similar to dynamic high-pass filter for information transmission in some specific types of neurons. More than that, our device, our S effect, is an active memristor. And what is meant by an active memristor is that it's got a certain negative differential resistance inside its gate characteristics. You can see here that the voltage is, magnitude of the voltage is increasing, but the current is actually reducing. So this is a redox mechanism that we have explained in this article of ours. And this type of an active memristor can then function as a neuron. We've been able to demonstrate logic operations in the off state with our SEFAT. You can see very clearly the conductance level of the current. This has high current, so it's a low resistance state, whereas here for the high resistance state, the fluctuation is much harder than expected. But the beauty of the device having the third terminal is, of course, you can operate the device when it is off, and that reduces the power consumption. And we've been able to show 16 operations in our device, in a single device, just by using this concept of the switching it when it is off. If we had to benchmark and our device and scale it further, we can see here that our switching time is very slow, but the power dissipation is very small. And the reason why the switching time is very long is simply because the oxide thickness is very large. We haven't scaled our device dimensions. And if we were to scale it, we could then achieve a switching time almost in nanoseconds if we just extrapolate with the fit to our measured data. We've also shown the crossbar array. This is simulated, but the simulation is based on experimentally measured characteristics of real devices. And then we put it in MATLAB and simulate an artificial neural network with just 4x4 devices, which can do an OR or an AND operation. And this kind of an architecture is very similar to what the ferroelectric FET is being touted for. One of the other things that we have managed to achieve with this SEFET is reservoir computing. And because of the fact that we can control the gate voltage and therefore get many conductance states, we were able to show a rich reservoir capability here and achieve 96% learning efficiency. Because in reservoir computing, there are two characteristics which are needed, and one is volatility, and the second one is a number of states, and our device is more or less an analog memristor. So this work is being done in collaboration with IIT Roorkee, where they are doing the simulations and we have been supplying them with our experimental results. So the next goal of CMOS, of course, just to bring a close to my talk, is what's going to happen, despite the best efforts in von Neumann architecture, we are way below in terms of computing efficiency compared to a human brain. And the human brain is, of course, it can process far more information than the fastest supercomputer because we are great in parallel processing, sorting, and getting together a sensory input and making instantaneous decisions. And no supercomputer can achieve that today. One main difference, of course, is that neurons only fire about 200 times a second or about 200 hertz, whereas the Intel i9 processor goes all the way in excess of 3 gigahertz. So this onward march, or the goal, is limited by the power at the moment, power consumption. Looking into the future, of course, these are CMOS neurons that have been implemented in a number of neuromorphic computers, and they have pretty low efficiency. But looking well into the future, we can even see that one day it might well be possible to exceed the energy efficiency of the human brain. That just brings me to my conclusion. I hope I've convinced you that rho is a critical parameter that has a direct impact on the hysteresis in any device, actually, particularly in a single domain stabilized FEFAT. So and we find that the bulk of the literature just ignores this parameter altogether. And we see a lot of challenges in trying to stabilize it and continue to achieve this last node at 1.5 nanometers in 2028. And I've shown some of the features of a non-filamentary SEFET, which also has an internal mechanism for steep switching. So ferroelectricity is not the only mechanism, of course. And this is very useful because it gives a rich number of states in applications for reservoir computing. I'd like to thank you for your attention, but before I wind up, I'd like to acknowledge my students, Premlal Pillai, who's now in Manchester University, Ashwani, who now works for a firm in London, and Song, who's a postdoc in my team, for a lot of the work that I've presented today. And I'd like to bring to your attention some sponsorships for industrial placement, which I'm running, and it's sponsored by the EDS Society. So if any of you have undergraduate, graduate, postgraduate, or master's students, recently graduated postdocs, PDRAs, working in any of these fields, and you want to spend some time in company, whether it is in Brazil or anywhere else in the world, even if it were virtual, or if you want to fly to that site, please apply. I'd really welcome applications, especially from Brazil and from South America. So thank you. Thank you for your attention.
Thank you, Marilyn, for a nice presentation. Thank you also for offering the opportunity. If you don't mind, I will try to divulge this opportunity amongst the other sessions in the conference, because it may interest several people. So if anybody wants to ask questions, this is the time. I also want to have a look on the YouTube. If anyone attending us on YouTube is willing to ask a question, please type the question at the chat in the YouTube session, and then I can read it and pass it to Merlin. I will start asking you, Merlin, about this ferroelectric FETs or FIFETs. A few years ago, I've seen a comparison between FIFET and impact ionization FETs, which are, let's say, easy to fabricate in silicon and so on. Could you please comment on the efficiency of the impact ionization FET or the FIFET compared with the impact ionization FET? Because in both cases, we end up with an hysteresis, which is not of interest. But when we started exploring impact ionization FETs, that was the most, let's say, challenge. But at the end, we end up with the same. So could you please comment if you see advantages and disadvantages on the option of the FIFET with respect to these impact ionization FETs?
I must say that, you know, I haven't gone into impact ionization FETs as such, but if just looking at where the industry is looking for, this hysteresis is a fundamental problem, simply because of the principles that I have explained and the dynamic conditions. So I don't know whether, you know, in an impact ionization FET, you know, what sort of scaling would happen in the gate of that material. So whatever I have said will apply generically to that as well.
Sure. Okay. Thank you. So let me double check if there is something on the YouTube. So I don't see any. So it gives me space to do an additional question regarding the end of your presentation. You demonstrated some logic functions or NN functions using for these applications. Could you please comment on the amount of energy spent in the processing of these two functions, because this is something that is also taking the attention of the scientific community, the amount of energy for using these, let's say, analog FETs, because they are on most of the time and then you cannot switch them off easily and it consumes a lot of power, or let's say, people say it consumes a lot of power. I'm not familiar with them at all. So could you please comment about the amount of energy for these functions?
Yes, so most of these, I think, they operate with filamentary mechanisms, which, when you are making the filament, you have to spend a slightly higher voltage. When you're reading, you can go to a lower voltage, and they are mostly two-terminal FETs, two-terminal membristors. Whereas if you look at the ferroelectric FET and the SE FET, they are three terminals. So you can use the third terminal to benefit. It's got a lot of benefits. That means you can operate it completely in the off state. You can write to the device, but you don't need to read at the same time. So you put a gate voltage and you can write to it completely, and there will be no drain current. And when you want to read, you switch the gate off and you just read the conductance state of the device. So that becomes an advantage in that sense. But I don't think I am in a position where we can directly compare, say for the same, same logic function, using a memristor array and a conventional CPU, because I think there's still a lot of work to be considered in the sense that people will go towards neuromorphic in a stage-wise fashion, and it's still, these neurons are still CMOS transistors. At the moment, these memristors are the ones which are only used as synapses, because they store the waves and they automatically do this. Inherently, you get this matrix multiplication and addition from them. So, okay. Yeah.
Okay. So, okay, from me, my questions are gone. Let me just check if I have any other from the YouTube people. No one. Excuse me, Merlin, I haven't heard you. I've seen you speaking, but I haven't heard.
No, I didn't say anything.
Oh, no, sorry, it is the delay on the YouTube session, sorry. Okay, so with that, I would like to thank you very much, Merlin, for your very kind attention with us, staying with us during this mini-colloquium. It has been a pleasure to have you with us today. And then I will move back to the program and just let you know. So let me share my screen once again. So I hope you are now looking at my screen. Yes. And then we are now at the lunch break. So I ask you have about 1 hour for the lunch break, and we will start very close to 1:45 p.m. here in Brazilian time for the next presentation on quantum computing in nanoscale CMOS. I remember you, this presentation is common for the EDS Brazil Mini-colloquium and also for the SBCCI conference tutorials. So we will be very, very close to the starting time. Okay, so thank you very much, you all, for staying with us in this morning session. I wish you a very nice lunch time, and then we meet each other in this afternoon session for these 2 remaining presentations. See you.
Thank you.
Thank you, Merlin.
Thank you. Thank you for the opportunity, Marcelo. Thank you.
I thank you very much.
Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. partner with the NB-IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
ABSEMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABSEMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. ABSEMI members have also been significantly investing in the establishment of research and development centers. An example is the El Dorado Research Institute, located in Campinas, state of Sao Paulo. El Dorado has the country's first semiconductor prototype laboratory. Another example is the ITT Chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces the dependence on global centers of semiconductor components. There are many opportunities. Only in the Internet of Things field, the economic impact expected until 2025 is about 10% of gross national product. Semiconductors are the brain of the electronics industry and the heart of the technologies that move the world. Brazil is already part of this important universe. ABCME believes in knowledge, innovation, and people as the keys to identify new technologies. Above all, ABCME believes in Brazil.
Somewhere, maybe right at this very moment, the next technology breakthrough is about to inspire the next generation of minds, thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good, because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. Their top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our ESOF electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3 of the world's high-frequency electronic designers, empowering customers to confidently bulletproof designs long before they're built. As the physical prototype is made, customers turn to Keysight once again to validate that it works properly in the lab and in a variety of real-world environments. These complex tests help prevent losses that technology companies may face if there is an undetected defect hidden in their product. The device is finally ready for mass production, and Keysight is ready to help its customers get the latest, greatest technology into the hands of eager buyers. Tens of millions of units are at stake here. Customers rely on Keysight to keep the line moving with accurate test solutions and tools to help them maintain quality. The result? A bug-free, cost-effective, high-quality product in the hands of people who need it. Faster. If there's a signal to be measured, Keysight is there. From satellites to base stations to mobile devices, our job is to ensure the signal is clear, true, and reliable. It's what we do for communications and beyond, energy, aerospace and defense, computers and semiconductors, automotive electronics and safety, industrial applications, education and research. In fact, the minds of Keysight have been behind the most important technology breakthroughs of the last century. And today we offer world-class services along with the broadest design and test portfolio of any company in the world. With our global network of experts, we provide an emerging array of services to accelerate our customers' business goals, including calibrating multi-vendor test instruments, managing asset portfolios, and providing training, consulting, and other professional services. As a premier future technologies enabler, partnering with customers to help them move from design through manufacturing faster and more efficiently, no other electronic design and test company is better poised to help deliver what's next. First.
Each new day, technology is more and more present in people's lives. Everyone is more and more connected. Technology does not stop evolving, advancing. Smart modular technologies is at the very heart of all this evolution, developing and innovating in the semiconductor industry. With a large and modern production center, advanced equipment, high tech, high-precision tooling, machine-to-machine communication, robots, training and advanced manufacturing, prepared for the fourth industrial revolution. Industry 4.0. SMART delivers products that form a tripod, processing and storage, communication, energy. More than 15 years producing semiconductor components for the world's largest manufacturers and dominating the chip packaging technology in Brazil. Memory modules at the forefront of high performance. Lithium-ion polymer batteries provide power to the most renowned devices in the mobile communications market. Approximately 670 million reais were invested in the development, design, and implementation of semiconductor components, such as memories for smartphones and other high-tech memory integrated circuits. And additional investment that can reach 700 million reais by 2021 is already planned. SMART is a global company and is proud to have chosen Brazil to be its technology center for semiconductor components packaging. Strategically located in the city of Atibaia, state of São Paulo. SMART also has a research and development center dedicated to its operations in South Korea. Products with high standards and excellence. 250 million reais have already been invested in research, development, and innovation of products and manufacturing processes. An example of this is the unprecedented investment in the creation of a semiconductor prototyping line within the El Dorado Research Institute in Campinas, state of São Paulo. The worldwide technological evolution does not stop. The priorities for the Internet of Things are already defined in Brazil. SMART is part of the National Internet of Things plan, developing innovations to keep at the forefront of all this evolution. People recognition, training and specialization. Professionals with the highest levels of academic background. The challenge of further driving and developing semiconductor technology is the challenge of creating the future. SMART works unceasingly to be at the front line of this future. Think memory. Think SMART. SMART Modular Technologies, developing technology and projecting the future in Brazil.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
What sparks innovation? Is it thinking bigger or smaller? Does it strike fast or slow? Is it a flight of fancy or a stroke of genius? Innovation is everywhere, on desktops, in pockets, on wrists, in us. Innovation answers big questions, finds inspiration anywhere. It connects great minds, imagines the impossible, and propels us forward. At Keysight, innovation inspires us, fuels us to redefine precision in measurement, to surface insights, to remove barriers so the next stroke of genius is yours. We are Keysight. We accelerate innovation.
Designing state-of-the-art millimeter wave products, whether for 5G, defense radars, or satellite communications, requires expanded test systems. Applications at millimeter wave frequencies require wider channel bandwidths and multi-element antennas to overcome increased path loss, which must be tested using over-the-air test methods. Over-the-air testing has traditionally involved more test equipment, more measurement uncertainty, and difficulty getting accurate and repeatable measurement results for chipsets and network equipment. Until now. Testing applications at millimeter wave frequencies is about to get much easier with Keysight's new VXG microwave signal generator. The VXG is the world's first dual-channel 44 GHz vector signal generator with 2 GHz RF bandwidth in a single box. Featuring a dual-channel architecture, The VXG allows quick switching from blocker and interferer tests to dual-channel MIMO and beamforming tests without ever having to touch your hardware. With its ultra-low phase noise and the industry's highest output power, Keysight's VXG overcomes over-the-air path loss challenges without sacrificing error vector magnitude or adjacent channel power ratio performance. The VXG, together with pathwave signal generation, gives you access to a wide range of evolving standards-compliant 5G new radio signals for testing base stations, mobile terminal transmitters, and receivers with channel coding and multi-antenna support. If you are designing, manufacturing, or deploying millimeter wave devices, Keysight's VXG will give you higher confidence in your device's performance, faster. Visit www.keysight.com/find/VXG for more information.
Technology now connects everything and everyone, everywhere. From smart cities to smart clothing, we generate billions of new connections that bring us closer, make us healthier, safer, smarter. But the more connected we are, the more challenging it is to meet our expectations. How do you innovate what's next, first? How do you keep up with the accelerating pace and complexity? More speed, less power, perfect accuracy, tighter security. The pressures to be first and best are greater than ever. At Keysight, we work with you to design, test, and operate tomorrow's most innovative technologies today. We help you adopt emerging protocols and standards before they're defined. We challenge you to reimagine your innovation processes in automotive and energy, aerospace and defense, wireless communications, networking, cloud, and the Internet of Things. We integrate your development workflow to accelerate your next creation. We make your network stronger, and we bring our decades-long insight, research, and expertise with over 500 industry and application experts around the world to help you every step of the way. Our customers are the world's visionaries and innovators. They partner with us to innovate faster across every stage of their development lifecycle and every layer of the stack, making their businesses more productive to gain a competitive edge. They dream, we test. So the next great innovation that connects and secures the world is realized faster than ever.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB-IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
ABCMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABCMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components, since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. ABCMI members have also been significantly investing in the establishment of research and development centers. An example is the El Dorado Research Institute, located in Campinas, state of Sao Paulo. El Dorado has the country's first semiconductor prototype laboratory. Another example is the ITT Chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces the dependence on global centers of semiconductor components. There are many opportunities. Only in the Internet of Things field, the economic impact expected until 2025 is about 10% of gross national product. Semiconductors are the brain of the electronics industry and the heart of the technologies that move the world. Brazil is already part of this important universe. ABCME believes in knowledge, innovation, and people as the keys to identify new technologies. Above all, ABCME believes in Brazil.
Somewhere, maybe right at this very moment, the next technology breakthrough is about to inspire the next generation of minds. thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. Their top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our eSoft electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3 of the world's high-frequency electronic designers, empowering customers to confidently bulletproof designs long before they're built. As the physical prototype is made, customers turn to Keysight once again to validate that it works properly in the lab and in a variety of real-world environments. These complex tests help prevent losses that technology companies may face if there is an undetected defect hidden in their product. The device is finally ready for mass production, and Keysight is ready to help its customers get the latest, greatest technology into the hands of eager buyers. Tens of millions of units are at stake here. Customers rely on Keysight to keep the line moving with accurate test solutions and tools to help them maintain quality. The result? A bug-free, cost-effective, high-quality product in the hands of people who need it. Faster. If there's a signal to be measured, Keysight is there. From satellites to base stations to mobile devices, our job is to ensure the signal is clear, true, and reliable. It's what we do for communications and beyond, energy, aerospace and defense, computers and semiconductors, automotive electronics and safety, industrial applications, education and research. In fact, the minds of Keysight have been behind the most important technology breakthroughs of the last century. And today we offer world-class services along with the broadest design and test portfolio of any company in the world. With our global network of experts, we provide an emerging array of services to accelerate our customers' business goals, including calibrating multi-vendor test instruments, managing asset portfolios, and providing training, consulting, and other professional services. As a premier future technologies enabler, partnering with customers to help them move from design through manufacturing faster and more efficiently, no other electronic design and test company is better poised to help deliver what's next. First.
Each new day, technology is more and more present in people's lives. Everyone is more and more connected. Technology does not stop evolving, advancing. Smart modular technologies is at the very heart of all this evolution, developing and innovating in the semiconductor industry. With a large and modern production center, advanced equipment, high-tech, high-precision tooling, machine-to-machine communication, robots, training and advanced manufacturing, prepared for the fourth industrial revolution. Industry 4.0. SMART delivers products that form a tripod, processing and storage, communication, energy. More than 15 years producing semiconductor components for the world's largest manufacturers and dominating the chip packaging technology in Brazil. Memory modules at the forefront of high performance. Lithium-ion polymer batteries provide power to the most renowned devices in the mobile communications market. Approximately 670 million reais were invested in the development, design, and implementation of semiconductor components, such as memories for smartphones and other high-tech memory integrated circuits. And additional investment that can reach 700 million reais by 2021 is already planned. SMART is a global company and is proud to have chosen Brazil to be its technology center for semiconductor components packaging, strategically located in the city of Atibaia, state of São Paulo. SMART also has a research and development center dedicated to its operations in South Korea. Products with high standards and excellence. 250 million reais have already been invested in research, development, and innovation of products and manufacturing processes. An example of this is the unprecedented investment in the creation of a semiconductor prototyping line within the El Dorado Research Institute in Campinas, state of São Paulo. The worldwide technological evolution does not stop. The priorities for the Internet of Things are already defined in Brazil. SMART is part of the National Internet of Things plan, developing innovations to keep at the forefront of all this evolution. People recognition, training and specialization. Professionals with the highest levels of academic background. The challenge of further driving and developing semiconductor technology is the challenge of creating the future. SMART works unceasingly to be at the front line of this future. Think memory. Think SMART. SMART Modular Technologies, developing technology and projecting the future in Brazil.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes. but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So get a taste of our work. Appreciate the little things and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
What sparks innovation? Is it thinking bigger or smaller? Does it strike fast or slow? Is it a flight of fancy or a stroke of genius? Innovation is everywhere. On desktops, in pockets, on wrists, in us. Innovation answers big questions, finds inspiration anywhere. It connects great minds, imagines the impossible, and propels us forward. At Keysight, innovation inspires us, fuels us, to redefine precision in measurement, to surface insights, to remove barriers so the next stroke of genius is yours. We are Keysight. We accelerate innovation.
Designing state-of-the-art millimeter wave products, whether for 5G, defense radars, or satellite communications, requires expanded test systems. Applications at millimeter wave frequencies require wider channel bandwidths and multi-element antennas to overcome increased path loss, which must be tested using over-the-air test methods. Over-the-air testing has traditionally involved more test equipment, more measurement uncertainty, and difficulty getting accurate and repeatable measurement results for chipsets and network equipment. Until now. Testing applications at millimeter wave frequencies is about to get much easier with Keysight's new VXG microwave signal generator. The VXG is the world's first dual-channel 44 GHz vector signal generator with 2 GHz RF bandwidth in a single box. Featuring a dual-channel architecture, the VXG allows quick switching from blocker and interferer tests to dual-channel MIMO and beamforming tests without ever having to touch your hardware. With its ultra-low phase noise and the industry's highest output power, Keysight's VXG overcomes over-the-air path loss challenges without sacrificing error vector magnitude or adjacent channel power ratio performance. The VXG, together with pathwave signal generation, gives you access to a wide range of evolving standards-compliant 5G new radio signals for testing base stations, mobile terminal transmitters, and receivers with channel coding and multi-antenna support. If you are designing, manufacturing, or deploying millimeter wave devices, Keysight's VXG will give you higher confidence in your device's performance, faster. Visit www.keysight.com/find/VXG for more information.
Technology now connects everything and everyone, everywhere. From smart cities to smart clothing, we generate billions of new connections that bring us closer, make us healthier, safer, smarter. But the more connected we are, the more challenging it is to meet our expectations. How do you innovate what's next, first? How do you keep up with the accelerating pace and complexity? More speed, less power, perfect accuracy, tighter security. The pressures to be first and best are greater than ever. At Keysight, we work with you to design, test, and operate tomorrow's most innovative technologies today. We help you adopt emerging protocols and standards before they're defined. We challenge you to reimagine your innovation processes in automotive and energy, aerospace and defense, wireless communications, networking, cloud, and the Internet of Things. We integrate your development workflow to accelerate your next creation. We make your network stronger, and we bring our decades-long insight, research, and expertise with over 500 industry and application experts around the world to help you every step of the way. Our customers are the world's visionaries and innovators. They partner with us to innovate faster across every stage of their development lifecycle and every layer of the stack, making their businesses more productive to gain a competitive edge. They dream, we test. So the next great innovation that connects and secures the world is realized faster than ever.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB-IoT pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
ABSEMI, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABSEMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. ABSEMI members have also been significantly investing in the establishment of research and development centers. An example is the El Dorado Research Institute, located in Campinas, state of Sao Paulo. El Dorado has the country's first semiconductor prototype laboratory. Another example is the ITT Chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces
So good afternoon to you all. I hope you had the opportunity of stretching by a bit your legs during the lunch time. And then we are ready to restart the afternoon session of our Mini-colloquium. These, just to remember you are in the Ship in the Field 2021, which is a virtual event, unfortunately, because of the outbreak. And remembering the program of the event is composed by several symposia, and we are here at the first day, and especially this next presentation is a joint presentation. This is the tutorial composed by the tutorials of the SBCCI and the tutorials for SBMicro, which corresponds or coincides to the 2021 EDS Brazil Mini-colloquium. So with that, I would like to say that the next presentation is for both conferences. So it is a joint presentation for both symposium, SBCCI and SBMicro. And I am Marcelo Pavanello. I am here to chair this afternoon session, the EDS Brazil Mini-colloquium. Well, the next presentation is then quantum computing in nanoscale CMOS using position-based charged qubits. It will be given, by Bogdan Stasevsky and Elena Blochina, but unfortunately, Dr. Blochina could not stay with us because of personal reasons. And Dr. Reza Nikandesh will substitute her, and he is with us to start the presentation. So, this being said, let me just confirm that everything is all right to restart. So, okay. Then I will stop sharing my screen and I will pass the ball to you, Dr. Reza, to start the presentation. So let me just move it to you, Dr. Nikandesh, in a while. Is there? Rafael, are you with us? Can you pass to Dr. Nikandesh the right of sharing his screen? I'm not finding the way to do that here now. And also unmute his microphone. Well, this I think I can do. done, and I think you can now share your screen. Yes, Dr. Nikandesh, thank you. If you want, you can open your camera. We are looking for your screen, and now looking at you in our camera. So thank you for accepting our invitation. It is a pleasure to us to have you among us. And then I pass the ball to you. Our presentation is around an hour, so please feel free to go ahead. If I well understood, Dr. Bogdan Stasevsky will join us during the presentation to take the second half of the presentation, right?
Thank you, Marcelo, for arranging this presentation. So as you explained to our audiences, and the topic of this presentation would be on implementation of quantum computers using CMOS technology. So I briefly start discussing about quantum computing, some current activities in this area, and then we put our focus on CMOS quantum computing, what prospects this approach will have, and what challenges should be solved before reaching a level that we can implement a quantum computer using standard CMOS technology. So here you can see an outline of my presentation. So after having a brief introduction, we will discuss about qubit fundamentals. We review qubit technologies, different implementation approaches that have been proposed for realization of quantum bits or qubits. We'll review approaches to quantum computing, starting from the past, reviewing the present, and having an outlook for future of quantum computing. We'll discuss about quantum gates, their interface with classical electronics, and at the end, we will discuss about some activities in our Equal One lab about charged qubit-based quantum computing. So quantum computing is heard in many different venues these days. So we can say that quantum computing is a transition from science to an engineering field. So it can provide a revolution in high-performance computing. You know that currently we have many applications which rely on high-performance computing. So here we can have a brief introduction about them. Artificial intelligence and machine learning needs a huge amount of computing power to reach a level which can be comparable to human level intelligence. So other areas like cryptography, big data, drug discovery, and imaging, or some other applications that when high computing power can be provided, they can provide higher level of performance in their own area. So that's the reason that currently there are many activities in both scientific and engineering areas to develop techniques that achieve higher level of computing power. So quantum computing is one of the areas that has received huge amount of funding by different government agencies for R&D and education. We can see that multi-billion dollars of investment have been spent by governments around the world. So here you can see an outlook to see what activities currently are ongoing on quantum computing. So perhaps some examples can be interesting here. For example, China, you can see that it claims of $10 billion investment in quantum computing. For United States, it's just 1.2 billion. So perhaps it needs something to be increased. And you can see that several other European countries which are spending too much investment on this area to make a future in quantum computing. Currently, there are many players in quantum computing in different levels, starting from software, hardware, and enabling technologies. So you can see some famous names. For example, in hardware, you can see IBM, Microsoft, Google. In software, you can see some other companies, OneQubit, for example. And in enabling technologies, again, several other companies, including big companies and also startups, are actively working on different aspects of quantum computing. So here is a big picture of quantum computing. So now I'm going to have a very brief overview of fundamentals of quantum computing. So quantum computers are built using a quantum bit or qubit as a fundamental element. We know that classic bit can only be in one of two logical states of 0 and 1 at the same time. So it means that we cannot have both of them at the same time, right? So only one of them. But qubits can be in both of two quantum states of 0 and 1 at the same time. So it's some fundamental difference between qubits and bits. So at the moment, it may not be very clear. So, but if you wait a little shorter, we will learn how this randomness can be achieved using qubits. Qubits has some special differences with bits. So superposition is one of them. It means that a qubit state can be described as superposition of two quantum states, 0 and 1. So we can show it, as you can see, as a linear superposition of two quantum states. So in other words, if we show the state of a qubit on a sphere, which is called block sphere, you can see that the state of that qubit can be described by position of a point on the surface of this sphere. So it means that in ideal situation, the radius is 1, and with two angles of theta and phi, elevation and azimuth, we can define the state of this qubit. So we can say that the probability of finding qubit state at a state of 0 is given by this value of a, actually a squared, and the probability of b, and the probability of finding qubit in the state of 1 is given by a square root of b. So normally we expect that a squared plus b squared be 1, because qubit would be in one of these two states. Another interesting feature of qubits, which actually help to achieve much higher levels of computation power, is called quantum entanglement. It doesn't have any counterpart in classic computations. So here we can say that if we have two qubits, their states can be somehow coupled to each other, so that these two qubits seem to be like a single particle. So if somehow we do a measurement on the state of one of them, a state of another one will be automatically known. So it means that we can have some kind of data transfer with very high speed, which is not something that we can achieve using classical communication. So qubits had some difficulties to work with them. So the most known issue is that qubits are extremely fragile and sensitive to noise and disturbance from external environment. So they will lose their quantum state. They cannot maintain it. So all of quantum computing systems need some kind of protection from the external world. So depending on the type of technology that is used, so some of the qubits needs to be maintained at very low temperature. Some of them needs to be very well isolated from external world so that they can maintain in quantum state. So as a brief example, here you can see a comparison between classical inverter and quantum inverters, which are quantum Pauli gates here. So in a classic inverter, we know that we can transfer the state of 0 to 1 and 1 to 0. So the function can be easily described by a logic function that we know about this. In quantum counterpart, the situation is more complicated depending on which axis or which plane we consider to do this inverting. Three types of inverters, quantum inverters, are popular. So for example, in the X, you can see that the quantum state of 1 here, it will be transformed to 0 here, right? And vice versa. So if we define a qubit state as a vector, which is 1 or 0, so this quantum gate can be described by a 2 by 2 matrix. So we can say it is X matrix, Y matrix, and Z matrix. So three type of elementary quantum gates which can be defined here. So for further information, you can refer to some of the textbooks which are introduced here. So we are not going to go through details of this quantum computations. It's mathematics, right? We just briefly review them. After using quantum beats to fabricate quantum gates, at the higher level, we use these quantum gates to realize quantum circuits. So a quantum circuit that you can see an example here performs specific functions on input qubits. So it can be used to realize a specific quantum algorithm. So here you can see, for example, here is a circuit that we have here. We have some kind of gates. For example, Z is a quantum gate that we discussed before. We have Rx pi over 2. So it is rotation around the x-axis by the angle of pi over 2, right? And so other types of quantum gates, which you can see here. So I'm not going to go through details here. And here we have some measurements. So based on the input qubits, we can have some outputs, and this specific circuit can realize some quantum algorithm. Different technologies are used for implementation of qubits. Perhaps the most important ones are superconducting, which are based on superconducting loops. They can have some specific feature. For example, they can provide very high speed, but needs very low temperature, means on the order of, say, 100 millikelvin, right? As currently some companies like Google, IBM, and D-Wave are working to build quantum computer using this technique and trying to fix these issues. We have other type of qubit trap ions, silicon quantum dots, topological qubits, and diamond vacancies. I think I should also add photonic-based quantum computing, which is another promising approach, which is not included here. Here in this talk, our focus would be on silicon quantum dots because they can be implemented using CMOS technology. That's a specific feature of silicon quantum dot. The special feature is high circuit density. So you can, using features of CMOS technology, you can fabricate very high density circuits. It should be operated at low temperatures on the order of a few Kelvin. Currently, some companies like Intel and research institutions like QTech and Leti in France, in Netherlands and France are working on this area. So that would be focus of our talk, and we will specifically focus on the techniques that can be realized using CMOS technology. So before that, I briefly review some of the currently available commercial quantum computers, which are fabricated by some of the active companies in this area. So the first one is IBM, which is based on superconducting qubits, and they have used micro signals to control the state of these qubits and do read out on their state. So as you can see here, this is a diagram of the circuit that is used here. It needs a large electronic system to interact with qubits. And you can see that because it is superconducting, it needs a very large cooling system. So you can see the size of cooling system is very large, right? And such a system cannot be easily integrated in a compact area. So the biggest issue with superconducting qubits is their area, because they need to be operated at very low temperatures. So here we have another example. So this is again using superconducting qubits. It's an experiment that Google used to claim achieving the supermassive milestone, which has been defined based on a specific criteria that the quantum computer have been able to perform a specific task faster than a classical computer. So here, programmable superconducting qubits have been used. The system had 54 transmon qubits. Again, such a system, as you can see, needs a very large cooling system, and it's not scalable. So again, because of using superconducting, it cannot be easily scaled up. D-Wave is another company which was the first company, you can say, was the first company to sell their quantum computers. So actually, they are not, if we want to talk strictly, they are not quantum computers. Actually, they are quantum annealers. So it means that they cannot be used to implement universal quantum operations, but that's another admirable work that have been done in this area. So again, superconducting qubits, we can say have been used. Sorry, it is based on quantum annulars, right? But still the size of system, as you can see here, is very large. So it can, compared to previous versions, smaller, but still larger than what can be used by all users. So the past paradigm of quantum computers is built on the structure that you can see here. We have a quantum processor. So this quantum processor includes qubits. They are operated at millikelvin. The controller circuit is at room temperature or 300 Kelvin. High cooling power is needed to maintain this qubit at such a low temperature. And as the number of qubits is increased, we need higher and higher power here to maintain them at a low temperature. It can be very huge. And as the number of qubits increases, we have the issue with this interface lines, right? So what we call it I/O crowding. And the size of such a system would be very large, and the system is not scalable. So here we have a presentation by van der Sijpen in ISSC 2017. So here we have some prediction on the rate of increase in increase in the number of qubits in quantum computers. So on the time, based on current scaling trend, they have seen that they cannot reach on a level that a practical quantum computer can be fabricated. So it is suggested to have some kind of a new approach to quantum computing, right? So it means that based on for example, superconducting qubits, it's not expected to reach a practical quantum computer within 1 decade. So that new approach needs to have a new paradigm to look at quantum computers. Currently, approach that is proposed is to bring controller electronics from room temperature to cryogenic temperature. So as you can see here, here we have quantum processor, right? They are still at very low cryogenic temperatures. The control circuit, which previously was at room temperature, is operating at 1 to 4 Kelvin at cryogenic temperature. So this approach has many advantages because controller is operating at 4 Kelvin. So this issue of I/O coding would be less, but still it exists. The system would be more scalable compared to past approach, but still not too much. For example, we can say that with such an approach, we can roughly achieve up to 100 of qubits, which is still far beyond the level that can be considered as a practical quantum computer. And here you can see a schematic of a cooling system, right? So as you can see, as we go down, right, as we go down to achieve lower temperature, we need first the size of system would be larger, and also we need more of these I/O lines so that communicate with qubits at lower temperature. So all of these are barriers toward scaling of such a system. So the future paradigm of quantum computer that is proposed here, you can see both qubits and their controller circuits are operating at 4 Kelvin. So it means that qubits are operating at higher temperature compared to the original temperature that proposed in previous works. So first of all, you can see that such a change provides opportunity to build a single chip quantum processing unit, right? Because all of the elements, qubits and their controller, are operating at the same temperature, and we don't have that I/O crowding issue because all of this communications, all of these connections would be on the chip, right? So we don't need to have some lines from qubit chip to the outside area, so everything will be on the same chip. Also, because qubits have moved to higher temperature, their cooling power would be lower. So this provides opportunity to build quantum computers as a smaller system, and such a system seems to be scalable because theoretically there is no limit on the number of qubits that we can integrate here. Of course, there are many practical challenges that we should be careful of them. But compared to present approach, we can see that such a paradigm can provide many advantages. So to have a better feeling of the size of the system, we can see a comparison here. In the left, we have qubits which are operating at millikelvin range. So a big cooling system, say in the size of 2-story room, is required here. But if we can increase the temperature of qubits, say to order of 4 Kelvin, we can use very small cooling system. For example, Montana Instruments provides such a small system, which is on the size of like this top PC. So we can see that compared to what we have in a millikelvin temperature qubits, the size of system can be significantly smaller. So in terms of application, such a system can provide many advantages. So just try to imagine that, for example, in a self-driving car, we can use such a system, right? Easily, it can be put inside the car, but such a big system cannot be used for that application, right? So, so the question is that how to build such a system. As we discussed about different type of quantum technologies, semiconductor quantum dots are the approach that are elements that can be used to fabricate quantum computers using CMOS technology. So as a circuit designer, you may ask how I can contribute in quantum computing revolution. So quantum dots are semiconductor nanoscale particles which have spatial, electrical, and optical properties which arise from their quantum mechanical effects. In the past, size of electronic systems were you can say feature size of CMOS technologies were large, and quantum dot could only be fabricated in spatial conditions in labs. But currently, as the CMOS technology has scaled down in nanoscale, for example, you can easily have a 20 nanometer gate length process. So it can be used to implement quantum dots. So that's good motivation to try to implement quantum dot using a standard CMOS process and use it to fabricate quantum computers. So of course, this quantum dots should be operated at cryogenic temperatures, for example, below 4 Kelvin, to maintain their quantum properties. And many new physical phenomena should be understood to properly design such elements. So what is a quantum dot and how we are going to fabricate it using CMOS technology? That's the question that we are going to answer here. So we can see that first, if you remember from a basic problem in quantum physics, you know that when the electron is confined in a quantum well, right, when it has finite wall potential, we can see here, its position, right, or we can say its wave function is a solution of Schrodinger equation. So Schrodinger equation is given here. So the solution of this problem can be found in physics textbooks. So the result is that this electron will have a wave function. That wave function gives us the probability of finding electron in a specific area. So first of all, the energy of electron is on a specific discrete levels. And so here we can, for example, we can see these energy levels, which are dependent on some physical parameters, mass of electron, and the length of this area, length of this cell. And for different quantum numbers, you can see this wave function has different shapes. So you can see that also we have confined electron in the well. There is a probability of finding electron outside the well. So it's like a tunneling in classic point of view, right? So we call it quantum tunneling. So it means that transmission of electron through the wall. That's the essence of making qubits using quantum dots, right? So here you can see a double quantum dot can be used to realize a qubit. Here we have a double quantum dot, right? We have two quantum wells. and 3 barriers that isolate these qubits from their surrounding area. So the quantum state, so the qubit state, so can be defined based on a spin of charge of electrons in quantum dots. For example, we can say that we have 2 quantum wells. If electron is in the left, we say that this qubit is on 0 state. If electron is in the right, we call that the qubit is on 1 state. That's an example based on charge of electrons. Or we can define our quantum state based on a spin of electrons. Depending on if the spin is up or low, we can define quantum state. So this structure has been investigated extensively in the literature. Several methods are developed to initialize, manipulate, and read out the state of these qubits. For example, here we can see that this double quantum dot can be used to realize a charged qubit. So in the charged qubit, we define the qubit state based on presence of qubits in the left or right. So you can see the similarity of this physical structure implemented here and the theoretical structure that we discussed before. By controlling the voltage applied to these gates, we can control the qubit state, and the current of and the state of qubit can be read by checking current from passing from drain and source. Right? I'm not going to go through detail, just briefly overview them. Or we can define the quantum state based on a spin of qubits. Again, you can see another system, right? We have some gates here. So by we can define quantum state depending on spin of electrons in 2 dots. For example, if both of spins are done, we say that this qubit is in 0 state. If in the left is up and in the right is low, we say that the qubit is in 1 state. Right? There are many criteria to how to define this quantum state based on spin of electrons into quantum dots. So there are some other gates that you can see. They can be used to control, for example, the number of electrons here, or interaction between 2 electrons and their spins. And in this way, different type of quantum operations can be defined. There is a fundamental difference between charge and spin qubits. So to change the state of this spin in 2 quantum dots, for a spin-based qubit, we need to have an external magnetic field that we apply to this structure, right? So that can be a source of limitation or sometimes advantage for a spin qubit compared to charge qubits. So here we want to learn what type of qubits can be considered as candidates for CMOS implementation, because still there is no standard implementation of qubits in CMOS technology with comprehensive measurements, because there are some preliminary implementations, but still how qubits can be fabricated in CMOS technology in a standard way and how their performance can be controlled is not exactly known. So here we have looked at some structures that can be used as candidate for CMOS implementation, right? So this structure can be further investigated, how to implement them in CMOS. And what we have seen is that double quantum dot can be a simplified version of double quantum dot can be implemented using CMOS process. For example, here we can see that we can fabricate this structure. This is a quantum dot array, right? Multiple quantum dots are coupled to each other. We have some gate voltage which can be used to control quantum barriers, height of quantum barrier between these different quantum wells. And if we consider them as charged qubits, they can be used to control the flow of electron between these qubits. So here we can see a simulation structure that we have used in COMSOL to simulate properties of this quantum dot array using a specific technology in 22 nanometer FDSOI process. So we talked about FDSOI. FDSOI is a process that recently is becoming popular in different areas for quantum computing applications. It has a buried oxide or box layer, which can provide quantum confinement because, as we can see, it somehow isolates this quantum well from lossy substrate. So it can be considered as an advantage for quantum applications. Also, it can provide opportunity for implementing low power circuit, which is important for controlling the qubit structure. We can review another work here. This work that is recently published using a structure which is very similar to FDSOI process. They have implemented qubit using 2-gate p-type transistor. So one of the quantum dots is operated as a whole qubit, and another one is used for redot, right? And using this very simple structure, you can see it's completely different with classic quantum dots because it has only 2 gates. They have this structure have been able to achieve 16 nanosecond of decoherence time, but at 10 millikelvin. So what we are interested is to see how this structure can be implemented using a standard CMOS technology. What would be its performance at higher temperature like 4 Kelvin? And so that's a brief, I think, a brief review of quantum gates. So brief review of quantum qubit structure. Different type of qubit can be coupled to each other, can have some interactions to fabricate quantum gates. So in the literature, there are 3 main approaches to building quantum gates. So it can be through electrostatic interaction. As you can see, you have 2 double quantum dots. They have some electrostatic interaction with each other, and by controlling that interaction, different type of qubit quantum operations can be realized. In another form, which is called exchange interaction, multiple qubits, here 3 qubits, are grouped to each other to be considered as a multiple quantum dots, are coupled to each other. It can be considered as a qubit, and their interaction is controlled by the length of pulses which are applied to the gates between different qubits. So this is called exchange interaction. Just I briefly introduce this technique, so I'm not going to go through details again. And a more popular structure is an array of coupled quantum dots, right? So as you can see here, we have multiple quantum dots. Their interaction can be controlled by voltage applied to these different gates, and different type of quantum operations can be realized by applying proper timing to different gates of this structure. And we have some CMOS qubit implementations which are reported in literature. So there are some references here, you can refer to them. But still, I cannot find any comprehensive measurements that says that, for example, these are main feature of qubits which have been implemented using different process, and how performance can be improved, or what challenges we should solve here. And we need to do a redot on qubit states. So here we can see, for example, we have different type of redot again. I can have a quantum point contact. What is called quantum point contact is a structure that is integrated along the qubit, and as the quantum state change, the current passing between 2 electrodes can be read by using a redot amplifier to improve sensitivity of these circuits. So that's a technique which is used for charged qubits. For spin qubits, we can use again many techniques. 2 popular techniques are based on single shot redot and based on RF reflectometry. So in single shot redot, we have a magnetic field that is applied, and based on spin of electron here, we can read the passage of an electron from from this dot to this drain or reservoir. So depending on the spin of, either spin is up So no transfer will happen, so we cannot read any current. But when the spin is done, so we can read change in charge. So if this current is properly sensed, we can read the state of qubits. In RF reflectometry, which is again recently introduced, a specific pulse is applied to a specific RF signal is applied to the qubit. So depending on quantum state, this qubit has a state-dependent capacitance, which has different values in 0 and 1 quantum states. So the results would be the result of change in qubit state would be a change in capacitance, which is seen by this resonator, or a frequency shift in its frequency response. For example, if we measure reflection coefficient of the impedance seen from the qubit, we will see that there will be a shift in phase and magnitude of this frequency, which can be used to read the qubit state. For large array of qubit structure, again, we can have different techniques. So two popular approach are crossbar or DRAM-like structure, which is used for dense qubit array. Another approach is a sparse qubit array, which qubits are divided to multiple arrays of sub-arrays, right? So this structure has a lower density, but provides some advantage for controlling and reading of qubit and decreasing coupling, for example, between control line at high frequencies and some other advantage. So here we, so far we have a sense of how qubits can be operated, how they can be coupled to fabricate quantum gates, and how their state can be read by using a specific technique depending on mechanism of their operation. It is based on charge or based on spin of electron. So here we briefly review the activities that we had here in University College Dublin. So the first one is a quantum CMOS. The first one is how to start to have a quantum processing element. So the quantum processing element here is to coupled quantum dot arrays, right, which has an interaction node, and by controlling a spacing between these two nodes, coupling or entanglement of two structures can be controlled. So we have some interfaces to classical and quantum structures, right, or quantum dots and injector or detector circuits, which are used to inject electron into the structure or detect the presence or absence of electron in another quantum dot. So this structure have been simulated in some COMSOL, for example, COMSOL environment to understand its behavior. You can see that the standard FDSOI CMOS process is copied there and try to implement different structures and run these quantum simulations to estimate performance of qubit in this two coupled array structure. And at the end, we have some preliminary implementation of quantum system on chip on 22 nanometer FDSOI process. So we can see that this array of two coupled quantum dot arrays are implemented and integrated with their interface circuits. For example, these quantum dots, they have some quantum barriers between them. So these quantum barriers should be properly controlled by the voltage that is applied to them. This is controlled through D2A converters, DAC circuits, which are integrated on the same chip with quantum dots. And we have some other, for example, detectors here, some quantum point contact, and clock generators, all are on the same chip and implemented as the first step toward the future perspective that I discussed before, to try to implement everything on a single chip. So that's the end of the first part of our presentation. So the main point that I'm going to have as a conclusion is that current CMOS technologies can provide all the elements required to realize quantum computers. But we need to learn how to implement different circuit elements, how to control different qubits, how to evaluate their performance. There are several milestones for future activity in this area, which we can say that they can start from fabrication of high quality qubits in the standard CMOS process and a comprehensive measurement of their properties so that they can be considered as reliable qubits. We need cryogenic model of transistor in CMOS foundry models, which in some cases it needs understanding of new physical phenomena that happening at very low temperatures. For example, at a few Kelvin. Many new physical phenomena are happening there, so they need a proper understanding, and that understanding should be used to implement process design kit for standard CMOS processes. We need in some cases, we need to have simulation tools for quantum classic electronic co-design. For example, we have some quantum structures which they don't have any counterpart in classic electronics. For example, we have quantum point contact. And we need to have some kind of simulators to properly evaluate performance of such classic quantum structures. And at the end, we need to find proper approaches for realization of quantum error correction, because qubits which are implemented on CMOS cannot have very high quality compared to qubits which are especially fabricated using specific technologies in special lab conditions. We need to apply quantum error correction, which thanks to features of CMOS technology, low power and compact area, it can be easily implemented, but we need to have proper approach to have to use them. And so all of these can be used at the end to realize quantum processors, which classic interface electronics, all of them should be integrated on a CMOS as a CMOS system on chip to have a CMOS quantum processor. So that's the end of the first part of presentation. Thank you very much for your attention. So that's the end of our first part. So my colleague, Professor Strazewski, will continue this presentation.
Hello, can you hear me?
Yes, Bogdan, thank you for staying with us. Be welcome, and you may continue. You can share your screen. Can you share your screen, or
to allow me to?
You continue with the.
I think Reza needs to unshare before I start sharing mine.
Yes, sure.
Okay, now I can do it. Okay.
Fine. Great, thank you.
All right, so let me make it big. Okay, very good. So I'm going to, oh, sorry, it went to the presenter's view. How do I go back? All right, so let's use this this view. I'm watching on the other screen the YouTube just to make sure that everything is okay. So I'm going to talk about the second part, continue with Reza's presentation. So hopefully everybody got enough theoretical background into how qubits and how quantum computing works. So I would like to show, basically give you talk like engineer to engineer, IC, specifically IC designer to another IC designer. Let me minimize this and to show how it all started. So when I was in TI, I spent 14 years in TI, 5 years in Alcatel back then. So in TI, I was designing IC chips, and while we were very busy putting into production high volume of radios, wireless radios for GSM and for Bluetooth, at the same time, we were working on future technologies. And one of these technologies were quantum dots. So TI had access, actually TI is the company that invented integrated circuits. So we had the best CMOS technology for low power, for handheld, low leakage operations. Intel had the best technology for high performance microprocessor operations. So we basically had a fantastic opportunity to look for capabilities of process technology to see what can we do to explore the new operations. Let me change the pointer. What is single electron device, right? So single electron device is based on a quantum dot in which you have a very small capacitor. So the name of the game is as low capacitance as possible. And when you add a single electron there, the delta V will be equal to the electronic charge divided by capacitance. That will be on the order of tens or hundreds of millivolts. So you need to minimize the capacitance C in order to maximize the delta V. Right? So if your delta V is very small on the order of microvolts, if you add a single capacitor, you're not going to observe it reliably. So you need to drive C down. And CMOS technology, advanced CMOS technology goes to the rescue. So what we wanted to do is to exploit these single electron devices for things like data converters or high-speed quantizers. There is fantastic range of different applications that we can put in a cell phone. And that could operate at room temperature. So these are more details. So what we have here is we have a polysilicon area over here. Of course, we try to make it as small as possible. And we have an active area underneath diffusion. And notice that there is a little bit of overlap. So if we can control somehow this overlap so that this size is 5 nanometer by 5 nanometer, then we can create a very tiny capacitor on the order of attofarads such that the energy, and you can associate with each capacitor the energy which that electron has. If you want to add another electron, that other electron has to overcome that energy and so on, so that prevents from other electrons to coming and the electron from leaving. If this energy, E squared divided by 2c, is greater than the thermal energy, kT, of the electrons, which is vibrating due to heat, due to room temperature, then you can start observing real quantum single electron effects. So the cross-section of this can be shown over here. So we have a metal which is nearby. There is no tunneling possible. So the tunneling happens between this polysilicon, this red area, and the active area, because it's only separated by a few atomic layers of dielectric. So it's a glass, silicon dioxide, so it's a glass. So the electron's wave function, as Reza has mentioned, can tunnel from one area to another area. And this is schematically shown over here. So we have a capacitor C1, which is a classical capacitor. There is no direct current possible to go through. And then we have a tunneling area. So we started investigating this by reading lots of Likharev's papers. So Likharev is the guy that basically started this revolution a few decades ago. And this is a model. So if you control the voltage potential here on the x-axis, you can control the number of electrons. And this is a discrete operation, right? So some people say that at the fundamental level, world operates as analog circuitry. It's not true. It's all quantized because we are counting the number of electrons, right? We cannot count half an electron. So if we keep on increasing the voltage here to around 0.2 volts, then there will be enough energy to basically overcome this number such that the electron will tunnel from, and this is a ground, but you can think of this as a connection to the Vor source. So this is like a like a bath of electrons, reservoir of electrons that are basically tunneling into this quantum dot. And if you want to get another electron tunnel through, then you need to raise the voltage to around 0.8 volts. So you can see the system is very stable in this case. So this is at absolute temperature. The capacitance is very small, but we can certainly make this, if we are lucky, in advanced nanoscale technology. So what happens when we increase the temperature to 300 Kelvin, room temperature? We don't see these very distinct staircases, but the transition is still distinct. We can actually count the number of electrons, right? And we can, in this case, we still satisfy if capacitance C is a fraction of attofarad, then the potential of an electron is much greater than kT of the thermal energy. So we can observe single electron operation at room temperature. So we wanted to use it for cellular phones. So everything is about capacitance. This is on the x-axis in the attofarad unit. So we can comfortably create capacitors of this size shown over here in the advanced process technology. And what we have energy of the single electron, we have a thermal energy of this, and as long as the energy of the single electron here, this part of the inequality is greater than the thermal energy, then everything is going to be fine. So it's all about capacitor size. So if your capacitor is very small, then you can actually obtain the single electron operation at room temperature. The red is hot. If your capacitance is not so small, then you need to reduce the temperature to 4 Kelvin. The blue color indicates 4 Kelvin. And these are the equivalency, right? So this is equivalence where this inequality becomes equality. So you need to have a certain capacitance at 4 Kelvin temperature in order for these two energies to be the same. But if you lower the capacitance, then you can operate at a much higher temperature. So we try to build it. So the actual structure that we implemented is this differential, right? Previously, I showed you single-ended. So we have a poly, and we have two of these single electron tunneling area. The cross section is shown over here. And what is happening is that this is a typical diagram used to explain single electron transistors. So we have source, drain, the gate in between. So somehow we control the potential over here. And if we raise the voltage, then there will be enough energy for these electrons to basically keep on jumping. And at certain voltage on this battery, we are going to see the steady stream of electrons, which will be shown here as the current. So the higher the voltage, the larger the current or electron tunneling rate. So in 2006, we implemented this structure. We had a PhD from UC Berkeley that was actually working on the tape out during his internship. And we built a bunch of these structures because simply we didn't know what would work, what wouldn't work. So we put this on 45 nanometer CMOS technology, which at that time was the best finest technology available. And here is the TEM, transmission electron micrography photo shown over here. So these are certain structures that we built. And this is zoom in of a structure. Now you can see that this part of the single electron device is actually done properly, but this part is not done properly, and there is no way you can control it. I mean, the wavelength of that process guys were using is orders of magnitude bigger than the feature size that we are trying to do. So you rely on optical proximity correction, and the algorithms are not very good. So you cannot really control it, because any line which is, you know, micrometers away, very, very long distance away, can completely change this scenario. So how do you handle it? Well, you build lots of these structures, right? So the size is very small. These are nanoscopic size. We can build thousands of them, right? And they will occupy only few micrometer square. And then we'll just simply go during the testing, we'll go and find out which ones are correct and which ones are meeting these specifications or not. So we are basically using like a gunshot approach, right? We are building lots of them, and then after they are fabricated, we will pick the ones that are actually meeting the specifications. And we filed 3 patents on the single electron operation during this time. So when we fabricated, we saw, of course, you would measure the V out versus V in, right? So this is a pretty linear kind of characteristics, but when you zoom in into some of these, you will actually see single electron operation. But, you know, because at that time I was in a company, Texas Instruments, TI would not really put an army of engineers to incorporate this in a product unless we have some better proof. And that was not really, that could be a good proof for researchers, but not for industry circuit designers. So we kind of had to abandon it for some time. And then 10 years later, 4 years ago, I got back with my former colleagues from TI, and we reminded ourselves of that research that we did, and then we kind of asked, well, the process technology back then was 45 nanometer. Now we have the 2017 is 7 nanometer, which is like 10 times finer feature size. So why don't we revisit the topics, the ideas that we've been working on previously, and we had it abandoned simply because the technology was not fine enough. So he said, okay, let's do that. And the underlying idea here is that if we can build a qubit or single electron device or quantum dot, whatever, we are talking about some nanoscopic structures in which single electrons are visible, and it meets all the DRC rules, design rule checkers, then we can fabricate millions of billions of times, right? So, it's similar to designing a microprocessor, right? If you can build a single transistor that meets all the rules, manufacturing rules, you can build a microprocessor consisting of these billions of transistors. And this gives us additional benefit of being able to integrate these qubits with transistors on the same die. So this is a holy grail in quantum computing. Basically, we would like to build a chip, single chip quantum processor, quantum computer, which would have qubits at its core, and all the surrounding electronics will be around it, right? And we can have millions of these qubits, just like you can build a microprocessor with billions of transistors. You can build a silicon die with millions of these qubits, right? And all the supporting electronics like drivers, detectors are going to be there on the single chip. And voila, you connect to a PC and you can run your quantum algorithm. So we actually fabricated such a single chip CMOS quantum computer. Size is 3 by 3 millimeter square, and its diagram, this photo is shown over here. So This chip is small enough, and the qubits can operate at 4 Kelvin. So it means that we can go and grab some of the existing gadgets. For example, here is a cryocooler by Montana Instruments, which is the size of a coffee maker, basically, desktop coffee maker, not much bigger than your regular desktop computer. And it maintains 4 Kelvin temperature right in this small box. You can actually, if you have $40, $50, $60,000, you can actually go and purchase tomorrow. Here is the zoom in of this, right? So you basically open this structure, this box, and they even provide you with electrical and optical connections. They also have a space for magnets if you want to deal with spin qubits, right? So they make the whole thing very simple for you, and you put it in a structure on your desktop, and voila, if everything is working fine, you can have a quantum computer on your desktop. So this is the lofty goal of building a quantum computer. So as Reza mentioned, we are using various kinds of qubits. The most fundamental is a charge qubit or position-based qubit. The position charge is because we are using charge of an electron. Our first version of quantum computer doesn't use spin, the second will, but the fundamental versions use only charge. We are identifying, so we are basically have 2 quantum dots, quantum dot left, quantum dot right. There is a barrier in between. Of course, there is a barrier, otherwise the electron will run away, and we can control the barrier in between. And we have a detector, single electron detector, right? So we are detecting if there is a presence or absence of a single electron, and then this detector notifies the rest of the electronic circuitry. So if the detector detects this, then on the block sphere, so block sphere is basically something that mathematically visualizes the state of a qubit. It's going to be here in the South Pole, but if the electron is detected here, then it will be on the North Pole. So this is how it operates, and we are building it using this simple structure of transistors. So these are transistors, right? So here we have a source drain, and then gate, which controls the state of this of the barrier between the two. And if we lower the barrier, then, as Reza mentioned, the wave function of the electron. So the electron is not a cannonball, right? It has a wave characteristic. So the wave function will go from one side to another side, and it will start shuttling, right, due to Rabi, for example, oscillation. So we can control this. So we are exploiting things like superposition, because if we lower the barrier and the electron shuttles from one to another, and when it is middle, meaning that 50% of the wave function is here, 50% here, then if we suddenly raise the barrier, and remember, in this advanced process technology, you can raise the barrier, you can turn on the transistor in a few picoseconds, right? So if we are dealing with 5 nanometer FinFET process, you can turn it on in 2 picoseconds. So 2 picoseconds is a very, very fine time to control the state of the wave functions. So how it works? Well, we basically inject, so we have a structure, right? Complicated structure, but here we are only concentrate in this middle part over here, right? Where basically there is a barrier. With a gate, we control the barrier, and the electron can tunnel from this side to another side. So that's a zoom in version of this. If we lower the barrier, then the electron starts shuttling. And then if we raise the barrier when the wave function is here, then we basically have performed the transfer of electron from one place to another through tunneling, through quantum property. So using this structure, we can implement various quantum gates. So here is an example of a 1 qubit x-axis rotation gate. So here is the block sphere, right? We can rotate, as you can imagine. So when we are injecting the electron will be in this position, right? In this quantum well, or in this position, which is over here, right? Will not be anywhere. So this is a sphere. So we have 3 dimensions, X, Y, Z, but there are, because of constraints, there are only 2 degrees of freedom over here, right? So, so what is happening is we are injecting the electron here, then we are increasing, raising the voltage, and this causes the transfer of the electron to basically rotate from one pole to another pole, and this keeps on going. It has its own frequency, which can be determined by solving the electrostatic potential, solving the Schrödinger equation. So that's one kind of operation. Another 1 qubit gate operation, quantum gate operation, is rotation around the z-axis. So how it is happening, we basically create a little bit of asymmetry by raising the neighborhood gate a little bit to 1 or 2 volts, right? And that will create asymmetry, and this will cause the rotation around the equator. We can also perform rotation around the y-axis by simply providing pulses over here. So the gate, instead of getting a single pulse, constant pulse, it will have a train of pulses. So this way, we are performing, also going from one pole to another pole, but according to different trajectory. So I've mentioned superposition. In order to build a quantum computer, you also need entanglement of 2 electrons, right? So how do we do this? Well, we duplicate the structure. So we have the top qubit, we have a bottom qubit, and somehow the middle quantum dots can be electrostatically entangled. So there can be electrostatic interaction between the 2. I will show you later how it is done. So first, we inject the electron over here into this lower left quantum dot. Then we lower the barrier between them, right, by increasing the voltage. Then there's going to be a tunneling. And then we raise the barrier over here. So half of the wave function is here, half is over here. And then we inject the electron here. And then when we lower the barrier, now there is going to be a electrostatically caused entanglement between these 2 electrons. And this entanglement can be used to realize C0 2-gate functions. So this is how you go step by step by building from simple equivalent of NOT to input AND gates. Of course, quantum computer cannot use AND gates because these are irreversibles, but we are using simple structures such as C0 gates. So let me show you one more time quickly how it goes, right? So we inject the electron in the lower left, then we lower the barrier, there is tunneling, Rabi oscillation, and that lasts, that's greater than 1 nanosecond. Then we raise the barrier, so the tunneling is going to be difficult. There is still going to be tunneling, right, theoretically, but it's not, the rate is going to be very slow. We are injecting the second electron in the top right. We lower the barrier, and now there is electrostatic operation, electrostatic interaction, which basically creates this C0 type of quantum gate operation. So we use these principles to build a quantum computer. So we have many structures on our chip tester. We have actually 2 test chips with these ideas. So one of them is a double V-shaped structure. Remember when I told you there is a staging area? This is the staging area where there is a strong potential for interaction that causes entanglement. So we are injecting the electrons here. So this is what Reza was mentioning. This is a classical part of the IC chip. This is a quantum part. So here is the quantum point contact, which has a transition between the classical and quantum part. So this shaded area is a gate. This one is like a source drain, the diffusion area, but here in this process there is no diffusion because it's FDSOI, fully depleted silicon on insulator. So there is a 5 nanometer silicon film with which is very thin. So the silicon there is intrinsic, right? There's no doping, which certainly helps with trying to get the quantum fidelity as high as possible. So we lower the barrier, right? There's a sea of electrons over here. One of the electrons jump in over here, and then we can move the electron here through the mechanism that I described, and then we can also move the electrons from this side or this side for for CNOT operation. And when we are done, we move electron back to this one of these 4 corners, and the detector, single electron detector, is connected, which detects the presence or absence, right, the results of quantum operation. So the capacitances are quite small, so that it's not a quantum dot yet because there is a metal over here. This is connected to real transistors, right? So if we want to detect the absence or presence of electron, we need to connect to metal, to the other transistor gate, to injector. So the capacitance goes up, but not by much. Still, inject 1 electron can make the difference of 4 millivolts. And that can be detected quite reliably by very simple low power electronics. And the output of the chip, we get 50 millivolts, which is no problem. We can actually observe it with an oscilloscope. So as Reza mentioned, we model the structure over here with using COMSOL. We put all the parameters, so you can see a cross section. And if you know Schrödinger equations, you can actually solve the potential, the energy potential over here. It's quite laborious, takes quite a bit of time going through lots of derivations, but you can actually do it by hand, right? If you want to have exact potential, then you need to use COMSOL, and this takes about 2 weeks in order to solve this potential, right? So this is a position, right? Here we are in the middle. There is one gate, there's another gate, and this is the electrostatic potential, which we can lower and raise in order to create the shuttling of these electrons, right? So we use this model to basically simulate what will happen. So this is a density plot, heat map, which basically shows the density of these electrons when we start moving this. So this is a pulse duration. We are increasing the duration of this pulse that we put on the gate, and then you can see with the pulse duration, there is going to be repetitive patterns. So this points at Rabi oscillations. And we are in the process of making measurements, and indeed we see something which basically resembles this, but it's too early to say that exactly what kind of parameters we are going to extract. So for more information on this, please go to this paper. Unfortunately, Elena could not present it today herself. So what else we do? We also send half of the electrons. For example, we simulate the same structure, right? So this is a zoom in into this structure, right? You can see that when you lower the barrier over here, then the wave function, right? I mean, when you solve the Schrödinger equation, you can see that because this barrier is very high, if the barrier is infinite, the wave function c squared will be 0 at these points. But because the barrier is not infinitely high, is going to be finite over here. So you can see that this is extending, right? And this is non-zero on this side, so there is going to be a certain probability of leakage, of tunneling, right? So especially when you lower this, there is going to be more possibility for tunneling. So we lower the barrier, right? And then the electron from one quantum dot goes to another quantum dot, but it's going to basically keep on shuttling, right? From left to right, from left to right. And this is actually shown over here in the previous plot, right? There is a shuttling between these two. And then when we raise the barrier, there is no shuttling anymore. And there could be shuttling when we lower the barrier here between dot 2 and dot 3. So you can see, so you can basically transport full electrons or part of the electrons from one dot to another. And you have a large number of them. You can say half of the electron will be here and half of the electron will be in the dot number 1000. And you can take it to extreme, and that half of the electron, you can move it to the moon, and it will be one electron in both places, right? This is the principle of superposition, right? That the electron can be in both places at the same time, right? Until you observe it, until you look into this, use your consciousness to inspect it, and then it will instantly collapse. So if half of the electron is somewhere in the moon, half over here, then the moment you measure it, it will be collapse into one place. Okay, so we've built quantum SoC, quantum system on chip, meaning that in the center, we have this quantum structure, as I have mentioned, right? So these are the quantum dots, single electron devices. There is a tunneling in between, there is electrostatic potential, and we have a bunch of capacitive ducts. So these are the ducts, and ducts are needed to, first of all, we need to reset the whole thing. Before we start quantum experiments, we need to reset, make sure that the structure is free from any electrons, right? Otherwise, we might be measuring some spurious memory from the previous event. So we need to perform this reset. So we have a reset device, and the drain and gate are being connected, controlled by the duct, right? Then we are injecting the electrons by simply virtue of this duct. So this duct is called injector, right? It injects, controls the injection of electrons from this sea of gates into this quantum structure. And then the movement of the electrons is done through these imposers. We call them imposers, right? Once the quantum experiment is done, we are moving the electron back and we are detecting the quantum point contact, right? So this is a sea of gates. This is a classical sea of electrons. This is a classical part, but the capacitance here, due to the technology fineness, right, advancement of the technology. Well, when I say advancement of the technology, I'm not talking about some kind of cosmic technology which we don't have. I mean, if you have iPhone or Samsung processor, that technology that they use is actually more advanced that we used in building a quantum computer. So you have this technology in your pocket, basically, right? But the capacitance is so small that a single electron detector can reliably detect the presence because the delta V here is a few millivolts. And then we have a high-speed pulse generator, which basically controls these pulses, not only the amplitude and positioning, but also duration and so on. And pattern generator is like a control center, control and command center for everything. And we are supplying 2 gigahertz clock from externally. We are planning to go on the next tape out for 6 gigahertz clock so that we can have a better resolution. And the communication is done through SPI with external controller operating at room temperature. So the DAC, over here, the CDAC, the details is shown right in the center. So we have a quantum dot, right? We have communication with the external world through this interface, and we have lots of memories, right? So we store the patterns. We don't want to send the signal, which can perturb through the ESD protection during the quantum measurement. We want this to be clean during this measurement, so we store everything in the quantum memory. And we have different library of sequences because we like to go from one sequence to another immediately. So we are basically generating pulse positions, right? But going from VSS to VDD. But we need to control the amplitude, because the amplitude has an exponential effect on the quantum operation. So we need to control precisely this V-pulse amplitude. And also we need to make sure that there is no overshoot, that the pulse shape is very well controlled, similar to what we are doing with wireless communications, right? When we are sending the bits, we need to make sure that they are pulse shaped so that the spectrum doesn't get regrown. And this is how we control the quantum core. And so we have high-speed pulse generator, and the pattern generator actually, as I mentioned, is our command and control. So that's the top view of the quantum SoC and its interface with the FPGA, which is nearby. So we've done some experiments. We published last year in the IEEE Solid State Circuits letters. So you can see how we prepare the experiment by using reset. This is associated with the threshold voltage of this transistor, right? So the transistor, for example, VG is much greater than VD, more than its threshold voltage. Then what we are going to see, the transistor basically is going to be turned on fully, right? So we won't be able to inject single electrons. This is bad. If in this case, if we are in region 4, it means that we haven't turned on this reset transistor, so it's useless. So the transistor is only useful when it is just barely turned on in this sword region. So you can see just a microvolt voltage change can make a difference between detected electron or not detected electron, right? So this points to nothing but single electron behavior. So we fabricated the chip. We have two such tape outs. This is the first tape out. The size is 3 by 3 millimeters square. It's a fully depleted SOI from GlobalFoundries, 22 nanometer. We have 28 of these cores, and then something happened. I don't see the YouTube. Hello?
Robert, yes, you can hear you. We're looking at you.
Okay, I don't see YouTube. It stopped.
YouTube.
Yeah, because I'm observing it on the other screen, just to see that everything is okay.
Let me see. To my screen, I can see the YouTube screen.
Continue then. Okay, sorry for that.
I think so. I think so. No problem.
Okay, so this is a chip. Here is the chip photo, and we put this chip in a flip chip package, flip chip manner, directly on this daughter card. And here is the chip micrograph. You can see we have 28 of these structures. You can see the distance between the balls is 1/4 of a millimeter. So you can see that the quantum stuff is actually very small. It's tiny. The most space is occupied by the classical electronics over here. This is a pattern generator, and this is digital. And on the whole chip, we have something like more than 10 million gates. This is a SoC, digital SoC. So we place this daughter card in the motherboard over here. And we put it right on this cryocooler. So the cryocooler is cooled to 4 Kelvin temperature, which is much higher, orders of magnitude higher than, let's say, Josephson junctions, something that IBM and Google are currently using superconducting, which is a benefit. We can we can make it much cheaper. We can reuse lots of these parts from MRIs, and MRIs are pretty much every major hospital has MRIs, so they are building thousands, millions of them, so we can buy quite inexpensively. So this is our structure, Alice, Mark 1, equal 1. So basically that sample is over here. This is a cryocooler, this is a heat pump, and our computer, FPGA and computer are located over here. So it's a 19-inch rack, quite small, and it has a connection. It has only 4 electrical connections to the outside, right? It has a keyboard, a mouse, screen, and internet, and that's it. And the power supply, obviously, 220 volts. And we communicate through Linux computer over here to make the quantum measurements. Okay, so if you are interested in more details, here are the references. And in conclusion, this is a second conclusion, in addition to what Reza has said. So quantum computing is the next step in the computing revolution. We need quantum computers to basically simulate quantum matter. Like if we want to build quantum drugs, the reason regular computers cannot simulate drugs or materials is because the equations are all known perfectly, no problem. But the classical computer cannot simulate this because the memory and CPU requirements are just exponentially grown, right? So for a very small hydrogen atom or helium atom, we can simulate, but nothing more sophisticated than that, definitely not molecules. So quantum processor operates at the subatomic level, which is nanoscopic levels. CPU is fade and decoherence very quickly. That's why we need to operate at low temperatures. The physics is very well known, but the implementation is far behind, right? So this is similar to what we have in 1950s and 60s, where we had big mainframe computers, and we needed to make the step in order to revolutionize the computing, we had to go to desktop computers. And the key to this goal, lofty goal, is microelectronics, right? We have to capitalize on the hundreds of billions of dollars already invested in the IC infrastructure in order to meet the Moore's law of scaling, right? And we made the first step in a practical quantum computer, which doesn't exist yet. I mean, the quantum computer is basically currently good for example, toy purposes, right? They basically show you that 21 is equal to 7 times 3, which is split into 2 prime numbers, right? They cannot do anything better, more useful than that. And we have shown that if we can operate qubits together, integrated together on the single die in advanced CMOS process, then we can build a quantum computer on a chip. So thank you very much for your attention.
Thank you very much, Bogdan. Thank you very much, Reza, for your very nice presentation. There is a lot of people attending it both on YouTube or on our main room. So I am opening your invited paper for your invited presentation, for questions. If you want to do a question, please just put your question on the chat. So let me wait a second and have a brief look on the YouTube if anyone is writing a question there. If you want to ask a question from YouTube audience, just write a question on the chat there and I can read it for Bogdan or Reza, or both. Okay, so to give people time to type their questions, I start asking one with regards to the qubit and the operation of these circuits at 4 Kelvin. In terms of the device point of view, it is known that fully depleted SOI or SOI at all is prone to have some self-heating. So could you please comment on how challenging is the pulse width to not generate some local heating that may let the qubit or the signal electron transistor to a failure because the heating of the system, because of the self-heating. I mean.
Well, so to solve this problem, to solve this problem, we just need to make sure that the electronics consumes very low power, right? It's very well known that silicon at 4 Kelvin is a very good insulator, unlike room temperature. So it's difficult to extract the heat. So you need to manage it, right? Put temperature sensors, but you also need to make sure that you don't generate the heat. So we have CDACs, capacitive DACs, which consume very little power, right? So if you want to access quantum dot using spin technologies, right? So this is currently leading by other groups. You need to burn at least 20 or 30, 40 milliwatts per qubit, right? 20, 30 milliwatts per qubit. Here, we don't need to modulate the signal. There is no carrier, right? There is no carrier associated with the qubit. The qubit access is done using baseband signal. So we send the signal. There is no carrier modulation. We simply send one signal and that's it. The second pulse is not needed unless for other operation. So the whole thing can consume orders like 3-4 orders of magnitude lower power, lower energy than operating the spin qubit. So we think by going to position-based charge qubits and also using spin qubits, but rarely is needed for longer memory, is the key in order to ensure this. Okay. So it's a big engineering problem.
Great. Okay. So there's a question from Dr. Roberto Panecucci here at the chat. How reproducible does the barrier control need to be to ensure the proper interaction for entanglement?
So the barrier needs to be properly controlled. So as you can see, the tunneling depends on the voltage, right? So, so you need to control this voltage with the resolution of microvolts, basically. But it's not a problem because we have high resolution CDACs, right? So we have high resolution CDACs. They are very low power. They don't have to be linear as long as they are monotonic. It's all fine. We can control this position. So here I need to point out to this measurement, so you can see that we need to operate in this, we call it sword region. If your voltage, for example, is a little bit higher or lower, then you might have difficulty. You're not going there. And when you look at this particular this site, there are 4 sides to this quantum core. In each site will have a slightly different position, right? And voila, we see this because this is something similar to mismatches, right? And we know that at cryogenic temperature, mismatch of the MOS structures is much worse, like 2-3 times worse than at room temperature. So it means that we need to calibrate each one. But the good thing is that this calibration is only for the process mismatch, right? The let's say the edge roughness. So you don't need to repeat it over time or temperature. If you change the temperature, for example, from we typically operate our cooling machine at 3.6 Kelvin. In the US, we have 2 locations. We have Silicon Valley, the companies in Silicon Valley and in the University College Dublin. The temperature that these guys obtain in Silicon Valley is 3.2 Kelvin. So we were kind of scratching our heads trying to figure out why is the difference, and the difference is 60 hertz versus 50 hertz, right? 60 hertz basically allows your engine to run faster, so you can extract more heat. You can get lower temperature. So you need to calibrate for this. But when you look at the conventional commercial quantum computer that you can get from IBM or Google, you also need to calibrate all of this. Every time you perform the heat cycle, the power-up cycle, right? You need to spend, the technicians need to spend several days calibrating these things. So calibration would be necessary, right? And calibration is actually something that myself and my colleagues are very comfortable with, because we build our transceivers, radios, synthesizer using lots of calibrations, right? Which are basically done most of the time in a self-calibrating manner.
Okay. So we are a bit behind the scheduling. So I would like to finalize thanking you very much, Robert and Reza, for your very nice presentation. I don't see any other question at the chat. So with that, I thank you very much on behalf of both societies and both conferences, SBMicro, SBCCI, and the other remaining conferences in these Chip in the Fields 2021. And okay, so thank you very much for having our this very nice presentation, for giving this very nice presentation to us. So I'm going to interrupt your screen. I will just do a very brief announcement. So the next presentation is, so I hope you are now looking at my screen. Yes. So we are moving to this presentation, but I think we can do a very short interval just to let the people stretch a bit their legs and so on. So let's say in 5 minutes we are back for the next presentation, heterogeneous, last and final presentation, heterogeneous integration for AI architectures. Dr. Mukhtar Farouk, I've seen her name in the list of participants, so she's already with us. And in 5 minutes, we'll be back to start the last one, okay? So thank you very much and see you soon.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things, and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
Okay, I hope you all listen me. Okay, is it fine? Can you hear me? Yes. Oh, okay. So first of all, let me welcome you, Mukta, for your nice presentation. Thank you for coming. It is a pleasure to us to receive you in this mini-colloquium. So for those who are joining us now, let me just position you where we are. So here we are going to the last presentation of the 2021 IEEE Electron Devices Society Brazil Virtual Mini-colloquium. In this presentation will be heterogeneous integration for AI architectures. It will be a presentation by Dr. Mukta Farooq from IBM Research in the United States. So Mukta, let me just know, do you prefer that I run your presentation as we discussed yesterday? Yeah, okay, fine. And let me just say a few words about Mukta. He's joined us for the presentation, and then for the Q&A session, she will be with us to answer the questions you may have. So just a few words about Mukta. Just a second, please. Yes. So Dr. Mukta Farooq is a distinction research staff member at IBM Research. She's an IEEE fellow and IEEE EDS distinction lecturer and a distinguished alumna at Indian Institute of Technology in Bombay, India. Dr. Farooq is a materials scientist with expertise in heterogeneous and 3D integration, CMOS back-end of line, and chip package interaction. Dr. Farooq received the IBM Outstanding Technical Achievement Award for the semiconductor industry's first high-volume T3 logic wafer. She granted 222 US patents and numerous publications. She's an IBM Lifetime Master Inventor and an IBM Academy of Technology member. She received her bachelor degree in Indian Institute of Technology in Bombay and the master degree from Northwestern University and her PhD from Rensselaer Polytechnic Institute. So by saying this, it is my pleasure to welcome her in our mini-colloquium. I'm going to, so the presentation you follow like this. I'm going to share you the screen that Mukta gently provided us with the sound and the video. Yeah, so let me just ask if you are looking. Are you looking at my screen now? Let me just be sure. Yeah. Oh, thank you. So with that, let me come back to the first slide, and then I will run the presentation, and then oh, time to start.
I'm not able to hear any sound, Marcelo.
Let me just double check then. Are you not hearing anything?
Correct.
That's right?
No, no sound.
sharing my.
If you prefer I run it, I could try and do that. I do have a connection. We don't have an issue right now.
Oh, if you prefer, we can do that. Okay. So I'm passing the ball to you because it should be okay.
It should be. Yeah. Let me open the deck. Give me 10
So let me
seconds.
then stop the sharing. I will pass the ball to you then.
Okay.
I'm very sorry. I don't know what's happening.
Yeah, for some reason there was no sound, but let me start. Okay.
So can you share your screen now?
I can share it. Yes, I have to just go in and say start sharing.
Yeah.
Share screen.
Let me double check because you cannot, I cannot see your, screen yet.
Okay. Trying to get to the.
Otherwise, I can restart the presentation from here and then.
I think I can share it. Let's see if this works.
Oh, no. Yes. Now yes. Now
okay.
It can.
And so, tell me if you can hear the sound as well.
You have to put in presentation mode, I think. No, there is some. So let me see where we have to share the sound. Because we have the same problem, then you are having the same problem than me.
I see.
So let me see if the guys from the backstage, if they can give us some guide.
I think it's asked to unmute. In that chip in the fields, it's asked to unmute. I have asked. I don't know if they can do that.
We are unable to share your own audio, but when you choose to share your screen, you must pick the share sound option.
I see.
So there are two moments in which you can do that. Either it's in the moment you share, you have a checkbox, share sound, or else after you started sharing, you can go on the toolbar.
Okay.
Then you hit the 3 buttons and then you see a bunch of options, and one of those options is share sound.
Got it. I see it.
Yeah.
So let's redo this and see if this works. Okay. I'm going to try again. Good afternoon. I am
now it works.
And today I'm going to be talking about heterogeneous integration for AI architecture. The outline of the talk is as follows. I'll start with an introduction to AI, discuss what the AI hardware requirements are, and then we'll talk a little bit about classical packaging and how this differs from heterogeneous integration, with a specific look at 3D TSV integration. Then we'll look at the path forward with HI and end with some concluding remarks. So, introduction to AI and AI hardware requirements. There has been a veritable explosion in data over the last 15 years or so. Some of these examples are image processing and object detection as in autonomous cars. So how does There has been a veritable explosion in data over the last 15 years or so. Some of these examples are image processing and object detection as in autonomous cars, natural language processing, facial recognition, medical image analysis, sentiment analysis, and so on. But what's very interesting about this explosion in data is that most of it has been in unstructured data. And while our traditional computers and systems were able to grapple and comprehend structured data, the requirements to understand and use unstructured data are very different. So how does all this data affect AI? For that, we need to take a look at training. Every intelligence has to be taught. We may be born with the capacity, but we would be nowhere without the training, right? A human brain, even though we are genetically primed to categorize things, still needs many examples to get trained before it can distinguish between objects. I remember when my daughter was around a year old, she had a toy where objects had to be categorized and selected before they could be inserted into the right slots. And she soon learned that a square peg does not fit in a round hole. It took several tries when she first started. But once she had mastered the data set, she could finish the puzzle in a few seconds. That's the one-year-old human brain. AI is different. Yet, part of the AI breakthrough lies in the tremendous stockpile of collected data about our world, which provides the big data for training that AI needs. So training can be achieved with the use of big data. Now let's discuss inference. Take the relatively simple task for a human brain to recognize that a face is a face. This inference comes to us instinctively, immediately, unerringly. But for a computer to achieve that, it took decades of computer scientists working to solve that problem. The key was to organize neural nets into stacked layers. When a group of bits in a neural net is found to trigger a pattern, the image of an eye, for instance, then that result is moved up to another level in the neural net for further parsing. The next level might group two eyes together, and so on. It can take many millions of these nodes, each one producing a calculation, feeding others around it, stacked up to 15 levels high to recognize a human face. So inference in AI needs better and better algorithms. And now on to deep learning, which is the first and foremost objective of AI. Deep learning is a subset of thinking. You could say it is a first step towards thinking. And thinking is an inherently parallel process, certainly in the natural world, requiring billions of neurons firing simultaneously within our cortex, our brain. So to build a neural network, which is the heart and soul of AI software, also requires many different processes to take place simultaneously. Each node of a neural network loosely imitates a neuron in the brain, mutually interacting with its neighbors to make sense of the signals it receives. To identify an image, it needs to see every pixel in the context of all the pixels around it, which really translates to intensely parallel computation. So to achieve deep learning in AI, what we need is intensely parallel computation. However, the training for deep neural networks comes at a huge computational cost. AI models are continuously getting larger. This leads to the voracious consumption of several petaflops per day for just AI training. As you can see in the graph here, this is doubling every 3.5 months. Clearly, this is unsustainable without significant hardware and software innovation, especially in the face of stalled scaling. So this brings us to heterogeneous integration, wherein we integrate separately manufactured components with advanced packaging methods and high-density interconnects to achieve superior functionality and better operating characteristics. Now, two principal ways in which HI can be leveraged are as follows. Number one, node optimization, wherein we can design, compute, memory, and I/O in different nodes for cost and technology optimization, and then bring them together in a final solution. The second is die disaggregation. So we know that smaller dies have higher yield, so breaking up a large die into smaller components will give us a cost benefit. But the other benefit is that we gain modularity, where we can flexibly compose optimally sized systems for any given application. So on the left is the example for node optimization, which is AMD's EPYC 2 processor. Here, the central die is a 14 nanometer IO die, whereas the CPUs surrounding it are in the more advanced technology node of 7 nanometers. On the right side, we see an example of die disaggregation. This is NVIDIA's research demonstration where a GPU was broken up into a 36 chiplet inference engine where chips were connected by low power, high bandwidth interfaces. So the key requirements for AI hardware are compute, memory, and connectivity. So deep learning algorithms are particularly amenable to hardware acceleration. On the training side of the coin, work is often parallelized among multiple accelerators. Even so, large models may take days to train. So let's look at BERT-Large, which is a natural language processing model with more than 345 million parameters. The original paper said that this took 4 days using a cluster of 64 TPU chips. NVIDIA then trained BERT-Large from scratch using 1,472 V100 GPUs, and this they accomplished in under 47 minutes. For the inference, similar operations as training do occur, but they have fewer operations and fewer memory requirements. And typically, one processor is sufficient. Now let's look at memory requirements. So deep learning has very demanding memory requirements, both for bandwidth and capacity. So the memory bandwidth has to increase in proportion to compute gains, otherwise the system can become imbalanced, leading to low utilization. Similarly, processors need fast access to large models, so the capacity must be commensurate. On the right side is a schematic of an HBM stack on a logic die, which is then connected to a GPU through an interposer, and then these are all on a packaging substrate. In such a configuration, it has been found that sustained performance of accelerators is often far below peak due to insufficient memory bandwidth. So here is a study that was done to understand the trade-offs of improving compute versus improving memory bandwidth. So a multi-chip network of AI accelerators training ResNet 50 was used, and system performance improvement was then measured as a function of either improving compute only, memory bandwidth only, or increasing both compute and memory bandwidth. And it was seen that when compute was increased, there was some level of improvement, but definitely a much bigger level of improvement was observed when memory bandwidth only was increased. Of course, the best solution was to increase both, but fundamentally, memory bandwidth is the one that gives us the best return on investment in terms of system performance improvement. Let's take a look at the connectivity requirements for AI. So remember, AI training can be parallelized among many chips or workers. What this means is that each worker takes a subset of the training data, determines the changes to the model, and then communicates with a large number of parallel workers. So in a large multi-chip training system, communication between workers can dominate the training time. And this is really important to note because it is one of the linchpins for AI hardware requirements. So how can heterogeneous integration help maintain the upward trend? By delivering in the three key areas: compute, by enabling dense compute modules; memory, by delivering capacity, such as by doing 3D stacking or emerging memories for large model storage; and bandwidth, by ensuring high bandwidth to match gains in compute throughput. And then finally, by enabling connectivity. So energy efficient interfaces for high bandwidth connectivity between compute elements is a key part of these requirements. Now let's take a look at classical packaging, heterogeneous integration, and particularly 3D TSV integration. So in classical packaging, there is conventional discrete chip on package where you have individually packaged components on a board, a system on chip style package where an integrated circuit combines all the key components of a computer or a full system in one single chip, and that is packaged as a very single, very expensive die. The third type is a traditional system in package where a number of integrated circuits are enclosed in a single module, and together this can perform the functions of a full system. The die can be sourced from various suppliers, and you can create a cost-effective solution such as found in mobile phones. However, the issue here is that classical packaging does not deliver the key requirements of AI compute, which are high compute density, high bandwidth access to memory, and chip-to-chip connectivity with low latency, low energy. So let's now talk about packaging versus CMOS scaling. From 1970 to 2016, although the number of C4s increased dramatically from about 16 to over 10,000 on a single die, there has been only a very gradual and very modest improvement in the C4 size and pitch. But in the same 50-year time frame, there has been a seismic shift in the minimum feature on the chip, going from about 10 microns down to a few nanometers. So why didn't the packaging elements keep up with the silicon side? This question comes up quite often, but there are some very solid reasons. There's the cost of development, introduction of new materials, yield and manufacturing cost, especially given how late in the process the C4s occur, and the part is already very expensive. But most importantly, there was no compelling overarching reason to do it, which meant that as long as the high-speed, high-bandwidth communication was happening in the silicon, and the C4s were only responsible for maybe a small amount of performance hit, there was no reason, there was no driving force to change the paradigm. Enter the brave new world of high-performance computing, especially with different requirements for the cloud and for AI. Now, the high performance coupled with the cost advantage of using disparate nodes for optimizing cost and performance changed the paradigm. So an SoC was now split into multiple die, GPUs, HBMs, other memory. Suddenly, transmissions between the chips of an erstwhile SoC became a limiting factor. And now the demand for memory, lots of it, in all three directions, skyrocketed. So rapid access to memory and high bandwidth have become the non-negotiables in system requirements, especially for AI workloads. And so this has really become a driver to truly change C4 interconnect and packaging. Today's HBMs are bumped routinely at 55 micron bump pitch. Copper-copper bonding can go down dramatically in pitch, below 10 microns, and also deliver better thermal and electrical performance. So what's the catch? So the organic packaging substrates are generally not capable of meeting coplanarity requirements demanded by copper-copper pad joining. Recall that when you do C4, there's a full melt interconnect. It allows for slop between center and edge. And since they self-align, the final assembly holds well together, even if some C4s may stretch and others bulge. No doubt, organic laminate technology, as in standard laminates, has improved greatly. But is it enough in its current form? No. So how do we solve the problem of getting fine pitches and superior bonding in packaging? And the answer is we use other methods to circumvent the problem. This is the heart and soul of heterogeneous integration. So now let's talk of HI options. These can be classified as three primary approaches. Number one is the interposer, which can be silicon or organic. Number two is back-end of line wiring built on silicon. If it stays on silicon in its final format, that's a silicon bridge. If it gets moved and transferred to something else, that's fan-out wafer-level packaging. And the last one is 3D integration, where the active dies have TSVs. Now that's in a separate color because in that choice, in that option, we're actually changing the dies themselves that need to be connected. The TSV is integrated inside those dies. In all the other options, which are marked in blue, the dies themselves don't change. It's just the way that we connect them to each other that's different. So let's start with the silicon interposer, which really has been the workhorse in terms of getting fine pitch connectivity between chips for many, many years. A passive silicon platform joined to a packaging substrate, which enables high bandwidth, low latency surface connections among die, is really the definition of a silicon interposer. And here, power delivery is achieved using through silicon vias. In an organic interposer, what's typically done is a set of thin films is joined to a traditional laminate substrate. This enables localized areas of high bandwidth, low latency surface connections among chips. Power delivery is through interconnections to the package, not using through silicon vias as in the silicon interposer. Now let's look at interposers and challenges for AI. In a silicon interposer, there is limited scalability due to its size limitation. There are warpage issues, and these get worse as size increases. Remember, silicon has a CTE, coefficient of thermal expansion, of 2.6 parts per million per degree Celsius, whereas the laminate to which it's attached is closer to 15. Also, insertion losses are high, which is a materials property, and this can degrade system performance at high frequency and restrict trace lengths between die. Plus, there are higher costs associated with fab processing because through silicon vias are made in the fab. An organic interposer is definitely more scalable than a silicon interposer. Also, due to its materials properties, it has lower insertion losses, so longer trace lengths between die are possible. And finally, there is a lower cost compared to fab TSV processing, but there is no doubt an additional cost compared to a standard laminate. So in the net, silicon interposers are size limited, have TSV costs and higher insertion losses. Organic interposers have lower insertion losses, can deliver sufficient fine wiring connectivity for many AI applications. And in the lower right are examples of two organic interposers, one by Shinko, the other one by Kyocera, both published in 2014. What about back-end-of-line silicon-built wiring options? First among these is the silicon bridge, which is essentially a passive silicon die with back-end-of-line wiring that enables high bandwidth connections among CPU, GPU, memory die, the latter group obtaining power delivery through a standard packaging substrate. The bridge die may be either on the surface, somewhat entrenched into the surface of the substrate, or it could be completely submerged inside the packaging substrate. For fan-out wafer level process, what we are looking at is a set of redistribution wiring layers that on one surface will connect CPU, GPU, memory die, which are typically encased in an organic mold compound, and on the other surface, opposing surface, connect using C4s to a packaging substrate from which power is drawn. So now let's take a look at some silicon bridges and AI challenges from industry. On the left-hand side is the AMD GPU HBM2 and Intel CPU, and these are connected with an EMIB bridge, which is an embedded bridge that joins the two components. On the lower side of this picture, you'll see the Intel Agilex with multiple bridges joining FPGA to HBM, CPU, and other dies. And on the surface, at least, it looks like there are 5 bridges in this configuration. In the middle of the page is the example of IMEC's flip chip on fan-out wafer level package. This package connects 7 chips. There's a wide I/O DRAM, flash memory, logic, 2 through package via chips, and 2 silicon bridge chips. And this enables high chip-to-chip interconnect densities with 20 micron bump pitch. But in the net, silicon bridges can provide the connection and bandwidth needed for GPU to HBM, but they're not without challenges. So number one, as connectivity needs increase, it starts driving multiple bridges. So at what point is it better to have another solution or an additional solution? And number two, what are the key test points and how does one ensure known good die? Because as these components get more expensive, the known good die problem becomes an imperative. So fan-out wafer level process and AI challenges are as follows. There are 2 examples shown on this page. There is the Amkor Swift structure, overmolded and exposed die. And on the right side is a chip first face up and then a chip last face down structure shown from TSMC's info. So the fan-out wafer level packaging definitely has versatility and is seen in applications such as mobile phones. But in the AI space, there are challenges. So large die sizes for CPU, GPU can create a larger footprint, leading to issues of warpage and handling. Memory stacks and accelerators may have different heights. Now, this can become a problem if you're going to use mold, because where do you stop the mold grinding? And if you stop it well above one of the dies, then how do you ensure that that die will also have an effective thermal solution, because there's going to be a layer of mold left before we get to the thermal solution, the thermal interface material and the heat sink. Plus, there are testability and known good die issues. Now, this is a very interesting example from industry called the fan-out embedded bridge, clearly a combination of those 2 heterogeneous integration options. This was published by SPIL at last year's ECTC. The process is as follows. They start with a glass substrate on which the first RDL layer is built. Then copper posts are plated and bridge die are joined. And then this is further encased in a molding compound, which is ground down. And in this stage, there are micropads and RDL2 that are further deposited on the wafer. Then the logic and memory die here are attached to the available micropads. And then this wafer is reversed. And at this point, the glass wafer that originally held it is released. Remember, now you have a mold compound on the other side. So there is stability for this entire structure. And once that's done, dicing can occur so that these C4 bumped entities can then be joined onto the final laminate substrate. So what's interesting is that if you look at the cross section, there are multiple items within this structure. So on top is the HBM, which is then connected with these fine HBM connections and then underfilled. There are 3 redistribution levels. Then there are copper posts alongside the bridge die, which connect to the bottom, which is to the substrate. And again, there are C4 connections here, and these are also encased in underfill. The 5 silicon dies and the 4 bridges are as follows in terms of dimensions. The bridges themselves have a line space of 0.8 microns each and a micro bump pitch of 40 microns, which is fairly aggressive. And then for the RDL, the line space is 2 microns each for signal and 10 microns each for power and ground. So this method, using a fairly large laminate, 72 by 75 square millimeters, with an 8-to-8 configuration plus a stiffener ring, is thus enabling a fairly complex method by which SOCs and HBMs can be allowed to communicate with very good bandwidth and very good interchip connectivity. Now, this is an example from the industry of using interposers, fan-out, and fine pitch, presented by TSMC at ECTC 2020. In this instance, what they're doing is combining the front-end 3D, which is SOIC, which is their improved version of system on chip, and the COW, which is the chip on wafer method, along with the back end with 3D, which is the integrated fan-out redistribution line-based method, to create extremely fine ways of joining memory and logic die as seen in the schematic below. So here they're saying that this immersion in memory computing method integrates multi-core logic and memory with the closest proximity for L to L and L to M for AI. IMMC is an ultimate near memory computing which is complementary to back-end heterogeneous integration using the optimized method shown here. What's important to note is that they have moved from the regime of flip chip, which uses solder, to solderless, which uses copper bumps. When you do that, you can improve the density of the bump counts from, something like 1,000 to approaching 1,000,000 counts per millimeter square. So this can be achieved, but it comes at a very definite cost of being able to do this only silicon to silicon. You have to remember that when joining occurs between silicon die and organic substrates, typically a flip chip is a method that has been shown to work. Perhaps a copper pillar with solder at its tip also works. But as the pitch starts getting very fine, the solderless methods are not going to work so well on laminates because of their inherent warpage. I'm sure more development is going to be done, and perhaps we can see more breakthroughs in the future. But as of now, these extremely fine pitch solderless bump methods are generally restricted to silicon joining. Now let's take a look at the 2.xd HI methods and comparison of attributes. So very quickly, the silicon interposer on the left and the embedded bridge on the extreme right are the two silicon options. And while the interposer has TSVs, the bridge does not. A minimum line space of 0.4 and 0.4 microns is available in both silicon options. Connections per layer are 800 or more, and this has been demonstrated very well down to 55 and even a 40 micron pitch. In the middle are the organic options. So we have the organic interposer and the fan-out wafer level package. Here, the minimum line space is not quite what the silicon can achieve. It is in the range of 2 microns lines and 2 micron spaces. And the connections per layer are clearly far less, only about a fourth of what silicon can achieve, close to about 200 millimeters per layer. The pitch has been demonstrated, again, down to 30 or 40 microns microbump. So that's comparable in both these cases. So for silicon bridge and fan-out wafer level process, there are some very specific test challenges which we should take a look at. So a key requirement for AI is the ability to test die during assembly to ensure a high-yielding final solution. So for silicon bridge, a wafer level test to ensure dice sort pick of known good die is important. But then you need sub-assembly testing followed by fully assembled testing for surface bridge die and fully assembled testing of embedded bridge die. For fan-out wafer level packaging, there has to be a wafer level test to ensure dice sort pick of known good die. And typically, because the redistribution layer is built after chip attach, there is no intermediate test. There is only going to be full assembly testing after chip attach. Net, high assembly yield is required to enable both the bridge and the fan-out solutions. And this is not a trivial problem in terms of its implementation. So now we come to 3D integration for AI. 3D integration is extremely well suited for AI compute. TSVs enable communication in the Z direction without the need for long XY travel. It enables tight coupling with very high bandwidth between accelerator and memory, and it's further enhanced by copper-copper or copper hybrid bonding with very tight pitches of only a few microns. For stacking order considerations, what we need to know is that if you have the accelerator on top, you can cool easily, but power delivery is a little more difficult. And there may be IR drops that have to be considered and discussed in terms of its use. In a lower power accelerator case, you can definitely have that on the lower side, but just remember that you'll have TSVs through the accelerator, so there could be a TSV area penalty, as well as a potential TSV impact, which need to be evaluated. Now we come to TSV integration options. So without going into every detail, it's important to note that VIA first is where the VRs are made well before the CMOS process starts. VIA middle is in the middle of the backend at some point, and VIA last is made after the backend is completed. So in industry, 3D integration is most often practiced using a VIA middle process. In such an instance, the wafer is processed through some part of the backend, TSVs are introduced, and then the wafer is terminated with the underbump metallurgy. Then we go to the wafer grind side processing, where a temporary carrier is attached to the wafer and a series of operations, including a mechanical grind and polish, followed by silicon dry, passivation using hard dielectrics, then a chem mech polish to expose the TSV, and finally a pad deposition to capture the TSV are performed. This is a standard 3D grind side process, which enables us to gain access to the TSVs from the other side of the wafer. 3D integration considerations for AI. We know AI compute requires accelerator memory connections to have high bandwidth, low latency, low energy. So at what level should these components be connected to achieve this objective? So connections between the actual transistors, the FETs on accelerators and memory is not required. So at this point, there doesn't seem to be any major driver for monolithic 3D. How about looking at them on a wafer-to-wafer scale? One that needs same-sized die on both sides of the wafers, and that we believe is very restrictive. Also, the wafer-to-wafer needs high yield, so it really suits memory only, given the current situation. The third one is a connection between accelerator and memory at very tight pitch. Now, this is eminently achievable using 3D stacked ICs, either in a die-to-die or a die-to-wafer format. And as you can see on the little table on the right, the 1 and 2 are not as suited to this method of integration as is number 3, where there is die stacking to give us this tremendous accelerator memory connection with high bandwidth, low latency, and low energy. Okay, let's talk about 3D integration test flow. So as you can see in the process flow there, both kinds of wafers may be tested at the end of the build, wafer final test, but typically there will also be a grind side test on the TSVs or some specific macro sets within a 3D wafer, and then the final known good die can be used for assembly and final module test. Particularly in instances like die to wafer, it is really critical to identify known good die before final assembly. Now let's look at some 3D integration industry cases. On the left is the TSMC wafer level thermocompression bonding, which is used for their system on IC 3D stacking, which could be either a face-to-face or a face-to-back bond. The TSVs here are 5 microns in diameter, 40 micron depth at a 10 micron pitch, and the TSVs are bonded to 7 micron pads. On the right side is the Intel Foveros configuration, which has a 22 nanometer IO die with TSVs, a 10 nanometer compute face-to-face die, and a memory connection using a package-on-package type connection. And below that is Intel's ODI, omnidirectional interconnect, showing a number of different types of connections, including embedded bridges, TSVs, and various configurations with the HBM DRAM die. So the 3D integration industry examples are as follows. We have the stacked main memory using Micron's hybrid memory cube technology, which shows that there is much to be gained in terms of efficiency of signals and power when using this configuration with all higher power logic functions localized to a single logic chip on the bottom and the DRAM stack sitting atop it. On the lower left here is IBM's 45 nanometer 3D die stack on laminate, where a face-to-back die was attached with fine pitch lead-free C4 to the bottom die. And then on the right side here is another example with IBM's 32 nanometer 3D die stack on laminate, having a face-to-face attached with lead-free C4. And on the top, you'll see the panoramic view of the lidded module. The other thing to keep in mind for HI combinations is that various options can work together. You can have a 3D die stack, you can have an embedded or a surface bridge, you can have fan-out wafer processing to enable connectivity between various dies and chiplets, and you can also have a high-density organic interposer to achieve the same end. One important thing to remember is that adding a TSV, as we said early on, actually impacts the chip which is being used for the connection. So this is not just the same as the other methods. And so the introduction of the TSV has to be considered very carefully. In a logic die, it's important to have impact assessments of copper TSVs on the FEOL and the BEOL as built and post-reliability stressing, and wafer thinning on devices at various proximities to the TSV. We've done this in the past, and a summary of our 32 nanometer 3D logic die evaluations has been published previously at IRPS 2015. We found that there were excellent reliability results both in front-end of line testing when compared to pure 2D control die without TSV, and similarly in the back end, we found no issues with reliability. So now we come to the last section, which is the path forward with HI, and then the concluding remarks. So how can HI help maintain the upward trend? By enabling all the key requirements of AI hardware. So the path forward for 3D memory connectivity is to make sure that our solutions enable high bandwidth. You know, in our analyses of the 2.xt solutions, it is possible to get hundreds of gigabyte per second bandwidth. And in 3D, it changes to a few terabytes. So therefore, it is definitely a different level of benefit that 3D can confer to HI configurations. Equally as important is that the link energy per bit in a 2.xd solution is typically greater than 1 picojoule per bit, and it is far less than 1 picojoule per bit, just because of the distances and the amount of traversing that one has to do in most 2.xd solutions versus a 3D solution. So we know that the desired state is a 3D memory accelerator stack, but if it's a high power stack, we are aware that having the accelerator on top is something that is difficult from the viewpoint of power delivery. And if you have it on the bottom, this is difficult in terms of the thermal solution. So these have to be considered very carefully before a final option is selected. The path forward for AI memory and packaging is also important. We know that the silicon interposer, which has been the workhorse to date, has a relatively high cost and limited scalability, but the emerging technologies for 2.xd can step in where the silicon interposer may not suffice. This includes bridges, fan-out wafer level processing, and high-density organic substrates. And of course, there is the 3D integration option in addition to the 2.xd options. So for the heterogeneous integration platform for AI, what's needed are the following. Interfaces between components that have high bandwidth, which are energy efficient, which are area efficient, can't disregard area, and where we have standards to allow connectivity between a wide variety of components. Because the entire idea behind node optimization and die disaggregation is to enable us to source components from various places. So having standards to allow this connectivity is actually a vital and a very key component of any HI platform for AI. And then we have the various HI technologies which can help us bring this together. Finally, in the concluding remarks, I would like to say that AI workloads are driving heterogeneous integration solutions to add ever-increasing compute demands. High compute density platforms with diversity of components, and then high bandwidth, low energy interfaces between components, both accelerator memory and accelerator to other accelerators. The building blocks of HI include high density silicon or organic interposers, silicon bridges, fan-out redistribution levels, and especially 3D integration using TSVs. So we have quite the toolbox at our hands, and it is our hope and definitely our plan to use these tools in the most optimal way possible to execute the various AI architectures to enable us to get the best system performance. Thank you for your attention, and also my sincere thanks to Marcelo Pavanello for the invitation to speak at the Brazil EDS MQ today.
Thank you very much, Mukta, for this nice presentation. It is very educative for us to listen all these features of heterogeneous integration. And well, let me just check if the audience has some questions already. Let me have a look on the YouTube as well. Okay. I remember people in YouTube, if you want to ask a question, just type it on the chat and I can read the question for Mukta if needed. But let me try first. I have some few ones, but I would like to listen your opinion about the limit for heterogeneous integration. I mean, in a certain amount or in a certain extent, I imagine that depending on the system delay, the delay provoked by the heterogeneous integration will affect the overall system performance. And then you have to come back to a unique solution using a monolithic system or a monolithic part, and then integrating it to the remaining part of the system because of the delay. So can you foresee something about the limit for heterogeneous integration, considering the size, the feature size of a transistor is in the order of 10 nanometers or so?
So, you know, the traditional argument for, and I'm going to say monolithic to kind of encompass the SoC, right, system on chip method. The argument has been that I have them at close quarters, I have them where I can readily access memory. But, you know, in reality, if you look at some of the really large chips, right, the distance that must be traversed to gain access to memory, particularly for certain repetitive operations where you have to go to the cache and get it, that has started, you know, it has become significant. Okay, and if once you start talking of, you know, even a 1/10 of a millimeter, now you're talking some very serious distances for travel. Whereas if you look at 3D integration, right, you can start by getting the 3D die to a very thin level, particularly when you utilize strategies such as die to wafer integration, where you can really thin down the dies which have the TSVs, you know, 30 microns, 20 microns, and now you're in a serious race, right? The monolithic method actually cannot do as well as the 3D method if you're looking for very specific things like access to memory. I must have it repeatedly, and I must have it with extremely low picojoule per bit transfer. So if I combine the key elements, right, low latency, high bandwidth, low energy in terms of picojoule per bit, the monolithic option of actually doing an SoC in some of these cases is actually worse. We're not saying 3D is comparable, we're saying 3D is better. You know, there are certainly situations where one may be better than the other, but in very specific examples like AI, where the access to memory is required on a repeated scale and lots of parallel processing is occurring, these options are some of the best you can have, the 3D.
Nice. And I imagine too that it does limit the placement of the parts of the system, because once you want to interpose the parts and so on, you need to have the circuits of the parts of the system in a right position, in an adequate position, to have the right integration. So how much it does interfere in the, let's say, in the generation of the system by a professional tool like any software tool we are accustomed to in universities?
So this is actually a really good question, because one of the things that is vital to any kind of HI solution is system architecture. If your system architects don't from the ground up start using the tools available to them, right, for HI, to look at a three-dimensional integration of the various components in, X, Y, and Z, using a number of these combinations, it is very difficult to come in and retrofit and say, I'll just change this and I will put it. It doesn't work like that. So, we are constantly working with the system architects to basically define the solution from the ground up. So you are 100% correct that if the system architects are not looking at this in a holistic way, retrofitting this is very difficult. Maybe for certain components, you can still do it. You can say, let me, break up my original processor die, let me remove some L3 cache, let me make a 3D configuration. It might work, but it's never going to be as optimized as if your architects had started with this toolbox, for them to work with.
Oh, very nice. Well, okay, I was just wondering about the researching universities in this field, because it looks to me that it's a very expensive as anything in microelectronics, but okay, it is not easy to an university to have access to the opportunity of stacking the chips and so on to get access to this technology. So could you please comment on the role you see for universities in this heterogeneous field?
Yeah, I think universities actually have an important role to play in basically trying to determine how how the architectures can come together, and B, in some specific portions of HI, because from the viewpoint of a development organization or an R&D or research like IBM where I work, you can look at certain aspects, but there are some very key details related to certain developments, which, we see universities really getting into it and talking about how they have developed certain technologies to enable the whole thing to come together. One classic example of this is copper hybrid bonding. So much work is being done at the university level, which really aids aids the overall picture, because as more information on that becomes available, we start seeing its applicability, right? How can the pitch be shrunk? What alignment tolerances are needed? A lot of this work has been done and continues to be done. So there is a finite way to collaborate between industry, research, and the academic system.
Okay, thank you. Okay. So with this, I don't see any other questions. So, okay, I ask the audience if they want to ask something. Let me just see if there is any reaction. So possibly no. So your presentation has been too clear and the people is not asking any questions.
Thank you.
So just me.
Okay. That's a good question. Yeah.
Thank you. Oh, so with that, I would like to thank you very much for your very kind presentation, for your nice discussion, and also for your time. It has been a pleasure to us in Brazil to have you in this Mini-colloquium. Thank you so much.
Thank you, Marcelo. I appreciate the opportunity that you and your colleagues have given me, and wish you good luck with the rest of the conference.
Thank you very much. Well, with that, let me just finalize this day. I will then start sharing my screen once again.
I'll do stop share.
Yes, thank you. So, okay, just some final words to finalize our mini-colloquium. So, okay, let's move on again. I hope you are looking at my screen now. I'm trying to move it. Yes, now I see. Sorry. Well, finally. So as I told you in the beginning of this day, we are in the Ship in the Fields 2021, which would be expected to be presential, but fortunately, due to the outbreak, we are in the virtual mode. But the fortunate thing of the virtual mode is that we are able to see people that we would not be able to see face-to-face. Otherwise, of course, the face-to-face interaction is unpayable, but okay, we are adapting. So I thank you all the presenters for being with us during this day. I would like to remember you that officially the conference, we had today the tutorials day for the SBMicro, the EDS Mini-colloquium, which has been the tutorials for and the SBCCI. And officially the conference starts tomorrow with the opening session here, as you can see. But in the morning, there is a mini course on semiconductor device characterization, a quick tutorial, and I invite the students that are amongst us to have a look on this mini course. It will be quite useful for you that are using to characterize devices in your works independently, if it is a PhD, master degree, or undergrad work, okay? So I would like to finalize thanking the electron devices student went at FEI for helping me to organize this mini-colloquium. I would like to express my gratitude to Professor Michele de Souza and Professor Durga Misra for inviting me to be the tutorials chair and giving me the opportunity of organizing the 2021 Brazil virtual mini-colloquium, as well as the conference general chair. And of course, I cannot finish this mini-colloquium without thanking the people behind the scenes, Rafael Bron, Lucas Zucchi, and Lucas Mota, because they are behind the engine, putting the Zoom to work and to allow the presentations. Although we had some trickies to solve, but everything has gone in a good way, and we reach at the end of this mini-colloquium very successfully with all the presentations done, and I hope people is satisfied as well. So with that, I thank you very much for your kind attention, and I wish you the best for the remaining of the day. And we meet each other during the conference from tomorrow on. Okay, have a good evening. Thank you. Bye-bye.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks, and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things, and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.
You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Tools and outfits. They're practical, give us comfort, create unity. They're part of an identity. At IMEC, we've got tools and outfits too. They help us do our jobs. But underneath them, there's us. And we perform science. Mathematical and accurate data, together with powerful gray matter that thinks out of the box, is the foundation for our creations. And the accumulation of digitization for the continuation of our population is our destination. Need a translation? Here's a simplification. At IMEC, we create possibilities. Possibilities that shape our future. One with healthier people, safer transportation, streamlined logistics and manufacturing, smarter cities, smarter education, and cleaner energy. We use brains and science to advance microchips and software. We combine them to create a meaningful change in our society. Over 5,000 unique people from over 95 nationalities and an extensive network of partnerships give us the capability to revolutionize the world, and maybe even more. IMEC, embracing a better life.
Somewhere, maybe right at this very moment, the next technology breakthrough is about to inspire the next generation of minds, thanks in part to Keysight Technologies. As a future technologies enabler, Keysight goes where the electronic signal goes, helping to unlock measurement insights at leading technology companies, so they can go from an idea to the marketplace faster and at a lower cost. And business is good, because technology is changing at an exponential pace, with more demands for more devices, faster, smaller, longer lasting, anywhere, anytime, smarter, connected. It's inspiring today's megatrends, the ideas that the world's brightest minds are already working on. By quietly partnering with the biggest names in the global technology business, we're helping to realize these future innovations. Their top engineers working side by side with our top engineers to overcome ever-increasing electronic design, development, and production challenges. How do we do it? Measurement, because you can only improve what you can measure. And Keysight has the electronic design, test, and services solutions that lead the industry, helping our customers get to market faster. Let's go back to that classroom. Imagine the potential of using real-time technology to teach and learn, empowering discussion and ideas across the globe, to and from anyone, anywhere. Now let's say that idea requires a wireless device that's 10 times more capable than current technology. That's where we get involved. Before that idea can begin to take shape, Keysight is helping make sure it will succeed, thanks in part to our participation alongside governments and industry leaders in the groups that help create the standards for technologies of tomorrow. We're involved early, which means Keysight can anticipate what will need to change and begin development of design and test solutions while helping to define the new standards. As a result, our customers have an early advantage because we'll supply the expertise they need right when they need it. In the world of R&D, long gone are the days of going straight to physical prototype. Today, it's all about software simulation. It saves expensive hardware prototyping cycles, development costs, time, and no other company is more respected for software solutions than Keysight. In fact, our ESOF electronic design automation software simulates the precise electronic behavior of the components in a customer's virtual prototype. It's the standard used by over 2/3 of the world's high-frequency electronic designers, empowering customers to confidently bulletproof designs long before they're built. As the physical prototype is made, customers turn to Keysight once again to validate that it works properly in the lab and in a variety of real-world environments. These complex tests help prevent losses that technology companies may face if there is an undetected defect hidden in their product. The device is finally ready for mass production, and Keysight is ready to help its customers get the latest, greatest technology into the hands of eager buyers. Tens of millions of units are at stake here. Customers rely on Keysight to keep the line moving with accurate test solutions and tools to help them maintain quality. The result? A bug-free, cost-effective, high-quality product in the hands of people who need it. Faster. If there's a signal to be measured, Keysight is there. From satellites to base stations to mobile devices, our job is to ensure the signal is clear, true, and reliable. It's what we do for communications and beyond. Energy, aerospace and defense, computers and semiconductors, automotive electronics and safety, industrial applications, education and research. In fact, the minds of Keysight have been behind the most important technology breakthroughs of the last century. And today we offer world-class services along with the broadest design and test portfolio of any company in the world. With our global network of experts, we provide an emerging array of services to accelerate our customers' business goals, including calibrating multi-vendor test instruments, managing asset portfolios, and providing training, consulting, and other professional services. As a premier future technologies enabler, partnering with customers to help them move from design through manufacturing faster and more efficiently, no other electronic design and test company is better poised to help deliver what's next. First.
ABCME, the Brazilian Association of Semiconductors Industry, brings together industries and government-owned and private technology, research and development institutes, covering all chains of semiconductors in the country. Established in 2014, its mission is to promote the dialogue and integration of the semiconductor industry with government bodies and research and innovation institutions. ABCMI promotes the development and strengthening of the national chain of semiconductors, from the design to the chip manufacturing, increasing competitiveness and the attraction of new investments. Always guided by principles of free competition and ethical, transparent, and fair relationship with the government, its members, and the society. Its members are established in all regions of the country, producing what can be considered as the most advanced in microelectronics and heavily investing in research and technological innovation. One of the largest economies in the world, Brazil already has relevant participation in the global scenario, second place in banking automation, and in medical technology among emerging markets, fourth in mobile phones, seventh in the computer market, and ninth in the production and sale of vehicles. Moreover, it is expected that Brazil will be prominently ranked in terms of connectivity in the coming years, from the interconnection of productive processes, either of the agribusiness or of the modern automotive industry, to the so-called Internet of Things devices. Due to public policies implemented in the last decade, together with the relevant invests made in the country by domestic and foreign industries, Brazil increases its relevancy in the global semiconductor chain each year. The industries established in Brazil count on state-of-the-art productive technology facilities, with a built area of 75,000 square meters, more than 27,000 square meters of clean rooms, more than 2,500 highly qualified employees, $830 million revenue in 2017, and more than $2 billion of accumulated investments in machinery, equipment, productive and research infrastructure, and human resources training. In Brazil, companies of the semiconductor sector already offer components and devices that are present in most of the electronic equipment used day by day. Projecting, developing, and manufacturing components, since the front-end process aligns know-how, expertise, and outstanding technology throughout the semiconductor value chain. Among the products packaged and tested in the country, there are memory components that deliver the most advanced technology applied by the largest IT companies in the most sophisticated devices in the world, being equivalent to components manufactured in the largest global semiconductor centers. ABCMI members have also been significantly investing in the establishment of research and development centers. An example is the El Dorado Research Institute, located in Campinas, state of Sao Paulo. El Dorado has the country's first semiconductor prototype laboratory. Another example is the ITT Chip, a semiconductor packaging and testing laboratory located at Unicinos, Rio Grande do Sul, which is also the only institution in Brazil to offer a master's degree course in the field. There are approximately 30 research institutions dedicated to the semiconductor sector and around 800 researchers acting in this market, evidencing the relevance of the investments made so far. The semiconductor ecosystem is a driver of the country's technological growth and promotes constant innovation. It is also dependent on continuous and significant investments, which are the result of cooperating among the companies, government, investors, and researchers. The semiconductor industry is strategic and fundamental for increasing of added value of the local industry. It already significantly contributes with the Brazilian trade balance and reduces the dependence on global centers of semiconductor components. There are many opportunities. Only in the Internet of Things field, the economic impact expected until 2025 is about 10% of gross national product. Semiconductors are the brain of the electronics industry and the heart of the technologies that move the world. Brazil is already part of this important universe. IEEE believes in knowledge, innovation, and people as the keys to identify new technologies. Above all, IEEE believes in Brazil. Each new day, technology is more and more present in people's lives. Everyone is more and more connected. Technology does not stop evolving, advancing. Smart modular technologies is at the very heart of all this evolution, developing and innovating in the semiconductor industry. With a large and modern production center, advanced equipment, high-tech, high-precision tooling, machine-to-machine communication, robots, training and advanced manufacturing, prepared for the fourth industrial revolution. Industry 4.0. Smart delivers products that form a tripod, processing and storage, communication, energy. More than 15 years producing semiconductor components for the world's largest manufacturers and dominating the chip packaging technology in Brazil. Memory modules at the forefront of high performance. Lithium-ion polymer batteries provide power to the most renowned devices in the mobile communications market. Approximately 670 million reais were invested in the development, design, and implementation of semiconductor components, such as memories for smartphones and other high-tech memory integrated circuits. And additional investment that can reach 700 million reais by 2021 is already planned. Smart is a global company and is proud to have chosen Brazil to be its technology center for semiconductor components packaging. Strategically located in the city of Atibaia, state of São Paulo. Smart also has a research and development center dedicated to its operations in South Korea. Products with high standards and excellence. 250 million reais have already been invested in research, development, and innovation of products and manufacturing processes. An example of this is the unprecedented investment in the creation of a semiconductor prototyping line within the El Dorado Research Institute in Campinas, state of São Paulo. The worldwide technological evolution does not stop. The priorities for the Internet of Things are already defined in Brazil. Smart is part of the National Internet of Things plan, developing innovations to keep at the forefront of all this evolution. People recognition, training, and specialization. Professionals with the highest levels of academic background. The challenge of further driving and developing semiconductor technology is the challenge of creating the future. Smart works unceasingly to be at the front line of this future. Think memory, think smart. Smart modular technologies, developing technology and projecting the future in Brazil.
What sparks innovation? Is it thinking bigger or smaller? Does it strike fast or slow? Is it a flight of fancy or a stroke of genius? Innovation is everywhere, on desktops, in pockets, on wrists, in us. Innovation answers big questions, finds inspiration anywhere. It connects great minds, imagines the impossible, and propels us forward. At Keysight, innovation inspires us, fuels us to redefine precision in measurement, to surface insights, to remove barriers so the next stroke of genius is yours. We are Keysight. We accelerate innovation.
Designing state-of-the-art millimeter wave products, whether for 5G, defense radars, or satellite communications, requires expanded test systems. Applications at millimeter wave frequencies require wider channel bandwidths and multi-element antennas to overcome increased path loss, which must be tested using over-the-air test methods. Over-the-air testing has traditionally involved more test equipment, more measurement uncertainty, and difficulty getting accurate and repeatable measurement results for chipsets and network equipment. Until now. Testing applications at millimeter wave frequencies is about to get much easier with Keysight's new VXG microwave signal generator. The VXG is the world's first dual-channel 44 GHz vector signal generator with 2 GHz RF bandwidth in a single box. Featuring a dual-channel architecture, the VXG allows quick switching from blocker and interferer tests to dual-channel MIMO and beamforming tests without ever having to touch your hardware. With its ultra-low phase noise and the industry's highest output power, Keysight's VXG overcomes over-the-air path loss challenges without sacrificing error vector magnitude or adjacent channel power ratio performance. The VXG, together with pathwave signal generation, gives you access to a wide range of evolving standards-compliant 5G new radio signals for testing base stations, mobile terminal transmitters, and receivers with channel coding and multi-antenna support. If you are designing, manufacturing, or deploying millimeter wave devices, Keysight's VXG will give you higher confidence in your device's performance, faster. Visit www.keysight.com/find/VXG for more information.
Everything has something to say, but someone has to make it communicate. Talk with Keysight. As the leader in the broadest variety of IoT device testing, Keysight can take on the biggest challenges. Partner with the NB IoT Pioneer and have unparalleled confidence in designs and their reliability at any range. Easily meet compliance requirements, stay flexible to tackle evolving wireless standards, and speed up your time to market. Teach the future to communicate. Test with Keysight and go from idea to now we're talking faster.
Technology now connects everything and everyone, everywhere. From smart cities to smart clothing, we generate billions of new connections that bring us closer, make us healthier, safer, smarter. But the more connected we are, the more challenging it is to meet our expectations. How do you innovate what's next first? How do you keep up with the accelerating pace and complexity? More speed, less power, perfect accuracy, tighter security. The pressures to be first and best are greater than ever. At Keysight, we work with you to design, test, and operate tomorrow's most innovative technologies today. We help you adopt emerging protocols and standards before they're defined. We challenge you to reimagine your innovation processes in automotive and energy, aerospace and defense, wireless communications, networking, cloud, and the Internet of Things. We integrate your development workflow to accelerate your next creation. We make your network stronger, and we bring our decades-long insight research, and expertise with over 500 industry and application experts around the world to help you every step of the way. Our customers are the world's visionaries and innovators. They partner with us to innovate faster across every stage of their development lifecycle and every layer of the stack, making their businesses more productive to gain a competitive edge. They dream, we test. So the next great innovation that connects and secures the world is realized faster than ever.
This is our land, a peculiar patch of earth, filled with possibilities, inspired by tradition. We love the little things in life. We enjoy working hard when we believe in what we're working toward. We always move forward and leave no one behind. We are Flanders. Sure, as the northern part of Belgium, Flanders is ideally situated between Amsterdam, London, Paris, and Berlin. Our roads, our railways, our ports, and our airports form one of the world's best transportation networks. And through the ages, innovators from Flanders have given the world modern map-making techniques, plastics, the contraceptive pill, the World Wide Web, and self-learning microchips. But we're also creators, team players. We struggle and we share. We take risks and care for each other. But above all, we work. Flanders has one of the world's most productive workforces in life sciences, the automotive industry, nanoelectronics, and chemical production. Right here is where you'll find some of the hardest and smartest workers. We don't shout from rooftops, and we don't pursue prizes, but our ambition reaches across the world. We say, strike a deal over a good meal. We're a warm people, especially around the dinner table. So, get a taste of our work. Appreciate the little things, and spend your time in good company. We don't pursue progress for the sake of progress. We're driven by possibility, inspired by tradition. We aim to shape the future, actively, together, on this peculiar patch of earth that we call home.